Hello everybody and welcome to today's video where I'm going to be showing you how to create a full game using Unity's data-oriented technology stack and their entity component system. Now I did just want to put out a massive disclaimer at the beginning before we get into the actual video, because this video was actually created using an older version of Unity's entity component system, the Entities 0.51 version. Now since I've actually filmed and edited this video, Unity has released a new version of the entity component system, which is their experimental 1.0 release. Now this isn't a full 1.0 release, but it does have kind of all the changes to the API that are going to be kind of the standard way to do things going forward. Now this is a breaking change from the 0.51, which I'll be showcasing in today's video. And unfortunately, a lot of the things and the ways that I'm showing how to do things in today's video are completely irrelevant in the experimental 1.0 release and will be that way moving forward. So definitely just keep that in mind as you're following along, that some of these things may not actually be relevant. However, unfortunately, the experimental entities 1.0 package that I've been referencing, it is quite a bit unstable. So I've kind of had better luck and much more stability with the 0.51 version. So at least as of right now in late 2022, if you do want to have the most stable version of the entities package, it's probably best to stick with the 0.51 version for now. So again, feel free to follow along with this video. A lot of the concepts and a good amount of the API are going to be, pretty much the same or, very similar to how you'll do things moving forward. However, just keep in mind that there are some kind of major breaking changes. Of course, I will be covering over, all those things in the coming weeks and months to come. So, it is just very important that you do use the appropriate version of the Unity editor, as well as the appropriate version of the entities packages. I do, clearly say that all inside the video later on. But if you really just want to be sure that you have everything set up correctly, I would highly recommend downloading the packages, the starter project files rather, using the links down in the description below, because everything is basically already set up for you and ready to go. Anyways, with that, I hope you enjoyed today's video. Definitely stay subscribed to the Turbo Makes Games YouTube channel for all the cool new changes coming to the entity component system in the weeks and months to come. Enjoy. Hello everybody and welcome to today's video. Well, I guess you could probably call it a miniature course at this point. But anyways, in today's video, I'm going to be showing you how to create a full game using Unity's data-oriented technology stack and their entity component system. I'm going to go through the entire process from the planning phase to setting up your project, actually developing out the project, adding some polish things to it to make it, a real actual playable game. And then finally, we're going to be creating a build of it so you can package it up and share it with your friends. If you aren't yet familiar with Unity's data-oriented technology stack, basically it is a collection of packages that you can add to the Unity editor that are really optimized for high performance. A lot of these are oriented around data-oriented programming, which is a different programming paradigm than object-oriented programming. We'll be going into the difference between these a little bit later, but there are a number of benefits for creating a game with a data-oriented approach, especially if you're making a game that has a large number of entities, such as a bullet hell space shooter, which is the type of game that we're going to be making in today's video. Now, my main goal with this video is to empower you with enough working knowledge of Unity's entity component system that you could feel confident to go out on your own and create a game that could be used for a game jam or maybe prototype out a larger project. And as you can see, this video is quite long, so I don't expect most people to just watch this through all in one sitting. This is the kind of video that I would highly encourage you to actually just bookmark and then maybe come back to it, maybe, spend a little bit of time each day after work, or maybe go through it over the course of a weekend. And as you can see, I've broken up this video into a number of different chapters. Of course, all the time codes for all those main things will be available down in the description below. Also, I've broken it up into 4 different sections. So the first section of this video is going to be the theory and planning phase. So we're basically just kind of talking about the theory of data-oriented programming and going through a little bit of planning about how we want to plan out our data and data transformations. After that, we'll be diving into the new project setup. So I'm going to be showing you how to set up your Unity editor for, everything that we're going to be needing to do in this video. After that will be the ECS tutorial phase. So this is where we do, all the ECS specific things. So you're going to be learning a lot of new APIs in this section, and I'm going to be showing you how to create a game using pretty much everything ECS. Then the final phase is going to be the polish phase, where we're going to start integrating more features that are kind of standard Unity game engine features, integrating things like mono behaviors to give us more visual effects and user interface and all that type of stuff. So that last phase is going to be dedicated to integrating things from the regular Unity game engine into the new ECS workflow. Now, I know some of you may be eager to just dive right into the tutorial phase, but I would highly suggest that you stick around for the theory and planning phase, just so you kind of get a good understanding about, what we're doing and why we're doing this. I think a lot of times throughout the course of this video, a lot of this stuff might seem a little bit overly complicated for the end result that we're getting. So I hope with the initial theory and planning phase, you kind of get a good understanding about not only what we're doing, but why we're actually doing it. And if you do really want to go out and make your own games with Unity's data-oriented technology stack and the entity component system, it's really important that you understand sort of these core concepts about why we're doing these. And so I do just want to put out a big disclaimer at the beginning of this video. Right now, Unity's data-oriented technology stack is still in the experimental preview phases. Unity says that it's not necessarily recommended for production release, although we have seen a number of production ready projects that have been really successful using Unity's data-oriented technology stack. Also, just be aware that as we get closer to an official 1.0 release, what they're referring to, which we will see sometime next year, some of the API may change from this video, and some of the ways that we do things might end up being a little bit different. But basically, all the main concepts should stay the same, and the ability to think as a data-oriented programmer will still remain the same. Now, throughout the course of this video, we're going to be covering a wide variety of topics, and in the interest of saving time, I'm not going to go super into detail on all the intricate ins and outs of every single little concept. I would just like to give you a working knowledge of all these different concepts though, so you can kind of understand, why we use them and how to use them. However, I'm not just going to leave you hanging. If you are interested in learning more about, any of these concepts, I've pretty much done an in-depth video on like every single one of these that we're going to be going over. So what I'm going to be doing is, I start bringing up a concept, I'm going to go ahead and just slide in a title and thumbnail of a video that you can go to learn a little bit more information about that particular thing. If anything seems a little bit confusing, or like you just kind of want a little bit more information to, understand more about it. And again, if you just check the description below, I'll have direct links to all those videos, so they'll be easy for you to access as well. Also, I would highly recommend checking out Unity's official documentation. It's been getting really good lately for Unity's data-oriented technology stack, and they do go into, very helpful detail about many of these concepts. So I would recommend checking that out as well. Now, by the way, I do have some links down in the description below that will give you access to the starter project files, which is basically just the assets and everything that you kind of need to get up and running. Also, I'll have the completed project files if you do want to reference that. And I will just include a final build of the game if you want to fire it up and play around with it on your own system. Also, throughout the course of this video, I'm going to make it a point to try and not repeat myself as much as possible. So I'm going to be showing you multiple ways to essentially accomplish the same goal. I kind of want to give you as much familiarity with different types of APIs, and maybe give you a little bit reasons about, why we might choose one implementation over another. Also, I do want to familiarize you with as many different implementations as possible, because when you start, running into a problem at some point, you maybe, start doing a little bit of searching and come across some forum threads that are going to be referencing some certain APIs that you may not be familiar with. So I do want to give you, a variety of different ways to, show you how to get to the same goal, so you can kind of understand different parts of code that people may be talking about in forum posts and things like that. Also, once some of the fundamental concepts have been introduced, I'm not going to go like super into detail about, why we're doing every little bit of code. I think that would just be a little bit of a waste of time. I'm really just going to focus on the parts that are kind of new and more relevant to that specific thing. For example, throughout the course of this video, we're going to be creating a whole bunch of data components. And at the beginning, in the first couple, I'm going to be telling you, exactly why we're doing things as they are. But then as we go along in the video, I'm going to just kind of assume that you understand how to create a data component. And I'm just going to be focusing on, what specific data components we're creating and why we're creating them, rather than, the specific reasons about how we're setting a data component up. Also, throughout the course of this video, I'm going to be showcasing a number of console errors and warnings, just because these are common ones that you may come across. And I want you to just have an understanding about how to actually approach these and resolve these errors if you do see them as you're going about debugging them. So there are some things that I'm going to be doing slightly incorrectly or naively at first, just to show you that doing it that way will give you an error message or a warning, and then I'll show you how to resolve it for that particular case. Again, that's not always going to fix your particular issues, but it can give you some information about how to approach these types of problems. So anyways, before we get into the prerequisites for this, I would just like to say, if you do find this video helpful, I would really appreciate if you share this video out with some people who may find it interesting, maybe a coworker, or maybe in some online community that you're part of, or just some of your friends who are interested in game development. That would really mean a lot to me, and I think this video is going to be able to help a lot of people who are just starting to get involved with Unity's data-oriented technology stack. And I would just like to take a brief moment to call out the TurboMakes Games Discord community. If you are really serious about learning more about DOTS and ECS, the TurboMakes Games Discord community is going to be a really great resource for you, not only to learn, but also to get inspired, because there are a bunch of really cool people in there who are all making some awesome things with DOTS and ECS. I know that I personally have learned a ton of things from people in the Discord community, ranging from small little tips and tricks all the way to high level kind of DOTS architecture. So again, if you are really interested in learning more about DOTS and ECS programming, the TurboMakes Games Discord community is going to be a great place to go. You can just go to the web address tmg.dev/discord and it'll bring you right there. So anyways, at this point, I'm going to go ahead and dive into the prerequisites. Basically, I just kind of want to give you a little bit of information about, the specific versions of Unity that we're going to be using throughout this. So in case if you do need to download a new version of Unity, you can start doing that right now before we go into kind of the theory phase and all that. All right, so prerequisite number one is that I expect you to have a working knowledge of Unity in C#. Now, while this is an introduction to Unity's DOTS and ECS, this is not going to be an introduction into Unity in general. And there are going to be a lot of things that are kind of considered more or less common Unity knowledge. And if you know how to make prefabs and drag them into things in the editor, and what a mono behavior is, you're going to be pretty much good to go. But I do just want to set your expectation in case you're not all that familiar with Unity yet. Also, I would highly suggest that you have at least kind of like an intermediate level knowledge of C#. We're going to be going over some concepts that may seem a little bit confusing if you aren't, all that familiar with some of the more inner workings of C#, because again, while this is going to be an introduction into DOTS and ECS, DOTS and ECS in general isn't necessarily a beginner concept. This is not necessarily the most easy and friendly APIs to use, and it is going to take an at least intermediate level of understanding of C# in order to fully grasp these concepts and be able to go out and actually use them on your own. However, I don't expect you to have any knowledge about DOTS, ECS, or data-oriented programming in general. Again, this is going to be an introduction to all these concepts. Now, of course, it would help to have a little bit of an understanding of these things. However, if you don't have any at all, I'm really going to do my best to introduce you to these concepts enough so that you have a working knowledge of them, and of course, give you plenty of resources that I can kind of link off to if you do want to learn a little bit more in depth about any certain concept. Okay, so as far as the Unity version goes, I'm going to be using Unity 2021.3.4. The specific version of the entities package that we're using is the 0.51 version. It's only compatible with Unity 2020.3.30 and newer, or if you're on Unity 2021, you need to be on Unity 2021.3.4 or newer. And again, with this video, I'm really going to be showcasing all the latest standards that are available with this 0.51 version of the entities package. However, I am still going to be showing you some things that were how we did things in older versions of Unity. Again, just so you have some familiarity with these concepts. So if you ever do run across them in some research, you have an understanding and at least a little bit of familiarity about what's going on. Also, you want to make sure that you're using the proper IDE that supports source generation. So this is going to be Visual Studio version 2022 and up, as well as Rider version 2021.3.3 and up. In this video, I'm going to be using JetBrains Rider, I think version 2022.2, but as long as you're using either Visual Studio or JetBrains Rider, you should be able to follow along with this video. Just note that there are some issues with Visual Studio, unfortunately, that people have ran into, specifically when it comes to compile times and things of the like. But I'll go ahead and leave some resources down in the description below if you do want some information about how to alleviate some of those issues that you're experiencing if you are using Visual Studio and you are running into some very slow compile times. Okay, so now let's go ahead and dive into the theory phase here. We can talk a little bit about what is DOTS and what even is data-oriented programming. Now let me talk a little bit about the differences between object-oriented programming and data-oriented design. So I'm sure many of you are familiar with object-oriented programming because that's what Unity uses by default, and also is what most of the other common programming languages are built around today. And in object-oriented programming, of course, as the name implies, everything is centered around objects. So we can have something like a car that has some certain properties about it, what's its acceleration rate, what's its top speed, how many wheels, how many doors does it have, all things like this. But it also has functions. It has, the ability to press the gas pedal and go forward. It has functions to allow the doors to open and drivers to enter and exit the vehicle. And object-oriented programming is nice because it is very human understandable. Us humans can really easily wrap our brains around object-oriented programming because it's basically the same way that we interface with the world. We have different objects that have some certain properties about them, and they also accomplish different things for us. And of course, with object-oriented programming, we can do all sorts of nice abstractions where we can have, say like a base car class that has some, certain things about it. And then we can have child car classes that can kind of override those different things. So, maybe we have different properties if we're driving a sedan versus a pickup truck. And again, us humans can kind of understand, we see that, a sedan has a lot of similarities to a pickup truck, but there are some key differences. So again, it all really makes sense to us. We can kind of, intuit those abstractions and see, okay, both of these things have 4 wheels. Okay, but maybe the tires are bigger on one versus the other. And then you'll know, of course, if you've ever gone to, say, create something like a car in Unity, you'd probably create some car controller script. So maybe you'll create a mono behavior with some serialized fields for the move speed, acceleration rate, and all that. And then you'll also have some functions that can, allow the car to drive forward and steer and have passengers enter and exit. And again, this is all very easily understood and intuited by us humans. Now, data-oriented design, on the other hand, is a little bit different because we're actually more optimizing for how our computer stores and processes data versus how we intuit and understand things about our world. Now, really the main idea with data-oriented design is separating out our data from our logic. We're really orienting everything around the data versus the objects. So instead of thinking about an object and what properties and functionality that it's going to need, it's actually better to take a step back and just thinking about, how the computer actually sees the problem. And the computer basically just looks at the data. So you say, okay, so I have some goal that I want to accomplish. What is the input data that I need? And then what is the output data that I need? And then from there, once you have the input data and the output data, then you can come up with a transformation. You say, okay, how do I take this input data, transform it in a way that it goes into output data? But really the main important part here is that the data is completely separate from the transform. The data is standalone, and we can store it in memory in such a way that it leads to very efficient storage and processing of that data. And one way to demonstrate the benefit of this concept is by going into AOS versus SOA. So that is array of structs versus structure of arrays. Now, when we typically think about, Unity mono behaviors or any type of object-oriented programming, let's say that we want to make a collection of all the particular characters that are in a game world. So typically what we'd do is we'd take some basic collection like a list, and then let's take all the characters in the world and store them in that list. And again, that makes sense for us humans because we're, taking all these characters and we're storing them in a list, and we can just access that list to get to any of those characters that we need. However, there are a couple technical problems that happens when it comes to this. For starters, with object-oriented programming, that data is stored in all kinds of different places in memory. So when we actually have a list of these characters, we don't actually have a list of all that data. What we really have is a list of pointer references to different portions of data. So, we look at, say, the first element of the array, it's going to point to one location in memory, and we go to the next element of the array, it's going to point to a completely different portion of memory. Now, basically this means is if we're iterating through the array, we want to say, check all the characters in the game to see if they fit under some certain condition. Well, that's going to be a little bit of an inefficiency because we're going to have to be going, bouncing back and forth between all different places in memory to find the characters that meet that specific criteria that we're looking for. So that's one potential issue. Now, another potential issue is, let's say for the sake of argument, we'll just go ahead and allocate all these new characters when we create them at the exact same time. So they would theoretically be at pretty much all next to each other in memory. So we kind of, remove that issue that we have with all these random accesses from going in different places pieces of memory. Again, this is just kind of for sake of argument here, but even in that case, we still end up with an array of structures. So basically what happens is, let's say we want to move all the characters in the world, forward by 1 unit or something like that. Now for that, we would basically need to modify the world position component of every single one of those characters in our game world. Now, again, there's going to be a little bit of an inefficiency here, is because with an array of structs, basically each character in the array is going to have all its components next to each other, followed by all the components of the next element of the array, and so on. So basically what's going to happen is, if we were just want to modify the translation of each one of these things, well, we're still going to be making some kind of jumps in memory. Even if the elements are still all pretty close to each other in memory, maybe not everything fits nicely in a cache line. So we still may end up having to go out to a lower level of cache or RAM just to get to the next world position component of the element of the array. So as you can see in this diagram here, basically if we're just looking from left to right and we're just hitting, say, the world position on each of these, well, again, we're going to have to skip over some data. Now, when we think about data-oriented design, we can structure things differently. So we can actually use a structure of arrays. So that basically does, say, a 90-degree turn on this. And this is really great for a couple of reasons. Now, we don't really need to worry about all the nuts and bolts of how this works, because Unity ECS does take care of a lot of this stuff for us already. But basically, when we say create some new entities that have some data associated with them, they end up getting put in a structure of arrays. So if we say want to have all the characters in our world, well, they're going to be stored in such a way that they're all right next to each other in memory. And not only that, all the data types of similar types, so say, all the world positions, those are all going to be grouped together first, followed by all the data of the next type. So say we'll have all the rotation components next, and then all the mesh components after that. And again, this is really great, especially for operating on a large number of entities, because if we say just want to modify the world position component of each of these entities, well, we can just go right through and hit all those very quickly, because when we access the first one, the next few are all going to be stored right in that cache line, so we can very quickly and easily update those. And with data-oriented design, we want to treat everything as if we're operating it across a batch of entities. It doesn't matter if we have, say, 1,000 entities that we want to operate across, or just one entity. We want to treat it as if we're operating across a batch of entities, because that's how we're going to get the best performance out of our data-oriented design. So just to start off with a couple definitions. So if we think about DOTS, this is the data-oriented technology stack. Now, DOTS isn't necessarily something by itself, but DOTS is really a collection of packages. The packages that we are going to be using in today's video are going to be the entity component system, the job system, the burst compiler, as well as the new Unity DOTS physics package. So just to go into a little bit more detail on these, I'm going to be getting back to the entity component system because that's going to be the main one that we're focusing on. But the job system, many of you may have heard of this already, but basically it's a way that we can enable multi-threading in the Unity game engine. Basically the way that it works is we're going to create some type of work that's going to be compatible with the job system, and then we're going to be able to schedule that work. Then the job system does this, really cool thing where any of the work that's scheduled, it's going to have, any of the available threads on our computer, basically can pull in from that work queue and actually perform that operation. Now we do need to make sure that the work that we're scheduling is actually compatible with the job system. And that means that we can basically only operate on simple data types like integers, floats, bools, or other blittable data types. Now, when it comes to the C# job system, one important concept to note is the concept about job dependencies. So basically, because we are operating across things on multiple threads, we can't always guarantee thread safety. So basically what that means is if we're, say, iterating some work across multiple worker threads, well, those different threads can't actually talk to each other, and they don't really know which data that each other one is going to be operating across. And job dependencies start to get really important to consider, especially when we're scheduling many different types of jobs. Now, as we go along in the video, you're going to see what's going to happen is that we have one job that, say, maybe writes to some data component, and then we're going to have another job after that that's going to read from that data component. And this becomes a little bit of an issue because when we say schedule these jobs and that work is now put in the work queue, well, we can't necessarily always guarantee that one job is going to be completed before another job. So that's where the concept of job dependencies come in, where we can say, hey, we have one job that depends on another job. And that basically means that that job that has that dependency needs to wait for that job to be completed before it can begin executing its work. Again, this most often comes in when we have, say, a job that modifies some bit of data, and then another job that's going to say read from that bit of data. Because we could start to end up in some really weird situations where sometimes some bit of work, runs before or after another job that is modifying some data that other job needs access to. And with Unity ECS, this is something that Unity takes care of for us for the most part. However, there are ways that we can manually modify the job dependencies and set things specifically, which we are going to be using in a couple of cases. Next up would be the burst compiler. Now the burst compiler is really great because we don't really have to do a whole lot of things to get it running. And basically it is subject to a similar amount of restrictions that the job system is, where we need to use, basically only very simple data types. We can't use any like Unity game object mono behaviors or anything like that. It's really a way that math operations can be optimized so we can run a bunch of these operations really quickly. A lot of it takes advantage of SIMD, which is single instruction, multiple data, which basically means that we can have multiple bits of data and combine that into one instruction in the CPU to really optimize the processing of large amounts of data. And it is really one of the main gains of performance for Unity's data-oriented technology stack. It really is incredible tech. Next up is the DOTS physics system. We're not going to be using this for anything too crazy in this particular example, mostly just for collision detection, because that is something that is kind of important to most game development. One interesting thing to note about the DOTS physics system is that it is a stateless physics system, which means that entities don't have any, say, collision states. So that means we don't have any equivalents of, say, an on collision enter or an on collision exit or things like that. You'll see that when we actually do get to the part where we are doing any collision detection, basically we can only detect if something is collided with another thing or not, when we basically can't tell, when that collision started or when it ended. I should say that that's kind of the case out of the box. We can add that functionality in if we want to, but in this case, we don't need to. And you might see this as a bit of an inconvenience, but it's one of those things where, the performance gains are really great for the new physics system, and then you kind of have to just weigh out that convenience in the performance for your specific applications. Okay, so now we'll circle back to the entity component system. Now, an entity component system isn't anything specific to Unity. In fact, the entity component system is a concept that has been around for decades now. Now, an entity component system actually represents three different things: entities, components, and systems. So this basically means that we're going to be separating out our data from our entities and from our systems, and our systems are the things that actually transform that data so things happen within our game. Now, if you are familiar with Unity, which again I highly suggest that you are before following along with this video, then you'll know that Unity is actually a little bit of a half step towards a full entity component system. This can actually be considered more of an object component model, because we have things like game objects where we can actually apply different components to them in the form of mono behaviors in order to add or remove functionality from game objects in our game. Now you'll see that one of the great advantages of the entity component system is being able to do just that. We can easily add or remove components from different entities to change how they behave within the context of our game. Personally, that is one of my favorite reasons for using the entity component system. But before we get into that, let's kind of take a little step back and actually go into, what are entities, components, and systems. So what exactly is an entity? Well, an entity isn't really anything, to be honest. An entity is just kind of a way that we can say index into some bits of data, that we can say, all these bits of data are all kind of grouped together. We can kind of consider them all as one entity. And the reason that we may want to group some bits of data together is to basically create different things in our game. So in this example, we're going to have a player ship, and we'll consider that player ship an entity, and then we'll have some components on it to give it some, say, movement and collision properties. However, you'll see that we can start getting a little bit creative about, what exactly is an entity. So, not everything related to the player ship is all going to be part of the same entity. In this case, we're actually going to have maybe some child entities that are going to be taking care of other aspects of the entity, such as rendering the mesh and doing some other useful things for us. And then we'll move on to the components part of the entity component system. So this is the actual data. And again, we're using data-oriented programming here. So of course, this is an extremely important part of this. So the data is basically going to be the driving factor for how our entities behave in our game. So for example, we could maybe have, say, a move speed data component, and this is going to store, how fast in, say, meters per second that this particular entity is going to move throughout the game world. However, it's not always just static data like that, but it can also be dynamic data. So maybe we have, say, a counter for ammo count, and every time that we fire our weapon, that ammo count will go down by 1. Now that actual data about the ammo count is held by itself, and there's no functions on that particular data component that say, how to increase or decrease the ammo. That's all taken care of in systems, which we'll be getting to in just a moment. Now, I should point out that the actual data is stored in 16 kilobyte blocks of memory known as a chunk. Now, in discussing chunks, this is where we start to step into the territory about, why the entity component system is so efficient. Now, one of the reasons is because all data associated with a particular entity is going to be stored within the same chunk. So that means that, whenever we're doing operations on a particular entity, we can access all data on that entity very quickly, because more often than not, when we access one bit of data, the rest of that is all going to be inside the cache. Now, if we say create multiple entities that have all the same sets of components, now we can fit all the data for multiple entities within that chunk. Ideally, we want to keep our chunk utilization in mind so we can fit as many entities as possible into a chunk, which is going to lead to the most efficient processing. Another efficiency of these chunks is data of the same types are going to be stored next to each other. So for example, say if we have an entity that has a world position and a move speed data component, then all the world positions for all the entities in that chunk will be right next to each other, followed by all the move speed components for those particular entities. So what this means is if we're trying to move a large number of entities through the world, which was what we're going to be doing in this bullet hell type game, we can do this very efficiently because we can just go through all of those world positions and update those as needed. And we're pretty much always going to be pulling in this new memory from the CPU cache, which is a whole lot more faster than going out to the RAM to find that data. Now, all the entities that are in the same chunk are guaranteed to have the exact same data components. Doesn't mean that all the data values on them they're going to be the same, but they're going to have the same makeup of data components. Now, this makeup and unique combination of data components is known as an archetype. So in the example of this project, we're going to have an archetype for player ships and a separate archetype for enemy ships. So now we can get into systems, and probably as you've gathered by this point, systems are the actual transformations of data. This is when we take, say, some bit of data, do some transformation off of that, and write it to either back to that data component or to another data component. So it's basically a way for us to actually do things in our game. So again, back to the example of, say, moving an entity through the world, maybe we can look at the world position of an entity. We can also take into account the move speed of that entity, do some calculation on them to figure out how far we need to move an entity any given frame. And then we can write that back to the world position component so it's updated in the world. Now again, these systems are completely separate from the data. And this makes it really nice because when we're going through and prototyping things, if we want to try out, multiple implementations of things, we can create just brand new systems, disable ones that we're testing, and enable new ones to, try out and see how it works. Now, again, the way that we really get the efficiency out of systems is to run these systems on groups of entities. And we always want to treat as if we're running on a group of entities. Even if we're only going to be running it on one entity, we still want to treat it as if we're running across a group of entities. And basically the way that we say gather a group of these entities is through a concept known as an entity query. Now, an entity query, the way that we do this in Unity ECS most often is going to be to say, hey, let's go ahead and define a set of components that we want. And from that, it will basically return us this entity query, which represents a group of entities that we can run our systems across. Now, I should point out that when we execute one of these entity queries, we're not necessarily just going to get one entity archetype back. Oftentimes we could get multiple entity archetypes back. So for example, if we say did an entity query on anything that has a world position and a move speed, well, not only are we going to get our player ship, but we could also get our enemy's ship, and we could also get the bullets and the shots that are moving about in our world. So we really just need to take into consideration, how we're structuring our entity queries, and we're making sure that we're just grabbing the entities that we want and not getting any extra entities that we don't want. And then finally, I just wanted to go over the concept of what a world is. Now, a world is basically just a collection of entities and systems. So this basically, represents all the entities and all the systems that are running across those entities. It is possible to have multiple worlds, and this is, really handy for things like multiplayer. But in this case, we're just going to be using one world, which is the default world. Sometimes you'll see it referred to as the default game object injection world, but basically just note that a world is a collection of entities and systems. Okay, so now let's dive into the planning phase for this project. Now, the planning phase is definitely important, but I don't want you to get this in your head that this is, the end all be all and everything that you create in this planning phase is going to be the final way that you do things. I think the planning phase is really important, and some of the exercises that we'll be doing here are just a good way to get you started. And again, kind of thinking in that data-oriented mindset, thinking about how to structure things out in your project, but don't treat it as like the most important part of your project here. So let's just kind of get a base understanding about some of the features that we want in our game. So in this case, we want to have a player ship. We want it to be able to move around throughout some world, and we want it to be able to fire weapons. We also do want to have enemy ships. Now, these enemy ships basically need to be spawned into the world at random locations, and these enemy ships will chase down our player and fire its weapons at our player. Now, these ships will need to be able to detect collisions with these shots that are being shot out into the world, and then when they are, it's going to go ahead and decrement the hit points of a given ship. Once that ship reaches 0, then it's going to go ahead and destroy that ship. If that ship is the player, then we're going to go ahead and kick ourselves over to a game over screen and give our players the options to say restart the game. Now, that is kind of the things that we want on a base level, but of course we want to go ahead and add some juice to it. So let's go ahead and add some, visual effects, some sound effects. We're going to go ahead and integrate Cinemachine to have our camera follow the player around the world. And overall, it's just going to be a dang good time. So at this point, really just kind of consider, what are the features that you want to have? This is probably no different than what you would do for any old regular Unity game. Now, at this point, it's important for us to consider the data layout. So, what are the main data components that we're going to be having in our game? And then what entities are going to need those data components? And finally, we're going to go ahead and add in, the systems that are going to be operating across those data components. So let's go ahead and create a little bit of a chart like this. Unity actually does have a best practices guide on their website where they do show off a chart just like this one and how that you should kind of go about filling this out for your particular project. Now, we're just going to do a real small version of this. It's not going to cover every single data component and feature that we're going to be adding in our game, but I do just want to give you an idea about how you can fill this out for your projects going forward. So we're going to go ahead and start out with the components that we need. So we know that we're going to have to basically be able to move around within our world. So we'll go ahead and add in a position and rotation component. We also need to consider the type that this data component is. So the position one is going to be of type float3. This is kind of similar to a vector 3, but it works a lot better with the burst compiler, so we can really get some good performance gains out of it. The rotation is going to be of type quaternion with a lowercase q. This is another one specific to the Unity.mathematics library, which is kind of the data-oriented mathematics. Again, there's kind of some efficiencies that can be made with the burst compiler and so on, but just having a position and rotation isn't enough. We actually want, say, our player to move about throughout the world. So let's go ahead and keep track of a move input. This is going to be a type float3. Even though we're really only going to be moving in the X and Z directions, it's just easy for us to keep track of this in a float3 type. Now, for the enemy ship, we want this to basically follow our player around. So we're going to need a way to reference our player's entity. So we can go ahead and give them a target entity component of type entity. Now, of course, we want these ships to move around in the world at some type of speed. So we'll go ahead and add a move speed, which is just going to be a float scalar. Also, we can have something like a rotation speed, so some can rotate faster or slower. So now you can see when we go ahead and add in our player ship and our enemy ship archetypes, they're going to have the components that are relevant to them. Of course, both of them are going to have a position and a rotation, but only our player ship needs a move input and only our enemy ship needs a target entity. Of course, both of them are still going to have a move and rotation speed though. Now let's go ahead and also add in the third main archetype that we're going to be using, and these are the shots. These are actually the bullets that are going to be moving around in the world and hitting the different ships. Of course, these will also need a position and rotation because they're going to be moving throughout the world. It doesn't need a move input or a target entity because they're just going to be moving in a straight line. However, they still will need a move speed. Now, they don't necessarily need a rotation speed because they're just going to be moving in a forward direction, so we don't need to worry about that. But let's say we want to add in one more component on these because we don't want our shots to just, go out into the world forever. We do want them to clean up after some bit of time. So let's go ahead and add in an entity lifetime component there. So these are kind of the main archetypes and the data components that we're going to be adding to them. However, in practice, there are going to be many many more data components that we will actually be adding. But again, these are kind of the main ones to get ourselves into that data-oriented mindset. Furthermore, we can start planning out our system. So let's go ahead and just extend out this chart just a little bit here and go ahead and include some systems here. So for example, we can say start with the move player system. So at this point, we kind of need to consider a couple of things. So we need to know which components this system needs access to. We're going to need to determine if it has read-only access or if it needs read as well as write access. And then finally, we need to determine sort of the general magnitude about how many entities this system is going to be running against. So for our move player, for example, we're going to need read and write access to both the position and rotation, because of course we need to see its current position and rotation. And then we're going to need to write an updated position and rotation to it. As far as the magnitude, of course, we're only going to be running this against one entity because our game is going to be designed with only one player in mind. Next up, we're going to need read-only access to our move input. Of course, it's going to happen only on one entity. And then same thing with our move speed and rotation speed. We're just going to go ahead and read in from those. Now, there is something important to note. Basically, the move speed and rotation speed, those are going to be fixed set at the beginning of the game. However, the move input, that's something a little bit more dynamic. That needs to be happening throughout the duration of our game. So maybe it makes sense to actually, before our move player system, we'll go ahead and do a get player input system. And all this needs to do is write to that move input component. Again, we're going to be running this on just that one single player entity. So we just need to make sure that we're running, say, our get player input before we actually go ahead and move the player. Now for the move enemy system, we can do something a little bit similar, where again, it's going to need read and write access to the position and rotation. And then we're going to be reading from the target entity move speed and rotation speed. Now for the magnitude of these, we can say 100 entities. For the cases of this, we figure probably the maximum that we might want to have in the world at any given time would be around 100 enemies. That would be pretty hectic if we did. And the reason that we're actually considering, how many entities these systems are going to be running across is we can kind of make some determinations about how efficient a system needs to be. For example, for the move player system, we're only running that against one entity. So in theory, the move player system could be a little bit less efficient than the move enemy system. Obviously, we would want to prefer everything to be as efficient as possible, but this just kind of gives us some understanding about, we need to really make sure that we're making this system very efficient. Now for the target entity, we will need to set that at some point. So we're going to go ahead and create a new system. This would be the get target entity system. Now I'm going to say that we're only going to be writing to this on one entity at a time. The reason for that is because the way that I've designed this project is that we're going to have an enemy spawner, and this enemy spawner is just going to spawn one enemy into the world every few seconds. Now, every time a new enemy spawns into the world, we're just going to go ahead and run this get target entity system one time. So again, this is something that we don't necessarily need to be super efficient on. That's okay if we have a slightly inefficient system, because this is only running against one entity once every few seconds. And then just to round things out, let's go ahead and add in the move shot system. Of course, this is going to need read and write access to both the position and rotation. We're of course going to be reading from the move speed, and then we're going to be doing read and write to the entity lifetime. The reason I'm saying that we're reading from and writing to is because we're going to be updating the time of that every frame. Basically, we're going to have a counter that's counting down to 0. Once it reaches 0, we'll just go ahead and destroy that entity from our world. Now, if you figure we're kind of maxed out around 100 entities, and each of those are shooting about 10 shots into the world at a time, so maybe that kind of gives us a high end for this move shot system of about 1,000 entities. So at this point, just kind of looking at this, we want to really make sure that we're being very efficient with our move shot system, because that's going to be something that's running every single frame across a relatively large number of entities. Okay, so now let's actually get into setting up this project. You see that I'm over in the Unity Hub. I've created a new project here. I'm going to be using Unity 2021.3.4. Again, this is compatible with that 0.51 version of the entity component system. You see that I'm currently using the 3D template. Now you can use the URP 3D template if you do want to kind of have some of the URP stuff set up for you already, but I'm just going to go ahead and use the regular 3D template so I can show you everything that's needed to set up the hybrid render correctly. So you see the project settings, I've just called this the DOTS Space Shooter project, and I've just gone ahead and saved this to my typical Unity directory here. So anyways, we'll just go ahead and create this new project. Okay, so now we have Unity opened up. Now the first thing that we're going to do is just install all the correct packages so we have all those ready to go. So anyways, just go up to Window and Package Manager, and then once the Package Manager has loaded up, now we can actually install all the proper packages that we need. Now the thing with the Unity ECS ones is it's still considered an experimental incremental preview package. So it's actually not available through the package manager as you would normally expect it would be. So you do actually have to add it in a special way. You go up to this little plus button, and then we can just say add package from get URL, and it'll ask you to actually type in the get URL of the packages that you need. Now I know that the one that I'm going to need here is the com.unity.rendering.hybrid. So it's always best to just go ahead and add the hybrid renderer first, because the hybrid renderer is what we use to actually render entities within our game. And then the nice thing about adding the hybrid renderer is it adds all the regular entities packages that we need. Now you'll notice that we didn't specify a version number or anything like that. When we do that, it's actually just going to go ahead and install the latest available packages to us, which is generally what we want to do. However, if you do need a specific version, there is a way that you can do it through the get URL, but it's typically best recommended to actually go into your packages manifest file and manually add in all the packages that you need through there. Okay, so now that we'll see the hybrid renderer has installed, you see that it is version 0.51 here. Now one thing that we can actually do is if we go to the advanced project settings, and over in our project settings window, we can actually check mark the box for show dependencies. Now it's actually just going to go ahead and show basically all these other packages here. You'll notice that the hybrid renderer does have a dependency on the entities package, so it basically automatically installed the entities package. Now if we go find the entities package, which is right here, you'll see that it is using all these other packages. It ends up being kind of a cascading effect where you install the hybrid renderer, which installs these entities packages, which installs the other needed packages that you need here. However, we're not quite done yet. We do have a couple more packages to add. Another one from the get URL, which is going to be the com.unity.physics. So that's going to be the dots physics package, and that's going to allow us to do collision detection and things of that nature on the entity side. And then the last few that we're going to need are all part of the Unity registry, so we can just flip over to that drop down right here. First one we'll need is the universal render pipeline, which is just under universal RP. I'll go ahead and install that here. Now we do need the universal render pipeline because the version of the hybrid renderer that we're using does require universal render pipeline and will not work with the built-in render pipeline. And then the final one that we're going to need to install is Cinemachine. And now we're just going to be using Cinemachine so we can have our camera kind of follow our player around the world all nice and easily like that. Also, if you do want to install the Pro Builder package, now would be a good time to do that. I did use Pro Builder to create some of the meshes that we are going to be using in today's video. However, this is not necessarily to follow along with the video. Again, if you download the project files, you'll kind of have all the meshes already. But if you do want to create your own meshes through Pro Builder, feel free to do so. Just be aware that right now there are some issues using Pro Builder when you want to spawn entity prefabs. However, I did create a video showing you how to fix this issue. Basically, you just need to export your meshes through Pro Builder to a regular mesh asset. So anyways, we'll go ahead and close out of the package manager. Now we'll switch over our layout. Again, this will all be included as part of the initial project files, but you can switch over to this ECS 0.51. And then let me just give you a quick rundown of what we have here. Of course, we do have the scene view and game view, just kind of as you would expect here. I am going to change this over to a 16:9 aspect, so all the UI that I've created shows up how I want it to. Of course, we just have our regular Unity hierarchy right here. You can see we can expand this sample scene, and we just have a camera and directional light in there right now. I've also included this tab for the dots hierarchy, so when we start creating things on the dot side, all these entities are going to start popping up in here, so it's kind of nice to just flip back and forth between the regular hierarchy and dots hierarchy. If you do not have that window or any of the other ones that we're going to be talking about in just a moment, you can just go up to Window, Dots, and then you'll see there's the Archetypes, Components, Hierarchy, and Systems window here. Now down below, I do have the console, so of course if we have any errors, which we will, we are going to see them in here. Next would be the Archetype window. We don't really use this one all too much, but I do have a video just kind of going over what all these ones do. Components one, again, we don't use it too much. And then the Systems window, it is kind of nice to see how our systems are all ordered, and we can easily disable a system for debugging purposes if we do want to there. Of course, then I do just have the project view here. I do have two inspector tabs. I like to just kind of keep two in case I need to lock something or use a debug menu. And then I also do like having my project settings just readily available. Okay, then I've just gone ahead and created the folders that I want. So you'll see that I have just kind of some art for the different types of art assets that I'm going to be using. I do have a prefabs folder and another folder inside there for game object prefabs, because we will have both entity and game object prefabs. Of course, the scenes folder. Under the scripts folder, I do have a couple subfolders, one for authoring and mono. These are going to be, typical mono behaviors, and also something known as authoring components, which we will get to later on. We also do have components and tags. Those are ECS specific data components. Helpers is just going to be something for a couple little helper functions that we're going to need. And then systems are actually going to be the data transformations. So it's kind of nice to, have things kind of separated out like this. It makes it a little bit easier for tracking down files and things like that. And then finally, I do have a settings folder in here. So in the settings folder, we're just going to go over here, and we do need to enable the universal render pipeline. So we'll just go to create, then down to the bottom to rendering, and we will make our URP asset. And we can just call this the URP asset. Pretty much we can keep all the settings on the URP asset as is, and then we'll just need to drag the URP asset over into the scriptable renderable pipeline settings. We'll just go ahead and click continue on the little window that pops up here. A couple other things that we will need to do in the project settings. The next one here is going to be changing the color space to linear. So we just go over to our player settings. You'll see that rendering the color space is currently set to gamma. We'll just change that over to linear, and again, just accept that change there. Next up, we're going to enable our fast enter play mode settings. So this is going to make editing really nice and easy for us to use, because basically right when we hit the play button, we're going to be immediately into play mode. So it's really nice to do that. So again, in the project settings, you'll just go to editor, and then you're going to scroll down to the enter play mode options. You just go ahead and check mark that box, and then leave the other two options unchecked. So again, those are going to be the fast enter play mode settings. And then finally, we'll just go over to the Text Mesh Pro option, and we're just going to go ahead and import the TMP essentials, because we will be needing those for some of the UI that I've created. Okay, so now I just went ahead and imported all my art assets. So you'll see that I do have kind of some background art assets, a couple audio assets for some music and sound effects, and then a couple materials here. Take a look at these materials. They're just URP lit materials, just a red one, a green one, and kind of an orange one. Nothing really special there. And then for the meshes, again, I do have two separate meshes, one for the enemy ship and then one for the player ship. They're basically the same thing, just the enemy ship is a little bit wider to kind of differentiate the two. And then a couple last things that I did want to mention as far as the Unity setup goes. Just go ahead and check our dots settings. We'll go up to our dots and conversion settings. We'll make sure the live conversion enabled is checkmarked, as well as the live conversion runtime state in scene view. Basically what that means is that when our entities are going to get converted to entities at runtime, I'm going to display those properly inside of the scene view. Also go over to jobs and burst, and we'll just make sure the enable compilation box is checkmarked. Sometimes during debugging, you may need to actually disable this to get a little bit more information on some errors, but by default, we do just want to have enable compilation turned on, because that's going to give us the best performance. Also, under safety checks, we'll just go ahead and set those on for now, which is fine. Also, in leak detection, right now it's currently set to off. If you want, you can turn that to on, which is going to be, a little bit more costly, but it will give you some more information about some errors in your project. And then the full stack trace is expensive. Only use that if you absolutely need it to. Okay, so you'll see that I've gone ahead and set up a couple of the sprite renderers in the game. You'll see that I do just kind of have these star backgrounds kind of scattered out here, as well as these closer up asteroids. Now, later on in the video, we are going to do a little bit of a parallax effect where the star backgrounds are kind of moving at a different rate. And I did make sure the asteroids and star backgrounds are on their own sorting layer, and they are sorted in the proper manner. And then the other thing that I did also set up is the main camera. If we go over to that, I have the projection set to orthographic, and it's at a size of 100. And it is also at this position right here. Okay, so now that we have our project set up, we're ready to actually start creating some things in it. So we are going to start with creating our player ship. So we'll just go ahead and create an empty game object here. We can just call this our player ship, and we'll just go ahead and set this to the origin for now. Now what we're going to do is we're going to go ahead and check mark this box for convert to entity. That is going to convert this game object to an entity at runtime. There are two options for convert and destroy, as well as convert and inject game object. The convert and destroy method is what we're going to be doing here. So if you see, if we actually hit the play button here, you see that the player ship no longer exists in our sample scene, and it's not tucked away in this don't destroy on load. However, if we do go over to our dots hierarchy, you see that we do have the player ship. However, you'll notice that it is invisible right now. So we're actually going to go ahead and add a renderer. Now the renderer is actually going to be a child of this player ship, and I'll get to why that is in just a moment. So we'll just go ahead and create create an empty game object child, and we can just call this renderer right here. You'll notice that the convert to entity box is basically checkmarked by default. It says by ancestor, and there's no extra convert to entity component on there. Like if we go back to the player ship, you see that we do have this convert to entity component. So let's go ahead and on our render component, we'll add a mesh filter as well as a mesh renderer. So we'll just go ahead and select our player ship mesh, and then under materials, we can go ahead and select our player ship material here. Now, the first reason that we kind of do this parenting is so we can set the position like this, just so the actual pivot of the player ship is going to be kind of at this position, like sort of around the cockpit. And basically that's going to be our pivot for our like rotation point and everything like that. So, you know, actually all the logic of moving the player ship and collision detection, that's all going to happen up on this parent player ship entity right here. And this renderer, this basically just serves the purpose of displaying that mesh on the screen. And now another reason that we actually do want to go ahead and separate out this renderer component is because oftentimes these renderer components, there are a number of them. Actually, if we enter play mode right here, you see that now we do see actually something within our scene view as well as our game view. Now, if we do go over to our dots hierarchy, you'll see that again, we have our player ship, and this time we can actually expand this little drop down and we see our renderer right here. Now, you'll see that there are actually quite a few components that are basically associated with rendering. You know, we kind of have some of the default translation ones, and then we do have, you know, all these ones here about, you know, different material properties and render meshes and all sorts of things. And this bit of data can actually add up. So if we did actually want to have this all on our parent ship, that's going to kind of lead us into a situation where, you know, maybe we cannot fit as many entities inside of a single chunk. Now, kind of going back to the concept of what a chunk is from the introduction portion of this video, but basically a chunk is, you know, a 16 kilobyte block of memory where we can fit, you know, all the components associated with entities into that. Ideally, we want to fit as many entities into a chunk as possible, and that's going to give us the best efficiency in our application. So sometimes it does make sense to sort of break entities up. You know, it's not always necessarily that one entity is going to have everything associated with one component. A lot of times we are going to be breaking these things up into multiple different entities. Okay, great. So now we have our ship rendering within our world and it looks wonderful. Now let's actually get it to move around. Let's kind of start to explore this space that we've created a little bit here. Okay, so now I've switched over to my IDE. Again, I'm using JetBrains Writer because we're going to start actually programming some things here. Now, again, the first thing that we're going to be doing is actually moving our player around. Now, in order to move our player around, first thing that we're probably going to want to do is gather input from our player. Now, before we can actually gather input from our player, we need to know, you know, what keys actually on the keyboard are going to be used to move our player in certain directions. So what I'm going to do is go over to my components and tags folder, just going to do a right click, and we're going to go ahead and add a new C# class here. It's actually not going to be a class, it's going to be a struct, and we're going to call it player input keys. So basically we're just going to get to this spot right here. You know, if you are just using Unity and creating a new script through there, basically just whack everything out and then create something that looks a little bit like this. I'm going to actually change this namespace over. It's just using the folder name right now. We'll call this tmg.spaceshooter. So now you see that we do have this public struct called player input keys. Now we are going to want to make this a data component. So what we're going to do is we're going to have this implement the iComponent data. You'll see that here it automatically imports the Unity.entities namespace. Pretty much all the scripts that we're going to be creating in this video do require that namespace. So this is our first data component. Now this is very important because our data components, they need to be set up in a very specific way. You know, inside here, we can only have them contain data types that are of blittable types. So these are very simple types, typically like floats, integers, bools, things of that nature. Another one that we can actually use are enums, which is really nice because in this case, we are going to be using key codes from the Unity engine namespace here. This is just a basic enum to give us a little bit of an idea about, you know, which key is going to be assigned to the up, down, left, right, and the primary weapon key. So basically the way this is going to work is this is going to be a data component and this is going to be on a game controller entity. Now basically we're going to run a system on that game controller entity, which is going to allow us to check the actual input of the keyboard against these keys that we've assigned right here. So let's go ahead, we'll come back over to Unity, we'll go ahead and create a empty game object. This one's going to be called the game controller entity. We are going to have a game controller mono behavior later on, so we can just kind of differentiate the two. Again, we'll come over here, we'll we'll check mark the convert to entity box. We'll go ahead and add a component. Now let's see if we can search for that player input keys, and we're not getting any hits. So kind of what is going on here? So basically this isn't a mono behavior, so it's not going to show up in that list of components. And this iComponent data unfortunately doesn't do anything for us right off the bat. However, there is one thing that we can do. Above this struct, we're going to go ahead and add an attribute, and this is going to be the generate authoring component attribute. Now the generate authoring component attribute, basically what that's going to do is it's going to create a component that now we can add through the Unity editor. Right now, this is again the built-in generated one, and we are going to be doing our own custom ones a little bit later on. So if we see, we can go to add component, and now we can search for this player input keys. Then we can come over here and then we can set up our input keys as we want it to. So you see that I've just gone ahead and set up the inputs for a W, A, S, and D for the movement, and then a space bar for our primary weapon key. Okay, so next up, we're going to do something very similar. We're going to create another data component, which again does have the generate authoring component tag. This one is going to be our player move input. Now this is actually going to be the data component that we're going to be writing to. This is the component that will actually live on our player. And then when we have a system that actually, wants to move our player, we're going to check this value here and see what it is. And we'll be able to move our player based off of this. You notice that I'm using a float3 data type. This is part of the Unity.mathematics library. And this is sort of equivalent to a vector3. However, it is a little bit more efficient. There are kind of some optimizations that can be made with the burst compiler, so it makes it a whole lot faster than a vector3. Anyways, we'll come back over to Unity. We'll go over to our parent player ship. We'll go ahead and add a component for the player move input. Right now, you see that we can actually edit this value right in the inspector if we wanted to. However, we're just going to go ahead and leave this all as 000 for now, because we actually are going to be setting this at runtime anyways. Okay, so now we're going to go ahead and create our first system. So we'll come over here and we'll go ahead and add a new class or interface. This time we actually are going to do a class. This is going to be our get player input system. Okay, then a couple things that we need to do on this class here. So for one, this is actually going to be a public partial class. The reason that we make it a partial class is because the latest version of Unity ECS does take advantage of code generation, which basically allows us to write code that's more or less easy for us to understand. And then it actually generates code that's much more performant than what we can just kind of write on our own through C# here. And we do actually need to inherit from system base. Now system base is a special ECS thing. This basically denotes that this class right here is a system. You'll see that we do have a red line under here because we do actually need to implement this protected override void on update. Now I've kind of gone into detail on systems in some other videos, so I won't repeat that too much, but I definitely will link to the videos as normal. But of course, these systems are where we actually do the data transformations within our games. Now you may come across some older documentation that has like job component system or component system. You don't want to use those. Basically from here on out, you do want to use system base. And actually going forward, there will be another one that you can use, which is the iSystem interface. However, it's still a little bit kind of on the cutting edge right now, so I'm not going to be showcasing that in this video, but of course I will be showcasing that when it does become more of a standard thing in the future. But a system base has a life cycle similar to a mono behavior. There are basically equivalents of a start and an update and a destroy method, and so we can kind of hook into those events to create some logic and some things happening in our games. And so speaking of, we actually are going to start with the onStart running, but first we're just going to go ahead and create a simple little member variable here, which would be the player input keys, which is of type player input keys, which is of course this player input keys right here. Again, we do want to basically, look for that game controller entity. We'll grab that component off of it, and then we can basically use that to compare against the input that's happening on the keyboard to determine whether we need to move our player up, down, left, or right. So in order to actually grab a reference to that, it's actually super simple to do. We're going to go ahead and do a protected override for the onStart running function here. Again, this is basically going to be called when the script starts up at the beginning of running our application. And we can just go ahead and set our player input keys equal to a get singleton of type player input keys. Now we can do this because we know that there's only one entity in our application that has this player input keys. Now we do need to make sure that there is one and only one of these, because if we have 0 or 2 or more, we're going to get some errors within the console. So, this is something that's kind of easy to do, but you just kind of need to be aware that there may be some potential issues if you do have, 0 or multiple of these entities in your game. However, now that we actually have a reference to that, we're going to go ahead and actually get our player input. So what I'm going to do is just create a method called get player input, and I'm just going to assign this to a new player input variable here. And you'll see that my get player move input is just returning a player move input here. So first thing I'm going to do is just create a couple local float variables for the horizontal and vertical movement, and then just based off of the input.get key, again, this is just the regular Unity engine.input.get key, basically just checking our player inputs.right key, player inputs.left key, and so on, and just basically assigning positive or negative values of 1 to our horizontal and vertical movement. So basically, say if we were holding down the right key, then our horizontal movement is going to be a value of 1. If we're holding down the left key, instead we're going to set that to a value of -1. Next up, we're going to create another variable. This one's a float3 for player movement, and you'll see that we're setting the X, Y, and Z based off of the horizontal movement, 0 or the Y direction, because we don't want it moving up or down. We're just moving it in the X and Z direction, and then the Z is for our vertical movement, because again, this is basically a 2D game. After that, I'm just going to go ahead and do a quick check to see if the magnitude of our player movement is greater than 1. Basically, when we want to do this, we're just going to go ahead and normalize that player movement back to a value of 1. Basically, this is going to happen, say, if we're holding the up and right keys at the same time, then basically the length of that is going to be greater than 1, and we don't want our player to move faster when it's moving in the diagonal direction, so we're just going to go ahead and normalize that to a value of 1. Now you notice that I am using the unity.mathematics library because we do have this lowercase m math. I am using the length squared because it is a little bit more efficient than the regular length. And again, we can just compare this with a value of 1 because 1 times 1 is 1, so that's super nice and easy for us to do. And then you'll see that the math library also has a normalize, so we can just pass in our player movement and set it back to player movement just like that. So super easy. And then really the last thing that we need to do is just create a new player move input, and we'll just set the value to that player movement. So now we have our player move input, and we just go ahead and assign that back to our new player input. Now, kind of similar to how we did a get singleton earlier, we can actually do a set singleton, and in here we can just pass in the new player input. Now again, we can do this because we know that there is one and only one player within our game. So this basically means it's going to set the player input based off of the keys that we're pressing. So now we can go ahead and enter play mode, and by default our systems are going to be created automatically for us. We can verify that by going over to our systems window, and we just do a quick search for our get player input system, and you'll see that it is running here, and you'll notice that it does have an entity count 2. If we do look over in our inspector, we can get a little bit of information about what's going on. So you see that we have 2 queries. There's one for our player input keys, again that's our game controller entity, and the other one is our player move input, which is just for our player. So if that's all looking good, we can actually come over to our dots hierarchy, and we do see that our player ship is here, and if we look over, we'll see that our player move input, this is currently set to a value of 0, 0, 0. Now, when I basically press any of these keys in real time, so for example, if I press the W key, you'll see that the Z value changes to 1. That's because we're basically going forward. Again, that's the vertical direction. If I let go, you'll see it goes back to 0. If I press the S key, that now is a value of -1. And then same thing over in the X. When I press the left and right keys, you'll see that it flips between -1 and 1. And when I let go, it's down to 0. Now, if I do hold down, say, the up and the right key, you'll see that now it kind of updates to be basically that normalized value there. Now, once again, that's just us getting the input for our player movement. Now we actually need to move our player. So first thing that we're going to do is create a new data component. Again, same thing. We're going to do a public struct. This one's going to be called move speed, which implements the iComponent data interface. And we just have a public float called value. Again, we are using this value pretty frequently here. Basically, kind of the common convention is if there's only one variable, we can just call this value, and it turns out to kind of write out really nicely when we end up doing something like a move speed.value. It just kind of makes sense rather than doing something like move speed.speed. It seems like a little bit redundant. And we do also have the generate authoring component, so that means that we can come over to Unity, we'll go over to our player ship, and we'll go ahead and add a move speed component on here. Now this one we can set in the editor. We'll just go ahead and set this to a value of 50 for now. Okay, so again, we're going to go ahead and create a new system. We're going to make sure it is a public partial class. This one's going to be our move player ship system, which inherits from system base. And again, we do need that protected override void for the on update. Now this system's going to be a little bit different from the last one. This one's going to be probably more similar to the typical systems that you're going to be writing in Unity ECS. We're actually going to be creating a job and kind of scheduling that. So basically the way this works is we're going to be creating a job outside of this system, and then inside the system we're actually going to be scheduling that job. So we're just going to actually go ahead and go outside this class, and we're going to make what is known as an iJob entity. Now this iJob entity is a really nice feature. I made a whole video kind of going into detail about what they are and all that, but basically it allows us to create a job where we can actually do some transformations on the data within our game. But basically the way that we do this is we're going to make a public partial struct, and this is going to be called the move player ship job, which implements the iJob entity interface. Now you'll notice that it doesn't yell at us for, any required members or anything like that. However, there is one that we are going to need, which is the most important one, which is just going to be a private void called execute. Now the parameters of the execute function are very important because by default, whatever we put into these parameters are going to be what our entity query uses to find entities in our game to actually run operations on. So to just put this in a very simple way, any component type that we put inside the parameters of this execute function, it's going to look for any entity within our game that has those specific sets of components. Any entity that it finds that has all those components, it's actually going to go ahead and run some operations that we are actually defining within this execute method here. Now there's a very specific way that we need to go about adding in the specific components that we want, and we need to consider whether we want to read from the data or read as well as write to the data. So again, this kind of goes back to that spreadsheet that we worked on at the beginning of the video, where we need to know, which components have, read and write access and when they need it. So here we're going to be moving around our player ship. So we're going to be modifying its translation component. So that basically means that we need read and write access to it. So the way we do that is we'll do a ref keyword. The ref denotes that this is going to be read and write access to the translation component here, and we can just call this translation. Now we will also need read-only access to our player input. The way that we get read-only access is just by using the in keyword, and then we can say player move input, and again we can just call this player move inputs. And then finally we do also just need to read in from the move speed, which we can just call move speed. Okay, so inside the execute function, first we're going to calculate how much our player needs to move compared to where it is, and then we're going to modify our translation component based off of that. So we can say a var current movement equals, we'll do our player move input dot value. Again, that's going to be that float 3, so we kind of know which direction that our player is going to move in. And now we can multiply that by our move speed dot value. Again, our move speed is basically going to determine how fast we move from point A to point B. And then lastly, we do want to multiply this by delta time. However, we can't actually do a time dot delta time as you would expect. We do need to actually pass this in. So this is going to be a member variable of this iJob entity job. So we can make a public float called delta time. And then so again, we can just go ahead and multiply this by our delta time. Now, when we actually go to schedule this job, we need to make sure that we actually do set this delta time value here. Anyways, next thing that we're going to need to do is actually go ahead and modify our translation. So we just do translation dot value, and then we say plus equals current movement. And so that's all that we need to do to move our translation. And basically what we're doing with this iJob entity is any data type that we pass in as a parameter for this execute method, it's going to create an entity query off that, and it's going to look for any entity that matches that particular set of components. Now in this case, we just have one single entity that's going to match these sets of components, but later on we're going to be running these iJob entities where many entities could be returned by this entity query. Now one important thing to note is the actual body of the execute method where we're doing our data transformations. All that is going to run just on one single entity. So if we say return out of this function, what it's going to do is it's actually just going to move on to the next entity in the entity query that we've done. And again, this is very efficient because the computer is basically doing the same operations over and over and over again before it moves on to an operation of a different type. Now, one thing that we are going to do to this move player ship job is add the burst compile attribute. This is basically going to mean that our execute function that is actually the job that's going to be running is going to be compiled using the burst compiler. So down here in Writer, you'll see that we do have this little thing beside it that says it's burst compiled code. Now, basically the burst compiler does a whole bunch of mathematical optimizations so we can get the best performance out of our games. So we do always want to use the burst compiler when we are able to. However, this isn't actually going to do anything on its own. We're going to again be scheduling that job from our system base in the on update here. So we'll go ahead and we'll create a new move player ship job, and then we can go ahead and use the open and close curly braces to actually do kind of our struct initialization here. So here's where we can actually set delta time equal to our time.delta time. Now be aware that this time.delta time is different from the Unity engine time.delta time that you may be used to. This is basically one that is part of the ECS. You'll see if you hover over the time, this is actually a type of time data, which is part of the component system base class. So that's basically what we want to be using to get our delta time. You can kind of tell the difference because it uses a capital D for delta time rather than a lowercase d for delta time. And then after that, we're actually going to schedule the job. So after the curly braces, we're just going to go ahead and do a dot schedule, and actually we're going to do a schedule parallel. So the schedule parallel, this basically means that this operation can run parallel to other operations as long as the dependencies line up properly. Now, if you are familiar with Unity's job system, you know that when you schedule jobs, you can often get a dependency from them. And that basically allows us to say, hey, if this code depends on this code, we need to make sure that this job is completed before this job runs. Now, one of the nice things about Unity ECS is a lot of that stuff is taken care of for you. There's actually a dependency property. You can get to it by doing a capital D dependency. And this is basically known as the auto dependency property. So basically any jobs that we're scheduling in here, it knows which components have, read and write access in this system. So it knows that certain jobs that may also be accessing that data may or may not need to be completed before this job runs. And so if we wanted, I'm just going to demonstrate this here to you real quick. We can actually do our dependency equals the new player move ship job. And then actually we can go ahead and pass in the dependency here. Now, of course, we can do, any manual job dependency that we want, but basically if we don't have anything, this is basically what it's doing. It takes in our auto dependency property here, and then it just reassigns that to the dependency here. And if that doesn't make any sense right now, you do not need to worry about that right now. Most of the times the auto dependency is probably going to be good enough for simple operations. Now, before we jump back over to Unity, I do just want to point out one thing. These systems in our game, they run in a very specific order. And now this is very important because in certain situations, maybe certain data is going to be modified before or after we're trying to access that. So we really need to have an understanding about, when things are happening in the proper way. So a couple things to note here is, we are going to be reading from our player move input. So we want this system to basically be running after we have already gotten our player move input. However, we're also writing to this translation component, and there are some operations which happen in a built-in transform system group. So we can add these attributes on to ensure that our system updates after the type of get player input system and before our transform system group. Now, the transform system group, basically this is a group of a number of different systems, and if you're curious, you can actually view those inside the system window in Unity. Okay, so now we'll come back over to Unity. We will enter play mode, and now when you see that we press the W, A, S, and D keys, our player ship moves around on the screen as exactly as we would want it to. So that is very exciting stuff. Now, you may have noticed that we actually do have a new warning in our console. And if you read it, you'll see that it is pointing towards our move player ship system. And we kind of get this whole warning for this CS0282. And then you can kind of read about kind of what's going on. Basically, the reason that this is happening is there's kind of some disconnect about how the iJob entity is set up and how that works with the Roslyn code generation package that Unity is using. And you see here in our iJob entity, you see that we're doing a public partial struct. Again, we need to do that because this does take advantage of code generation. However, there are some issues that actually need to be resolved in the Roslyn source generation side rather than Unity's DOTS side. However, I do know that there are some people from the DOTS team working on on this issue, you know, trying to get some things resolved in the Roslyn source generation repository so we don't get that warning anymore. And actually it's throwing this error because we have a public field here. You'll see that on some other iJob entities where we don't have any fields like this, we actually will not get that same warning. However, we are going to be using this iJob entity quite a bit, and we don't want our console to be filled up with all these warnings. So there is something kind of hacky that we can do. We can just do a simple pragma warning disable CS0282. Now, if we come back over to Unity and let that compile, you see that that error has now been suppressed in the console. So again, anytime that we have iJob entities where we have any fields, we're going to need to put that on there just to kind of suppress the warning. Again, hopefully that will get resolved soon, but that's just kind of a little workaround that we need to do for now. Okay, so we have our player moving around. Now the next thing that we want to do is have it rotate. And in this game, I've chosen to have our player basically rotate, and it's always going to be looking at the mouse. However, it's going to have, you know, a little bit of a rotation speed, so it's not exactly always one-to-one with the mouse, but it is going to be moving pretty quickly. So first thing that we're going to do is create another data component, and this one is going to basically store the world mouse position. So basically we know the world coordinates of our mouse at any given time, and then we can rotate our player towards the mouse. See that I do also have the generate authoring component, so that means we can come back to our player ship and then go ahead and add the world mouse position. Again, we don't need to do anything with the X, Y, and Z coordinates in here. Next, we're actually going to need to get and set our world mouse position. So again, we'll go back to our get player input system, and we're going to do something very similar that we did to the get player move input. So firstly, we're just going to go ahead and add a new member variable for our main camera, and we can just set that equal to camera.main when we start running our game. And then we'll go ahead and add a new method here for the get world mouse position. And of course, it's just going to return a world mouse position, kind of similar to what we did with the move input. You see that in here, we're just going to go ahead and get the mouse position by actually looking at the input.mouseposition.x and y, and then passing in our main camera.transform.position.y. And then now we can actually convert that to a world mouse position just by using the standard screen to world point off of our main camera, passing in that mouse position that we have here. And then all we need to do is just go ahead and return the world mouse position, and we'll just set the value of that equal to that world mouse position that we've created. You know, if you're familiar with Unity and getting a world mouse position, this should look, you know, more or less familiar. One thing that I should point out is this world mouse position, this is of type vector3, even though our world mouse position, this value is a float 3. So just to note, that conversion basically from a vector3 to a float 3 happens automatically, so we can do things like that. And then in our update method, you know, right after we're getting our player input, we can just go ahead and do something similar where we get our world mouse position. We'll set this equal to a local variable, and we'll just call set singleton. So again, that's just going to set the data right on our character. And then so here we can go ahead and enter play mode. You'll see that the world mouse position, as I'm moving my mouse around, you'll see that it is changing around to reflect the current mouse position. So if I'm right on the player right here, you'll see that it's roughly going to be at 0, 0, 0. As I move around here and there, it's just going to be, you know, updating to whatever value that it is at. Okay, so now we're going to go ahead and actually rotate our player towards our mouse. So one thing that we are going to need is a rotation speed component. You see that it's basically just a standard I component data where we have a public float called value, and again, a generate authoring component. So I'm sure you know what we're going to do is we're just going to go over to our player ship, and then we're going to go ahead and add the rotation speed on here. And for the player, we'll set this to a value of 500. And then before we go ahead and actually proceed with creating our system, I'm going to create this math utilities class here. You'll see it's just a public static class. And I do have a few static functions on here. One that's get rotation to point, which returns a quaternion, takes in our current position as well as our target position, and basically just returns a rotation from that. Next up, our set rotation towards, which does call this angle function down here. These are basically a couple ones that I've just taken directly from the existing Unity methods in the regular quaternion library. Again, not really, you know, inside the scope of this video to go into detail on these, but basically these are kind of the functions that we're going to need to allow us to, you know, do the proper math operations to rotate our ship towards the mouse position. Okay, so I'm actually just going to go back to the move player ship system, and I'm just going to go ahead and do everything all also in this system here. So what I'm going to go ahead and do is actually just add a couple more parameters to this. Now, one thing that's nice about these execute functions as compared to maybe some other things that you might have seen with Unity ECS is it actually doesn't matter the order of the different components that we have. So for example, here, we're going to need read and write access to the rotation. So we can actually just do a ref to the rotation, of course, just call it rotation. We're also going to need to get read-only access to the world mouse position. Of course, it's just world mouse position. And then just finally reading from the rotation speed here. So that is going to allow us to use these components inside the execute function here. So what we're going to do is actually get a rotation target from our math utilities dot get rotation to point. And then here we want our current position, which is our translation dot value. One of the reasons that I put this inside the same as the actual move job is so we can get the most up-to-date translation here. And then our target position, of course, is going to be our world mouse position. Again, we need to make sure we do a dot value on there. And then here we can actually just set our rotation dot value. I've basically done this through an extension method in the math utilities class where we can just say set rotation towards, and then it basically wants the rotation that we're setting to, which of course is going to be our rotation target. And then for our max degrees delta, it's going to be our rotation speed dot value multiplied by delta time. Now there is one potential issue with this where basically if the translation dot value and the world mouse position dot value are exactly the same, so in that case we can just do a quick distance check to see if the distance between the translation and the world mouse position is less than an epsilon value, which we can go ahead and set up here. We'll just go ahead and set this epsilon equal to 0.01 f. Okay, so now we can come back to play mode and you'll see that now our player is following our mouse around. So even however we move, our player is always going to be pointed at this mouse here. And if we just go straight through it, you'll see that basically it's just going to turn right around because it's always going to be pointing right at that mouse, which is exactly what we want. So this is basically going to allow us to move around and shoot in whichever direction we do want to. Now, one thing you may have noticed as we keep going along is, every time we've created a new data component, it has this generate authoring component, and we just keep putting all these on our player ship. And this is kind of like starting to take up a little bit of room, not too bad, but there are going to be a number of other components that we are going to need to add. So this can kind of start, just having a bunch of different components in here. Another thing to keep in mind is that we are going to have, many of these same components on our enemy ship as well. So actually what we're going to do is a little bit better of an approach. Rather than just using the generated authoring components, we're going to create our own custom authoring components, which is going to give us exactly the components that we need for the entities in our game. So here you'll see that we do have these, 4 data components. We're going to consolidate this into 2 different authoring components. There's going to be one, which is just a kind of generic ship authoring component, which is going to have the move speed and rotation speed. And then we're going to be adding some things later on throughout the video. And then that one is also going to be on the enemy ship. And then the second authoring component is the ones that are specific to the player, where we have the player move input as well as the world mouse position. Now, one of the nice things about the player one is that we no longer are going to have these variables exposed in our editor. So it's not going to confuse anyone else who's, on our project. It's basically just going to look like an empty component with nothing on it. But when we actually run our game, it's going to add all the proper input components to our entity that we need. So we're going to start with the move speed. You don't actually have to do this, but just kind of for clarity's sake, I'm just going to go ahead and remove the generate authoring component off of the move speed as well as off of the rotation speed here. So now I'm going to go to the authoring and mono folder. I'm going to go ahead and add a new Unity script, and we're going to do a new mono behavior. Now it's important that we do a mono behavior so we can actually add this as a component in the Unity editor. So I'm going to call this one ship authoring. So we're going to go ahead and do that there. So here's kind of the initial part of our authoring component here. So after this, we're actually going to implement the iConvert game object to entity interface. See that we do have a red line here, and then we can just go ahead and implement the missing members. So you'll see that we do need to implement this public void convert, and it does take in a couple parameters. Now we are never actually going to call this convert method directly. This is something that Unity is going to do automatically. So let me kind of go through what all this stuff means. So entity, this is going to be the entity that we're going to be converting. So basically the way this is going to work is, if we have this script on a game object that will be converted to an entity, this entity value is going to refer to that basically output entity that we're going to be creating. And just kind of for clarity's sake, I like to actually go ahead and name this something so that, if I ever come back to the script, I know, what entity type it's supposed to be. be. So I've just called this the new ship entity here. Next up is our entity manager, and you'll see that it's called DST manager. Basically, the entity manager is a very important part of Unity ECS because using the entity manager, this is going to allow us to spawn entities, add components, remove components, set values on components. It's something that you should definitely be very familiar with if you want to be using Unity's ECS more. And then finally, we have the game object conversion system. We kind of have a reference to this game object conversion system. It's going to be used in a couple specific cases throughout this video. Basically, it's a reference to the actual system that's doing the game object conversion. So the first thing that we're going to do is expose fields for the move speed as well as rotation speed. You'll see that I've created these two serialized fields, which are private floats for the move and rotation speed. So what we're going to do is we're going to use our entity manager to add a move speed and rotation speed component to our new ship entity. The way we do that is we do our DST manager dot add component data. It's important that we do add component data versus add component. Add component is basically when we want to just add a component with the default values, which we will be using later on in a few cases. However, we're going to be doing add component data, and this is going to allow us to actually set the values on that data as we add it to the entity. Now, first it's going to take in an entity, and of course we do want to add this to our new ship entity. And then the next parameter is going to be the actual data component that we're going to be adding. So in this case, we'll do our move speed first. So we can do a new move speed. We'll go ahead and in here, we'll set the value equal to our move speed. And so again, basically what this is going to do is the entity manager is going to add a move speed data component to that new ship entity, and the value is going to be set to this move speed, which we do have exposed in the editor. And then again, we're going to do something very similar with the rotation speed. Well, we're just going to use the entity manager to add a component data of the rotation speed, again setting that value to our rotation speed. So we'll come back over to Unity, and on our player ship you see that we now have a couple errors because these scripts are now missing because we've removed that generate authoring component attribute. So we can just go ahead and remove the errored out scripts, and now we can actually just go ahead and add in the ship authoring component. You'll see that we just now have this nice clean way where we can easily set the move speed. Again, we're doing a value of 50 and rotation speed of 500. So now I'll do something very similar for the player. Again, we'll go to the player move input, go ahead and remove the generate authoring component. And there was also one on the world mouse position. We'll go ahead and remove those. And then here we'll just create our new player ship authoring component. This one's really easy. Again, I've just renamed this entity to our new player ship just so it's clear about what exactly that is. And then here I'm going to do the add component. Again, not an add component data. This time we're doing add components because for the player move input and world mouse position, it doesn't really matter that we're setting those during the conversion process because we're going to be setting those at runtime right away. So we can just go ahead and add those components, and as long as the player ship has those components, then we are good to go. So again, we will come back over to Unity. I'm going to go ahead and remove these two scripts that now have errors, and then we're going to go ahead and add the player ship authoring, and you'll see that there are literally no fields or anything for us to configure or get confused by. And again, we can just confirm that now we can enter play mode, and we'll go over to our dots hierarchy and our player ship, and then you'll see that we now have a move speed with a value of 50. We have our player move input, which is set to 000 because we're not moving, a rotation speed with a value of 500, and a world mouse position to set to wherever the world mouse position is. And then so again, we can kind of still move around and rotate as exactly as we want it to. However, this is a much easier to work with interface now that we have these custom authoring components, and we will be adding more things to both of these authoring components later on. So this is just kind of setting us up for success in the future. So it's always a good idea to kind of create these authoring components early and then add on to them as you go. Okay, so the player is pretty good to go for now. The next thing that we're going to do is spawn some enemies within our world so they can kind of chase around our player. So we're actually going to start just by going ahead and duplicating this player ship right here. So now we'll just go ahead and actually rename this to the enemy ship. And then of course we don't need our player ship authoring on here. We're going to create our own for the enemy ship later on. So we can just go ahead and remove that. And then we'll drag this over to the side and we can select our renderer here. I'll just change our mesh over to the enemy ship mesh. You'll see that it is quite a bit wider than our player. And then also I'm going to go ahead and change this to the enemy ship material. So now it's red and a little bit wider to differentiate the two ships from each other. So now rather than having our enemy ship just exist in the world as we had it before, I'm going to go ahead and create a prefab out of this. So we can just go ahead and drag the enemy ship over into our prefabs folder. Just go ahead and delete that out of our world here. But so basically we're going to be creating a spawn controller, which is going to be spawning these enemies at random positions throughout our world. So here we'll actually go ahead and create an empty game object. And this is going to be our enemy spawn controller. And we can just go ahead and set this to 000. And now in here, we're going to go ahead and create a bunch of child game objects. So this is going to be our spawn positions. And so I'm just going to put a little gizmo icon on there so we can easily see them in the scene. Now just basically duplicate these a bunch of times and spread them throughout your game world. Okay, so I have about 20 spawn points and that looks good to me. One thing that we do need to do is go back to our enemy spawn controller. We'll just go ahead and check mark the box for convert to entity because we want this to be converted to an entity so it exists kind of within our entity world, so it's easy for us to actually spawn prefabs to these different points and everything like that. Now, basically what we're going to do here is take advantage of something known as a blob asset. Now, a blob asset is basically a set of immutable data that we can basically, reference from any entity within our game. In this case, the only entity that's going to be referencing this data is the enemy spawn controller. What this blob data is, it's going to be basically an array, and it's going to have a list of float3 positions for all these different spawn points that we've set in our world. Now we just went ahead and did this because it's nice and easy for us to set all these translations within the editor here. What we're going to do is we're going to create another custom authoring component. And in this case, what we're going to do is we're going to look at all these spawn positions and we're going to populate all that data into a blob array. Again, this blob array is basically a store to hold immutable data. It basically means that's data that we can guarantee that's never going to change throughout the lifetime of our application, which allows Unity to do some nice optimizations. Blob assets are a pretty big topic and I have made a few videos on them, so definitely go check out kind of my introduction to blob assets if you want to learn about how you can kind of utilize these more. And I do have some more advanced videos if you do want to go a little bit more in depth with that. Okay, so I'm going to start off by creating this spawner authoring script. Again, it's going to be implementing the iConvert game object to entity interface. And we do have the public convert method on here. And I've just renamed the entity to the spawner entity. And actually, before we go ahead and create our blob asset, we're going to need to create some special data components for us to basically utilize here. So the first thing that we're going to do is make a public struct called spawn point. And this is just a public float3, which we'll call value. Now you'll notice that this is just a regular struct. We're not implementing the iComponent data interface or anything like that because this isn't going to be a component that's added to an entity. Again, this is basically just data that's going to be stored in this blob asset. Now you'll notice that this is just a representation of a single point. This is just a single float3 value. So in order to actually hold an array of these, we're going to need another public struct, which I've called spawn point array. And here we'll end up doing a public blob array of type spawn point. And we will also just call this value. So you see kind of what we have going on here. We have the, very base, spawn point, which is the actual position of a single spawn point. And then we have the spawn point array, which is a blob array of type spawn point. So now we'll go up into the convert method and we're actually going to start constructing this blob asset. So the first thing that we're going to do is just do kind of a regular Unity game object thing where we look at the transform. Again, this is still a mono behavior at this point. So we can do a transform.getComponents in children type of transform. So this is going to get all the transform components of all the child game objects. And we can just go ahead and store this in a spawn transforms array here. So again, this is just kind of regular Unity stuff at this point. This is basically just going to allow us to get the position of all those child spawn points that we've set. So now we can actually go ahead and create our blob asset. In order to create our blob asset, we need to create what is known as a blob builder. So first we're going to need to use the using keyword because this blob builder does need to be disposed when we're done with it. So the using keyword basically just kind of will do that automatically for us actually. And then we'll do a var called blob builder. We'll set this equal to a new blob builder here. And inside it does need us to pass in an allocator, and we're going to do an allocator.temp. Now there are a couple different, allocation levels that we'll be touching from time to time. The allocator.temp means, if we're allocating some bit of data, in this case, it's a blob builder, The temporary allocation means that it's going to be disposed within the frame that is allocated. The temp job one is a little bit more lenient because we can actually have the data allocated for up to 4 frames. And then there's also an allocator.persistent, which basically means that we can access that data as long as we need to. So now here's where things get a little bit more interesting. In order to use the blob builder, we need to use this actually construct root method here. And here's where we pass in basically the type, the data type that we're going to be storing in our blob asset. It's going to be our spawn point array. And so we can actually capture this result in just a local variable called spawn point array. Now, one thing that we do need to keep in mind, we do actually need to get a reference to this. So we'll use the ref keywords before we both define the spawn point array, as well as call this construct root method here. Next thing that we're going to do is actually create a blob array. And then we'll set this equal to blob builder.allocate. And then here we actually pass in the reference to the blob array. And then so we do a ref spawn point array.value. And then here we pass in the length. And the length is basically just going to be our spawn transforms.length. And apologize if I'm just kind of going a little bit quickly through this. I would recommend checking out the videos that I've done on blob assets if you want a little bit more information on what exactly are the technical details about what's going on here. But basically, once we have all that set up, now we can actually go ahead and populate the data. So we're going to go ahead and use a for loop here. So of course, we're just going to go from 0 up to spawn transforms.length. And then here's where we actually can populate data inside our blob array. So we'll do blob array at position I is equal to a new spawn point, and then here we can set the value equal to the spawn transforms at position I dot position. So basically what this is going to do is it's going to loop through our spawn transforms array and populate that data into this blob array here. So then the next step is going to be to create a blob asset reference so we can actually, access this data. I'll call this the spawn point reference. Set this equal to blob builder dot create blob asset reference. The type is going to be our spawn point array. And then finally, we are going to need to pass in another allocator, and this time we're going to be doing a persistent allocator because we want this data to persist throughout the whole entire lifetime of our application. Now what we need to do is we need to put this spawn point reference on our spawner entity so we can basically access it from a system. However, this spawn point reference is not an iComponent data, so we can't just directly add it. So we actually do have to create our own iComponent data. So below here, I'll just go ahead and create a public struct called spawn point reference, which is an iComponent data. And this time it does have the blob asset reference of type spawn point array, which conveniently is the type of variable that this is right here. So again, because this is a custom authoring component, we can just do a DST manager dot add component data. Again, we're going to be adding this to the spawner entity, and this will be a new spawn point reference. And in here for our value, we'll set this equal to the spawn point reference. So now I know that was probably kind of a lot. So basically we'll work backwards here. So we have this spawner entity, which now has this component called spawn point reference. If we look over at the spawn point reference, this has a blob asset reference to a spawn point array, which is what we just call value. Now this value is this spawn point array right here, which is a blob array of spawn points. Again, this is called value. And then we'll go back up to our actual base struct here, which is a public float 3 called value. So it can kind of get confusing to keep track of all this because basically everything is named value. So a lot of times what I do on these blob asset references is I make a couple little helper methods for me here. One of them that we're going to need is a public int called length. And so we can set this equal to value.value.value.length. And then so that's basically actually just going to go ahead and return the length of this array down here. And the other one I like to use are custom indexers. So basically what this allows us to do is just right on the spawn point reference, we can basically pass in an index to that as if we're just indexing an array. And it's going to go ahead and actually return the specific spawn point at that exact location in the array that we want. So the way that we do that is we do a public float 3. Again, we're doing a float 3 because we want to return the actual spawn point when we pass in an index to the array. And the way we do the custom indexers is you say this, and then you do the brackets, and you say int I, and then here we're just going to go ahead and just return the spawn point value. The reason that we're returning the spawn point value and not, actually setting it as well is because these blob assets are immutable structs, and so we're actually not allowed to modify them. So we basically say value.value.value at position I.value. So again, I know blob assets are something that are, very wordy and complex to create, but really they actually are quite simple. Again, it's basically just a store of data, and doing things like adding these little helper functions inside your blob asset references just makes them a whole lot easier to work with. Okay, so now we'll come back to Unity, and then we can just go ahead and add that spawner authoring component right on there. You see that we don't have any data parameters that we're passing in right now. And then now when we press the play button, you see that we can go over to our dots hierarchy. We do see the enemy spawn controller in here. And if we do look over inside the inspector, you'll see that we do have this spawn point reference. And then actually the only data that we can see right now is the serialized hash. There is actually a way that you can see the underlying data, but that is a little bit outside of the scope of this video. But basically all this serialized hash means is if we were to, put this same spawn point reference component on any other entity, we would see this same serialized hash because it is pointing to, the exact same location in memory where all that data is being held. Okay, so I've created 3 new data components that we're going to add to our spawner entity. So basically the way this is going to work is we have this spawn timer, which has this value here, and this is going to count down to 0. Once it hits 0, we're going to actually spawn an enemy, and then it's going to reset that to the interval. So that's why we have the interval, so we can have a number to reset it to. The enemy ship prefab is going to be a public entity value. The entity is a blittable data type, so we can create an iComponent data off of this. And then finally, we do just have an entity random, and this just allows us to add a little bit of randomness to our game, so we can kind of, spawn at a random position of one of these spawn points. And I should point out this random is the Unity.mathematics random as opposed to the Unity engine random or even the system random. So this is, we're going to make sure that we're using the Unity.mathematics random library because this is fully compatible with the entity component system. Okay, so once we have the data components created, the next thing that we can do is we can add them to the authoring component in order to add them to the entity. So the first one we'll add is the timer. Now it will be nice for us to just go ahead and set the interval that we want just right through the Unity editor. So of course we can just go ahead and create a serialized field for a float, and we can just call this the spawn interval. Now down inside the convert method, after we go ahead and add the spawn point reference, we'll just go ahead and do the DST manager.add component data. Again, we're going to add this to the spawner entity. We're going to be doing a new spawn timer. For value, we can just set that to 0 so it spawns the first frame, and then we'll set interval equal to our spawn interval. Next up will be the enemy ship prefab. Now there's actually a couple of different things that we need to do for this. So the first thing that we need to do, of course, is just give ourselves a field, and we can't actually have an entity serialized field. So we actually kind of have to do this in a little bit of an interesting way. So we have to do a private game object, and we can call this the enemy ship prefab. Now, because this is a prefab, we do need to do one extra step here, and this comes in the form of another interface that we need to add to this, which is the iDeclare referenced prefabs. So you see that if we go ahead and add that method on there, it is this public void declare reference prefabs. And we do have this list of game objects called reference prefabs, which is being passed in here. Now, basically what we're going to need to do here is basically just add the game object prefab to our list of reference prefabs. So we'll just do a reference prefabs.add, passing in the enemy ship prefab there. So that's really all that we need to do. And now we can actually access that inside our convert method. So after we go ahead and add this spawn timer here, we'll go ahead and just create a local variable here called enemy ship entity prefab. And we'll set this equal to our conversion system.get primary entity. And inside here, we'll pass in our enemy ship prefab. So again, this conversion system is one of the parameters of this convert method here. And then from here, there is a get primary entity, and we can just pass in this enemy ship prefab. And basically that means when this game object goes through its own conversion process, we're going to get the entity from it through this conversion system. random, and then we can actually just go ahead and assign this here. Now I should mention that this extra step that we have to do for declaring referenced prefabs, we only need to do this for, say, prefabs that we're going to spawn. If it's just like a regular entity reference that we're just kind of like pointing to, and we don't need to, you know, spawn new ones of these, we don't actually need to do this. And we will be doing this later in this video. Basically, the purpose for this is it just says, you know, hey, this enemy ship, this needs to be a prefab. You know, we need to make sure that it's all set up with the proper prefab components and everything like that. So now let's go ahead and actually add this prefab reference to our spawner entity. So of course, we'll do a DST manager .add component data to the spawner entity, and this will be a new enemy ship prefab, and our value is going to be the enemy ship entity prefab. So again, we need to get the converted entity kind of from our original game object, and we have to have it as a game object if we want a serialized field on this mono behavior like that. Finally, the last one that we're going to want to add is the random. Again, we're going to be using this to, you know, randomly spawn this at one of the spawn points in our world. And so in order to set this, we're going to need a random seed, which does need to be a uint, so unsigned integer. And I typically just like to do a system dot datetime dot now dot milliseconds, and then that basically just kind of returns a random number that we can pass into our random as a random seed here. So go ahead and say DST manager dot add component data, again adding to the spawner entity, can be a new entity random, and then for our value what we're going to do is we're going to do a random dot create from index. Again, we're going to make sure that this is using the unity.mathematics random, and then in here we can pass in our random seed just like that. All right, so we'll come back over to Unity. We'll go to our enemy spawn controller. Let's set this as a spawn interval of 3 seconds. So it's going to spawn an enemy every 3 seconds. And then here we'll just go ahead and drag in this enemy ship prefab right on there. So now we can go ahead and hit play to enter play mode. We'll go over to our dots hierarchy, click on the enemy spawn controller. And you'll see that we do have these extra components on here. So we have this spawn timer. Again, the value is just set to 0 and the interval is 3. Right now we don't have a system to actually count it down or anything like that. Then we do have the entity random, and you can see that the random state is this number right here. And again, if we just exit play mode and enter back in, we should get another random number right in there, because again, we're just randomizing it based off of the milliseconds of our system clock. And then finally, we do also have the enemy ship prefab. So again, we can just kind of click on this right here, and it actually will bring us over to the actual enemy ship prefab. You'll see that again, we kind of have the move speed, rotation, and things like that. You notice that this does have the prefab tag right here. If you do look over in the dots hierarchy, you'll see that this is highlighted blue, and it does have this kind of little hexagon filled in as blue as well to denote that it is a prefab entity. Okay, so next up, we're going to actually create our system to spawn entities. Basically, the way that this is going to work, we're going to create another iJob entity batch, and we're just going to go ahead and decrement that timer until it reaches 0. Once it does, we're going to go ahead and spawn an enemy at a random position, and then just go ahead and reset that timer. So outside of our system base, I'm just going to go ahead and create a new public partial struct, and this is going to be the spawn enemies job, which of course is just going to implement the iJob entity like that. And we'll go ahead and create our private void execute. Okay, so here, of course, because we are going to be reading from our timer as well as writing back to it so we can decrement it, we're going to go ahead and do the ref keyword on the spawn timer. Of course, call that spawn timer. We're also going to need read and write access to our entity random. The reason that we need to do this is because every time we actually get a random value, we need to write back to the random to give it a new state value. I do have a pretty in-depth video about using random in Unity ECS if you do want to learn a little bit more about that. Next, we're going to need to read in from our spawn point references. Let's go ahead and call that spawn points. And then finally, we do need to have read-only access to our enemy ship prefab here. So the first thing that we're going to do is do a spawn timer.value, and of course we'll just go ahead and decrement this by delta time. So we'll do a public float delta time out here, and then that allows us to access that in there. So now we're just going to do a quick check to see if the spawn timer.value is greater than 0. If it is, we'll just go ahead and return out of here. Now, actually, the interesting thing here is if we say return, this basically just moves on to the next entity in the query. So if we did have, say, multiple multiple of these spawn controllers, and they're all falling under this entity query. This return basically means that it's only operating on that one particular entity. So then we return out of it and we'll go to the next entity in the query. However, in this case, there's only one spawn controller. So the return here is also basically just going to, not schedule any more of these jobs. However, now this means that if the spawn timer is less than or equal to 0, that means that we know that we can spawn a new entity here. So we'll go ahead and say spawn timer.value. We'll set this equal to the spawn timer.interval just to reset that timer for the next time that we need to access it. And here we'll go ahead and create a new enemy ship. Now, there are a couple ways that we can actually go ahead and spawn entities within our game. One of them that I mentioned kind of earlier is by using the entity manager. So if we have access to the entity manager, then we can easily spawn entities right in our world. However, there is a problem with that because that creates what is known as a sync point. Now, sync points are in general not that good in Unity's entity component system, because basically what a sync point means is that any scheduled jobs, it's going to force those all to completion. So, maybe they had kind of the whole frame to go ahead and actually do their work. However, if we say like right in the middle of the frame, say, hey, I want to spawn an entity right now, it's actually going to go ahead and say, any of these previously scheduled jobs, those are all going to have to get automatically completed. We need to wait for those to complete. Then we can actually go ahead and spawn our entity. Now, this isn't really that bad if we're just spawning, like one entity at a time. However, if we have, a bunch of these sync points like littered throughout our application, we can really start running into some performance bottlenecks. So really the best way to handle this type of scenario where we want to say spawn things or, do other things that are known as structural changes, such as, adding or removing components, we actually can queue up all these operations in an entity command buffer rather than using the entity manager. Now, again, I do have a video going pretty extensively into, what entity command buffers are and how to use them properly. Again, the gist is we can queue up these operations that do require a sync point, and then Unity already has a number of sync points baked into the player loop. So we can basically use one of those existing sync points to go ahead and do things like spawning new entities or adding and removing components. And real quickly, I'll just mention, if you're curious about, why these sync points occur, basically the reason is anytime that we want to spawn an entity in the world or again add or remove some components, these are all known as structural changes. And in these structural changes, it's physically moving around data inside of memory, and we need to make sure that there's no jobs that are running in the background that are trying to look for some bit of memory right here when maybe if we did a structural change, it could kind of just pull the rug out from under that, and then all of a sudden the job is looking at some garbage data. So again, just to sum it up, we're going to be using an entity command buffer to queue up these operations and then perform them later on in the frame. So we do need to create this entity command buffer outside of the iJob entity. So we'll make a public entity command buffer and we'll just call it ECB. So now for our new enemy ship, what we can do is do an ECB.instantiate. And then inside here, we can go ahead and pass in the enemy ship prefab.value. So that's actually going to go ahead and instantiate a new instance of that enemy ship prefab. And so I can actually just demonstrate to you what's kind of going on real quick. Don't forget that we'll just go ahead and put the burst compile attribute as well as the warning disable on this iJob entity here. So now we'll just go ahead and schedule this. We'll do a new spawn enemies job inside here for our delta time. We can do a time.delta time. And then next we'll need to set our entity command buffer. Now, in order to get the entity command buffer, again, we're going to hook into one of Unity's built-in systems. In this case, it's going to be the begin initialization entity command buffer system. Now, there are a couple of reasons that I've selected this. I've kind of talked about this in some other videos that I can link off to. What's going to happen is this is going to queue up this operation until essentially the beginning of the next frame. So actually, it's basically going to be a 1 frame delay from when we, record the operation to say, hey, I want to instantiate this new enemy ship into the world, and then it actually spawning into the world. So we are going to need a reference to this begin initialization entity command buffer system, which I've just called ECB system. And then in the on start running, we can actually just go ahead and set the ECB system. The way we do this is by doing a world.getExisting system, and then the type is of course going to be the begin initialization entity command buffer system. So basically this goes to our existing world that we have. It finds this existing system, which is the begin initialization entity command buffer system. Now from there, we can actually create a command buffer. So down here, when we're scheduling our job, we'll go ahead and go to our ECB system.create command buffer. And then for this spawn enemies job, I'm actually just going to go ahead and run this on the main thread. I'm not even going to schedule it. That's another option that we can do, is just go ahead and say run. That's going to run on the main thread. So now we will come back over to Unity, enter play mode, and you'll see that our enemy has now spawned into the world. And if you'll remember, when I initially created that entity, we kind of moved it over to the side a little bit, and you'll see that that's basically where it spawned. So it just spawned kind of at its default value right now. And you'll see that actually, because our interval keeps going, if we look over in the dots hierarchy, we do have a bunch of these enemy ships here. Okay, so now the next step is to make this a little bit more interesting by actually spawning these enemies at our random spawn points. So basically what we're going to go ahead and do is just create a local float 3 called spawn point. And we also do have this number of tries set to 0, and this is just kind of a fail-safe just in case we don't find a spawn point in a particular amount of time. Basically what we're going to do here is we're actually going to use a do while loop, and the purpose of this is basically just so we can kind of locate one of these random points, and then we're just going to do a quick check to see if it is basically within the bounds of our camera. Now ideally we would like to find a spawn point that is outside the bounds of our camera. However, if that is not the case, then we'll just go ahead and spawn it at whichever one that was on once that max tries value has reached. But it would be extremely rare if it actually did spawn on the screen. So anyhow, basically I'm not going to go through all of this, but I kind of just want to show you the main points about using random. So first we're going to go ahead and get a random index. And so we can use our entity random, which is called random, and we can do a dot value to actually get the random component on there, and we can call a next int. Now the next int, basically this is just going to return a random int between 0 and the max value that we pass into here, which in this case is spawn points.length. Again, if you'll remember, this spawn points, this is the spawn point reference, which is this blob asset reference. And this is why I put this length on here, just so we can easily just go and get our spawn points.length. And we don't need to do all this long chain of value.value.value.value. So once we have that random index, we can just get our spawn point by doing our spawn point at random index. And again, this is the exact same thing. This is the reason that we use that custom indexer right here, is just so we can actually easily return that spawn point without doing that whole value chain. So anyways, we'll just kind of loop through that until we find a valid position that is outside the bounds of our camera. Once we do have that, we're just going to go ahead and do an ECB.set component, but we can still use our existing entity command buffer to set the component data as well. So again, we're going to be setting this on the new enemy ship, and we're just going to go ahead and set our translation equal to that new spawn point that we've located. And so you see that in order to kind of support this operation, I've had to add a couple variables here. I've just gone ahead and set these in here, and you can see that this is where I originally calculate them in the on start running, and here's what I'm doing in the on update. All right, so now if we press play, you'll see that now we do have these different enemy ships spawning at these different spawn points throughout our world. So you can kind of see them popping up. We got 2 over here. There's a third one over here. And they're just going to keep spawning out at all these different spawn points here. And again, we've done this so they're outside the view of the camera, so we're not actually going to see any of these in the game view, but you can see that they're spawning at these different spawn points throughout our world that we've set up. Okay, so now that we have our enemy ships spawning throughout our world, let's go ahead and make this a little bit more interesting and have these enemy ships start chasing down our player. So we're going to start off with a couple new data components. I have an enemy ship movement properties. This is just going to kind of give us a little bit more control about how our enemy ship moves throughout the world. If you'll remember, the enemy ship is still going to have the regular move speed just from the base ship authoring component. So it is going to be able to move forward at a constant speed. However, let's make it just a little bit more interesting and add a lateral amplitude and frequency so we can just kind of have the ship kind of move side to side as it's moving towards our player. Also, I'm going to have this minimum distance from target squared. That's basically just so that the ship doesn't get too close to the player where it starts like overlapping it. We just want to have a little bit of distance between the ship and our player at all times. Next up is just a simple one called time in world, which is a public float called value. And this is just going to increment for as long as this ship is in the world. Basically, the reason that we have this is because we're going to be using a little bit of a sine wave to make it go side to side. And then we just need to keep track of how long it's been in the world, so we can basically, calculate that sine wave. And then finally, I have an empty data component, and this is known as a tag data component. Now, a tag data component is a really handy concept, and we're going to be using these a few times throughout the rest of this video. Basically, it's really cool because it's a zero cost data component. So of course, there's no memory associated with it, but the thing that it allows us to do, it allows us to structure our entity queries. So we can say, look for anything that has this set target tag, and then we can run a specific system on that. So we'll be doing that a little bit later. So then I've just gone ahead and created an enemy ship authoring script. Of course, we have just a couple of serialized fields for, all those movement properties, the lateral amplitude and frequency, as well as the minimum distance from target. Now, this is one thing that I should point out that's really cool about these custom authoring components. So we can basically author the minimum distance from target right from the Unity editor, just as like an easy value for us to edit. We can say, oh, we want it to be, say, 20 units away from the target. However, we can make it, a little bit more performant by actually storing the minimum distance from target squared. And you'll see that in the authoring, I'm just doing a multiplication of this value times itself. And the benefit of that is actually under the hood, we can do our distance check using the distance squared, which is going to be more performant than doing a regular distance check because we don't have to do that extra square root operation at the end. So it is just kind of a little bit of an efficiency gain, and we do kind of get the best of both worlds where we can basically, author this as a, human understandable value from right inside the Unity editor. And then when we actually go to calculate it, we can use the more performant data type because during this conversion process, we're just doing this simple multiplication method here. And then of course, I'll just go ahead and add the time in world and set target tag. No need to set any values on those. And then real quickly, we'll come over to Unity and add the enemy ship authoring to our enemy ship prefab. We'll add in a lateral amplitude of 50, a lateral frequency of 10, and a minimum distance from target of 20. Okay, and then here we are over in the move enemy ship system, and then I've just gone ahead and created the basics of this move enemy job in here. So again, it's going to be pretty standard iJob entity where we're just going to go ahead and schedule it from the system and then run it down here. Now, let me just talk a little bit about the theory of how we're going to get this move job to work. So basically, we're going to have the player as basically a target entity, and the enemies are always just going to be following the player around. We're just going to do a very simple kind of AI situation. Now, in order for our enemy ships to follow our player ship around, we're going to need a way to find the exact position at any given point in time of our player ship. Now, this does bring up a bit of a challenge in Unity ECS because most of the things that we're using are all value types and not reference types. Now, value types are great because we can do a lot of performance optimizations for them. However, we can't save a reference to the enemy transform from our player ships. So in order to do that, we're going to need to use a concept known as a component data from entity. Now, a component data from entity is basically a collection where we can pass in an entity value, and from that we get the values of the component at that specific point in time. So basically what we're going to do is on our enemy ships, we're going to save a reference to the player's entity, and then with the player's entity, we can pass in that entity to our component data from entity and then get back the specific world coordinates of our player at that given point in time. So in order for our enemy to reference our player ship, I've gone ahead and just created another data component called target entity, which just has a public entity called value. Now, basically what we're going to do later on is create a separate system that looks for anything with that set target tag, and it's going to go ahead and find our player entity and assign that value as needed so that when we go to actually move our enemy ship, we can reference that entity and any of the data on it through our component data from entity. Now, one important thing that I should point out on the component data from entity is anytime we do this, it is going to incur a random access. Basically, the reason for that is because when we're looking up data on another entity that's not the one that we're executing on, most likely we're going to have to look to a different place of memory that isn't already stored within the CPU cache. So it is going to be a little bit of an inefficiency, but sometimes we can't get around them and we do need to use these component data from entities. Just be aware that there is a little bit of an inefficiency and don't overuse them. So inside our job here, right above this execute function, we're going to go ahead and add in this component data from entity. So it's going to be a public component data from entity. And then of course it's going to be of type translation. Now the typical standard that I use is just do basically the data type. So in this case, it's translation, and then I use the word lookup. So that basically means that we can use this to look up the translation component on any given entity. Now we're going to come back to this in a moment, because if we do it this way, we're going to run into a couple errors, and I do want to showcase what those errors are just so you can kind of understand what happens when you see those types of errors in the future. And the reason that we're actually going to be getting some errors is because, not only are we going to be reading the translation of the player ship entity, we're also going to be writing to the translation of our enemy ships. So of course, because we want to, move our player ships around in the world, we're going to be modifying the translation component. Now, Unity is going to start getting mad at us, because actually what happens here is when we define this translation inside this execute method, basically the way that the code generation works is it actually creates a component data from entity under the hood, basically for every single parameter that we pass into one of these execute functions. And so if we have a component data from entity up here, and then we're doing this where we're basically telling the code generation to make another one, well, it's actually just going to generate one single component data from entity, and it's going to get mad at us because, say, if we're trying to, read the player's position from this one, but then we're going to be, writing to the enemy's translation here, if we're scheduling that across multiple threads, Unity can't necessarily guarantee thread safety on that, because, there could be some situation where, maybe we're trying to read from the translation, but it may or may not have already been modified, just depending on the order that the worker threads have completed their work in. So it kind of does lead to a couple of issues that we need to consider. Now, in our case, this is easy for us because we know that, we're only going to be modifying enemy translations, and we're only going to be reading from the player translation. So there's going to be, some ways that we can kind of, tell Unity to stop yelling at us, and I'll be showing you how to do that when we actually get back to Unity and we see those error messages. Okay, so real quick, I'm just going to go ahead and define the other parameters that we'll be needing here. So we're also going to be needing read and write access to the rotation component, because we are going to be rotating our player in this job as well. Again, the time in world, that's basically just going to count up as long as this entity is within the world. And then we'll be needing read-only access to our enemy ship move properties, our target entity, our move speed, our rotation speed, and then finally I do have read-only access to our local to world component. Now I'm not going to go too deep into how the whole translation system is set up and everything. I do have a pretty extensive video if you do want a little bit more information on how everything is working. But basically, when we have our translation, rotation, and scale components, Unity basically combines those into a local to world component, and then the local to world component is basically what tells the render engine where to render our entity within the game world. And there's a specific reason that I do need to use the local to world, and we'll be getting to that a little bit later. So anyways, the first thing that we're going to do is we're just going to check to make sure that that target entity actually exists in the world. And so we can do that using the translation lookup here. So we'll say if, and then we'll do an exclamation mark for not, and then we'll do our translation lookup dot has component, and then in here we can pass in the target entity dot value. So basically what this means is we're going to go to our component data from entity, that translation lookup. We're going to use the has component method, pass in the target entity right here. And this basically says, does this entity actually have a translation component? If it does not, we'll just go ahead and return out of here, because we don't need to proceed with the job any further if there's no target entity for us to actually follow. However, if there is, let's just go ahead and get a reference to the target position. And then so again, we can use our translation lookup. And then here we kind of index into this like it's an array, where we basically just pass in the entity. Again, we're just passing in the target entity dot value. Now this is just going to give us the translation component, and if we want the actual position off of it, we could just do a dot value at the end. This just basically gets us to basically the equivalent of, say, this translation, And then, if we want to look at the actual value on it, we need to do a dot value. So that's why we do a dot value at the end here. So then you'll see that this target position is a float 3 value. Next up, we're just going to go ahead and do a distance check using the math.distance squared. Again, that's going to be a little bit more efficient than just using the regular math.distance. And so we'll do that on the translation.value, which is going to be the enemy's world position, and then compare that to our target position. Now, if that is greater than our movement properties minimum distance from target, then we're going to proceed with moving the enemy closer to the player. So now, similar to how we did the player movement, the first thing that we're going to do is calculate the current movement in this frame. Now, basically the way that we want this to work is our enemy is always going to basically face the direction of the player's ship, and then it's just going to move directly forward. Now, I did include this local to world because there is an easy way where we can get our forward direction. So if we do a local to world dot forward, that's going to be the exact forward facing direction of our enemy ship. And then we can just multiply that by our move speed dot value. And again, we want to multiply that by a delta time as well. So outside of here, we'll just go ahead and define a public float for delta time. And then finally, we're just going to want to apply that current movement to our current translation dot value. So we'll just do translation dot value plus equals our current movement. So this basically is just going to move the enemy ship in a straight line from its forward facing direction. Next thing that I'm going to do is just, again, make this a little bit more interesting. So rather than just moving straight forward in a straight line, it's actually going to move side to side as it goes forward. So what we're going to do first is we're actually just going to get our time and world dot value and plus equals with delta time, just so that time and world kind of continues incrementing here. The next step, we can calculate our lateral movement. So set this equal to local to world dot right. So in this, instead of doing a dot forward, we're going to do a local to world dot right. So that's basically going to give us the right direction from our enemy ship at any given point. No matter how it's oriented, it's always going to be right from our enemy ship rather than, the right in our world space or anything like that. So we'll multiply that by our movement properties dot lateral amplitude multiplied by delta time multiplied by math dot sine. In here, we can pass in our time in world dot value and multiply that by our movement properties dot lateral frequency. So this is just a basic sine wave, and it's going to go ahead and move our enemy ship smoothly from side to side. And then of course we just need to go ahead and add that to our translation dot value as well. And then the final thing that we're going to want to do is set our enemy's rotation so it always faces the player. So I've just gone ahead and done something similar to our player ship, how we set the rotation based off of the mouse position. However, in this time, we're going to do it based off of the target position. So see that I'm going to do just a first quick distance check to see if the distance between the translation value and the target position is a very small number. If so, we'll just return out of here because we don't want to mess with trying to calculate a rotation from the same position. And then again, we're just going to go back to our math utilities and do a get rotation to point from our current translation to our target position, which gives us our rotation target. And then we can do a rotation.value set rotation towards the rotation target and passing in our rotation speed.value times our delta time. So again, those are just those math utility helper functions that we created earlier on. Okay, so now we'll actually just go ahead and schedule the job. So we'll go ahead and do a new move enemy job. And then for our parameters, the first one that we'll set is our translation lookup here. Remember, this is a component data from entity, and the way that we actually get the component data from entity is using, well, the get component data from entity. And then in here, basically we just pass in the type that we want, which in this case is going to be the translation. For delta time, we'll go ahead and set that, of course, equal to a time.delta time. And for the epsilon, we'll set this to a small value of 0.01f. Now this one, we're just going to go ahead and do a schedule parallel. Now we'll come back over to Unity and we'll hit play, and it's not actually going to do anything because you'll remember that we're not actually setting a target for the enemy ships yet. So we're going to go ahead and do that now. So in order to do that, we're going to go ahead and create this get target system. Now you'll notice that I've added a couple attributes here to specify our system ordering. The first one, I don't believe I've used this one in this video yet. It's going to be the update in group. So basically when we look in our systems window, you'll see that there are a number of basically groups that we can use to kind of group together systems. And this is a really handy organizational thing. And there are actually ways that you can create your own custom system groups. So in this case, we're just going to hook into the default one, which is the simulation system group. However, we're also going to put this extra part to this attribute that says order first equals true. So that means that it's basically going to force it to the very beginning of the system group. However, we are going to want it to update after the begin simulation entity command buffer system. I'll just go ahead and let that run first, and then our system can run after that. And it should be noted, if we actually F12 into the begin simulation entity command buffer system, you see that it does actually have this same attribute, which is the update in group type of simulation system group, and also does have the order first attribute set to true. Okay, so anyways, let's get started creating this job here. So first thing that we're going to need is a public entity for our player ship entity. So basically outside of this job, we're going to get a reference to that player entity, and then we'll pass it into this job here, and then we can actually set the specified component inside of our job here. Also, in order to do that, we're going to go ahead and need an entity command buffer. Of course, we can just call ECB, and that's going to allow us to add the component for the player's target reference and then remove that set target tag component. So inside this execute method, I'm actually not going to define basically a number of components to structure an entity query. I'm actually going to show you another way that we can schedule these jobs where we actually create the entity query outside of the job and then manually pass in an entity query in here. However, we will need a reference to the entity that we're operating against, which is going to be the enemy ship entity. And in here, all that we're going to do is an ECB.remove component type of the set target tag. Of course, we're going to be removing that from the enemy ship entity. Then we'll do an ECB.add component. We're going to add this component to the enemy ship entity, which is going to be a new target entity. And then for our value, we'll pass in our player ship entity. So again, basically what this job does is it just removes that set target tag, and then it adds and sets that target entity component. So pretty simple job. Now we're actually going to go ahead and schedule it here. So here I'm actually going to do something a little bit different. Now, you remember that we don't need to run this job, very often. And we know that, we're only going to have one of these enemies spawning once every 3 seconds. So we really don't need to be, all too crazy about how we optimize this job and everything. So I'm going to show you how we can actually manually create our own entity command buffer. So do a var ECB is equal to a new entity command buffer. And then inside here, we're going to have to pass in an allocator. Now, because we're passing this entity command buffer into a job, we need to use the temp job. And the temp job allocation means that we need to dispose this entity command buffer within a 4-frame window. However, we actually are going to be manually disposing it basically right after we use it here. So anyways, let's just go ahead and schedule this get target job. So we'll do a new get target job, and we can go ahead and set the parameters. I'm going to go ahead and get the player ship entity later, but first we'll just go ahead and set the ECB equal to our ECB that we just created here. And then this time I'm actually going to do a .run. So this is going to basically run it right on the main thread, which means that everything inside this execute method down here is just going to run immediately. So once that has been completed, now we can actually manually play back the changes of the entity command buffer just by doing an ECB.playback. And inside here, it's asking us for an entity manager, and we can just use the entity manager that is part of the system base class, which is just capital E entity manager. And then finally, we do need to manually dispose the entity command buffer. So we'll do an ECB.dispose. So again, let me just real quickly run through what's happening here. We're going to allocate a new entity command buffer. We're going to schedule and then immediately run this new get target job. Now our job is going to use the entity command buffer to record the operations for removing this component and then adding this component. And then the operations don't actually run until this job has been completed. And then we call our ECB.playback. Now remember, at this point, this is going to incur a new sync point in our code, but again, then I've determined that this isn't really that big of a deal because this is happening very infrequently in our game. And then finally, after that, we just need to make sure to dispose the entity command buffer because we are, allocating it up here. Okay, so now we're going to go ahead and get a reference to our player entity. So here we can just go ahead and create a private entity inside this getTargetSystem class, which we can just call the playership entity. And then here in the onStartRunning, we can actually go ahead and set that playership entity. Now there's another of these handy singleton methods that we can use, which is the getSingletonEntity. So basically, whichever component type that we pass in here, it's going to find the singleton entity with that component and then set it to our entity value here. Now we could use something that like references our player's movement or something like that. But in general, that's not like necessarily the best practice. Typically we would want something like a tag that specifies that that is the player entity. So I'm just going to create another of these tag components, which is again just an empty iComponent data. This one's called playership tag, and then we'll just go back to our playership authoring. Again, just do a DST manager.add component. This is going to be the playership tag, and then we'll just go ahead and add that to the new playership. So now back in the getTargetSystem, we'll just do a getSingletonEntity on the playership tag. Of course, it does not take in any parameters, and now we have our reference to the playership entity set. So now when we actually go ahead and schedule our job, we can set the playership entity equal to the local playership entity that we found earlier in the system. And then so kind of like I mentioned, we do need to specify an entity query that will pass into this job here, because if we just did this default one, we're only just passing in an entity, which means it's going to run on every single entity within our game, and that's not exactly going to work. So what we'll do is another member variable, which is going to be a private entity query, which we can just call the enemy ship query. So we can create the enemy ship query using our entity manager. So we can do our entity manager.create entity query. And in here, we can pass in the type of whatever data components that we want. So in this case, we're going to want to do the set target tag. There are more complex ways that we can create these queries, and I may be showing a few of them later on in this video. But if we just want to do a simple entity query looking for anything that has that set target tag, that is how we do it. And now that we have that enemy ship query, we can simply just pass that into the parameters of our run method here. So that is the enemy ship query there. So now we can pop over to Unity, enter play mode, and you see that nothing is happening, and we are getting some error messages in the console. So again, these are the ones that I wanted to show you in relation to that component data from entity. Now this is important because you may be running into errors like this as you go along in your programming, so it's nice to kind of understand how to actually handle these different errors. So in this case, this says invalid operation exception, move enemy job data translation lookup is not declared read only in an iJob parallel 4. This container does not support parallel writing. Please use a more suitable container type. So what exactly does that mean? So basically, it is calling out that translation lookup that we have created here for the component data from entity. Now what that particular error message is saying is because we are doing a schedule parallel when we schedule the job here, the component data from entity doesn't support parallel writing. Basically the reason for that is because, say that from multiple threads, we are writing to the same location in memory using this component data from entity. Well, that's going to end up being a problem because we can't really guarantee, the result is going to be the correct result that we're expecting because, some threads may run operations faster or slower, depending on how much other work that it needs to complete. However, because we know that the way that we've created this execute method, we're only going to be writing to the translation of one entity at a time. There's never going to be a situation where maybe, multiple instances of this job can be writing to, say, the same location in memory. We know that we're only going to be writing to one enemy ship at a time. So luckily, Unity allows us to kind of disable some of these safety checks. So we can put an attribute above this component data from entity. And this particular one is going to be the native disable parallel for restriction. So that basically means that, we can do parallel writing because we are disabling that restriction there. So now we'll come back to Unity, enter play mode, and you'll see that now we're actually getting some more errors. And you see that this one reads here, the writable component data from entity Unity transforms translation. Translation lookup is the same component type handle as the translation component type handle. Two containers may not be the same thing, aliasing. Now the reason that we're getting that error is because we're using the translation lookup to find, other translations. In this case, we're just looking for the player's translation. However, we're also reading from and writing to the translation of the enemy ship. So basically we kind of have, again, two instances of this translation lookup. One of them we're using to read from the player's translation, and then another one we're going to be writing to the enemy's translation. And again, because we know that we've structured a code in such a way that, we're pretty certain that we're not going to run into any major issues. Again, we can disable some of these safety checks by doing a native disable container safety restriction. So we just can add that attribute. We can just do a comma right after the other one, and then we'll come back to Unity, and now we can enter play mode, and you'll see that in just a moment we now have some enemy ships that are flying towards us, and they're moving side to side, and you see that they get close to us and they'll stay away from us. If we kind of move around the screen, they'll start following us, and you'll see that they're moving at the exact same speed as us. So now they're all just in this giant cluster right here, and that looks hilarious. So I know that was kind of a lot, so maybe this might be a good time for you to kind of take a quick break and kind of go back over some of your code and just make sure you kind of understand the basics of what we did here. Maybe just play around with it for a little bit before we move on, because next up we're going to be doing some more things that will start getting a little bit more complicated when we actually start shooting our weapons at each other. And by the way, if you've been enjoying this tutorial so far and you've been finding it helpful, I'd really appreciate it if you hit that like button, and also share this video with someone who you think might find it useful, or maybe on some forum or Discord community that you frequent. Okay, so now we're going to go ahead and actually get our players and enemies to shoot some shots at each other. So let's just go ahead and create a new 3D sphere here. And then we can just call this our shot prefab, because we're going to be making a prefab out of it here. And a couple things that I'm going to do here, I'm just going to set the scale to 444 just to make it a little bit larger and more prominent within our scene here. For our mesh render, I'm going to change this over to the shot material, so it's kind of this orange color. And then I'm just going to go ahead and remove this sphere collider off of here, because we're going to be using the Unity DOTS physics a little bit later on when we actually get into collision detection. So now we can just go ahead and drag this over to our prefabs folder and delete this main one out of our scene, and then make sure you add the convert to entity component as well. And so at this point, I'm going to offer up a little challenge to you. I'm going to have you go ahead and create a new data component for the entity lifetime. This is basically just going to be a float value to track how long that this shot will live in the world, and then go ahead and create a custom authoring component to add that shot lifetime to the shot prefab. And then you're also going to need to add the move speed component to that as well. So again, you're just going to go ahead and create that one new data component for the entity lifetime, and then create a custom authoring component where you can set the lifetime as well as move speed, and then add those both to the shot prefab here. So I'll let you go ahead and do that, and then show you how to do it in just a sec. So should have been pretty straightforward. You're just going to go ahead and create this iComponent data for entity lifetime here with a public float called value. And then over in the shot authoring, just going to go ahead and expose fields for the move speed and shot lifetime, and then just using the DST manager.add component data. Of course, we're going to be adding those components to the shot entity, where we're going to just go ahead and use our existing move speed value, or we'll set our move speed, as well as the entity lifetime, passing in the shot lifetime here. Then of course you can come back to Unity on your shot prefab, go ahead and add that shot authoring, and then I'll go ahead and set a move speed of 100 and a shot lifetime of 2.5 seconds. Okay, so now we're actually going to go ahead and move these shots in our world. Now this time, instead of using an iJob entity, I'm going to show you how to use an entities.forEach. I want to show off these because there are a couple other places in this video where we do have to use an entities.forEach, and I'll be discussing why that is in just a moment. But it's also important to learn these because there's a lot of forum posts and other documentation online that will be referencing these entities.forEach functions, because they've been quite common for a long time. Now, although they're being sort of phased out by Unity, there still will be a lot of things referencing these. So I do think it is important for you to understand how these entities.forEach functions work. So we can just go ahead and do an entities.forEach, and then this ends up being a little bit of a lambda function. So we do have to put a second set of parentheses inside this first set of parentheses, And then here's where we actually create our entity query. So in this case, it's going to be kind of similar to like an execute function like we were doing. So we can do a ref translation and call it translation. Next up, we're going to look into the move speed here. And we can call this move speed. And then we're also going to want read-only access to the rotation. So I'll just call this rotation, and I'll show you why that is in just a moment. Now, again, because this is a Lambda function, what we need to do here is after this first set of parentheses, we're going to go ahead and do the equals and then greater than symbol. So kind of like make a little bit of an arrow. And then we're going to do an open and close curly braces. I'll just go ahead and hit enter. So this goes, basically creates a new line here. And then inside here, this is where we're actually going to be defining the work of our entities.forEach function. So here's where we're going to be doing our data transformation and all that. Now, just to get rid of this last little line at the end, this is where we actually just go ahead and do a schedule parallel. So you see that there are a lot of similarities to an iJob entity batch. However, this time we're just defining it directly inside the onUpdate method of the system base rather than in its own separate job struct. So now, similar to before, we're going to go ahead and set the current movement, and then we're going to be adding that to the translation afterwards. Now, I did pull in this rotation because we can actually use that to get the forward direction of the particular entity that we're going to be iterating across. Similar to how we did like a local to world.forward, there's actually something that we can do using the math library. So we'll do a math.forward, and then inside the math.forward, we can actually pass in the rotation.value, and that will give us the forward direction relative to the current rotation of the shot. And then of course we'll just go ahead and multiply this by our move speed dot value, multiplied by time dot delta time. This is wrong. I'll be showing you why in just a second. And then here we can just do a translation dot value plus equals our current movement. So that is basically the system here. These entities dot for each, again, they're pretty similar to the iJob entities that we've been using throughout this video. However, there are some quirks and some other things that you need to note about them. So I will leave some more references to those in the related videos. But anyways, let me show you what happens if we just go ahead and come back to Unity. You'll see that we didn't even need to run the application. Just right when it compiled, we immediately got this error saying the entities.forEach lambda expression captures a non-value type this is only allowed without burst and run. So basically the reason is because we're getting this time.delta time here. Now basically the way that these work is we actually have to capture this in a variable beforehand. So we can say a var delta time is equal to time.delta time. And then inside here, we can actually just use this value that we created here. So basically kind of behind the scenes, these entities.forEach, these actually manually create a job, very similar to what the iJob entity batch does. So we do need to actually capture this value before we actually use it inside the body of this Lambda function here. So anyways, I'm just going to go ahead and drop a couple of these shot prefabs into the scene just so we can kind of, watch them go forward. So go ahead and enter play mode and you'll notice something interesting happens. You'll see all the shots go straight up. However, our player ship is moving as well. And look, I don't have my hands on the keyboard or anything, and our player ship is just going up straight forward. So what the heck is happening with that? Well, you'll notice that inside this move shot system, again, this is basically creating an entity query for, what types of entities that we want to run on. So we do need to, be careful and make sure that we're actually querying for the exact entities that we want, no more and no less. So right now, this is looking for anything with a translation, a move speed, and a rotation, and it's going to do operations on that. So right now, not only is it running on the shots, but it's also running on the player as well as all the enemy ships. So we basically need a way to say, hey, let's only run this on the shots in the game, and we can just, ignore everything else. So I'm just going to create a new empty data component called shot tag, and then inside the shot authoring component, I'll just go ahead and add the shot tag as well. So now in the move shot system, we can do something cool with these tags. So we can actually basically put another option inside this entities.forEach where we say with all. This basically will add to the entity query, so we can query for anything that has the shot tag, and it's going to ignore anything that does not have this shot tag. Now this is really cool because we don't have to add this as like an extra data component inside the entities.forEach, because, well, this doesn't even have any data to run off of anyways. So we can just do this with all shot tag. And then now when we come back to Unity and enter play mode, you'll see that the shots just go across the screen and the player is just kind of stationary here, and we can kind of move around with the W, A, S, and D keys as we would expect it to. Okay, so we'll just go ahead and delete all these shot prefabs out of our scene. Okay, so we want our player and enemies to actually fire their weapon from basically kind of the tip of their ship here. So what I'm gonna do is I'm actually gonna go ahead and create another empty child object under my player ship here. This will be called the firing point. And then we can just go ahead and drag this firing point up to right about there. Looks like I can just go ahead and set a value of 9 in the Z direction for that. Then I'm going to go ahead and go over to the enemy prefab, open that up, go ahead and add an empty game object, which will also be the firing point, and set this to a value of 9 in the Z direction here. Perfect. So we'll go ahead and save changes to the prefab. Okay, and so we'll just go ahead and create another data component for the firing point entity, which is going to have a public entity value. And the purpose of this is going to be similar to what we did for our enemy movement, how it follows the player's position. We're going to be able to use the reference to the entity's firing point in order to find that space in the world where we actually go ahead and spawn the new shots. Okay, now a couple other things that we do need to take care of before we actually get into spawning these shots into the world. First is going to be this shot cooldown timer. Basically going to have this value count down to 0, and then we can do a check on it to see if it is below 0, which means that we can actually shoot the weapon. And when we do shoot the weapon, we'll just go ahead and reset our cooldown time here. Next up is the team ID, and this is just a simple enum here, so we can just differentiate between the player ships versus the enemy ships. And basically each ship is going to have one of these team ID components on there, so we can basically say, you know, this is either a player ship or an enemy ship. And then using that, we're actually going to add this same component data to our shot. And then when we go ahead and do our collision detection, we can actually do a quick comparison on the ship to see if the shot came from a ship of the different team. So we can just come back to our base ship authoring here and then go ahead and add on these new components, because basically every ship in our game is going to need these. Okay, so you'll see that I've added this shot cooldown timer with an initial value of 0, so we want to be able to shoot right away. Cooldown time is set to that cooldown time that we've exposed here. You'll notice that I did use a game object for the fire point entity, again, because there is kind of that conversion that happens. If you remember, kind of in the past, we did that iDeclare referenced prefabs. In this case, we actually do not need to do the iDeclare reference prefabs, because this fire point entity, this is not a prefab. This is basically an entity that is a child game object of it. So it is basically not a separate prefab that we're actually going to be spawning. This is basically just an entity in the scene that we want to have a reference to. However, we still do need to do the conversion system.get primary entity and passing in that game object, so we can actually get the resulting game object from the conversion system. Then finally, of course, we'll just go ahead and add the team ID and set the value to that team ID enum that we set in the authoring. So we'll come back over to Unity, and on our player ship, we can set a cooldown time of 0.5. Our fire point entity, that is going to be this firing point child object that we can set there. And then you'll see by default, the team ID is set to player ships. Again, we're just going to go ahead and do the same thing on the enemy ship. Let's actually set the cooldown time of these to 0.25, so they're a little bit faster here. We will actually have to open up the prefab to get that firing point child object, and this time we want to make sure that the team ID is set to enemy ships. Go ahead and exit the prefab and save our changes. Now the enemy ships, we're basically going to have those firing as long as our player is active in the game. However, for our player ships, we want it to only fire a weapon when the space key is pressed. So we are going to need to add another data component in order to keep track of when the space key is pressed or not. So we just have this public struct for player weapon key pressed, which is a public bool called value. Of course, we can just go ahead and add that to our player's authoring component here. And because we're going to be setting this component at runtime, we can just add the component with the default values here like that. So then we'll go back to our get player input system, and we'll add the final method that we're going to be adding here, which is the get player weapon key pressed. Of course, it's just going to return a type of that weapon key pressed. So all we're going to do here is do our input.get key, again looking at our player input keys.primary weapon key. Again, we basically kind of set that up at the beginning of the video, and that's what sits on kind of the game controller entity. So we just go ahead and check the input.get key on that, and then just go ahead and return a new player weapon key pressed determining if the player weapon key is pressed or not. You'll notice that we're doing a get key as opposed to a get key down because we want this to return true, even if we're holding down the space bar. So basically we can hold down the space bar and our player ship continues to fire shots. And then in the on update, of course, we'll just go ahead and call that, just call the get player weapon key pressed, just save that to a local variable here. And again, we'll just do a set singleton because we know that there is only going to be one of those players within our game. Okay, so now we're going to create the shoot weapon system. Now this one's going to be kind of an interesting one and it's going to be a little bit complex, but I just kind of want to show you a couple things about Unity ECS. One of them that I'm going to be showing you is how we can kind of use one system to shoot the player's shots as well as the enemy's shots. And then the way that I'm actually going to be accomplishing this is rather than using an iJob entity or an entities.forEach, I'm going to be using an iJob entity batch. Now the iJob entity batch, I think this is a good one for you all to understand because it is actually the thing that the iJob entities as well as entities.forEaches get converted to behind the scenes. So it really just kind of gives you a little bit more of an understanding about what is going on under the hood. However, they are going to be a little bit more complex and do include some more boilerplate code. You definitely can get away with creating these using, say, an iJob entity batch or an entities.forEach, and you may even be able to figure that out on your own by this point in this video. However, I just want to show you something a little bit different. So I'm going to be going through how to do this using an iJob entity batch. Now, of course, if you do want to learn more about these, I do have a video going over exactly what they are and how to use them. So go check that video out if you do want a little bit more information on that. So similar to an iJob entity, we're going to have to define this separately than our system base here. So we can do a public struct, and this is called the shoot weapon job, and it will implement iJob entity batch. You'll notice that we're not doing a partial struct. It just needs to do a public struct here. You do see that the member that we need is this public void execute. So already kind of looking a little similar to an iJob entity. And of course, we can also make this burst compile as well. And you see that in Writer, we do have this little option saying burst compiled code. Now, a little bit different than the iJob entity. In here, we have to keep these parameters as is. We actually do not define the things that we're going to be accessing right here. The way we actually define what we want is we have to do this manually through some component type handles. So I'm going to go ahead and show you an example of what these component type handles look like. So actually we have to do this before the execute function. We can do a public component type handle, and then here we pass in basically the type of value that we want to access. So the first one that we're going to do is the shot cooldown timer here. And so I can call this the shot cooldown type handle. So the reason that this is public is because we actually need to set this and assign it when we schedule our job. So that's something that we need to make sure that we're going to be doing. And when we define it like this basically gives us read and write access to the components of this type right here, which is what we want for the shot cooldown because we do want to decrement that by a delta time each frame in order to properly update the timer. However, the other ones we just need read-only access to, and so we actually do need to go ahead and put this read-only attribute before here. We want to make sure that we're using the one from the Unity.collections. So we can do the read-only attribute before that. Again, we're going to do another public component type handle. This time we'll look up the player weapon key pressed, just call it the player weapon key type handle. Again, we only need read-only access to this because we just need to read whether the player is holding down the weapon key or not. So just those two type handles will be enough to get us up and running for now. So now let's talk about how we actually access these components on one of these component type handles. So the way that we actually do this is we need to get a native array from these different type handles, and this native array basically contains all the actual data values of that type. Now, a native array, if you're not familiar, it's very similar to just a regular array. However, they are fully compatible with ECS and the burst compiler and everything like that, so they are very performant. So what we can do is we can say a var shot timers is equal to batch in chunk dot get native array, and then here we pass in the shot cooldown type handle. This iJob entity batch, these actually operate over chunks rather than individual entities like in an entities.forEach or in an iJob entity. So now basically we're going to take a look at this chunk, and then we're going to go ahead and say let's get the native array of all the shot timers in here. So let's say maybe there's 20 entities in the chunk that we're on right now. It's basically going to return a native array of type shot cooldown on timer in the size of 20. Now, one of the cool things that we can do with an iJob entity batch is we can actually take a look at the components that are in that chunk right now, and then basically make a determination of what components these have, so we can kind of do some optimizations. So in this case, again, you'll see that I've passed in the player weapon key type handle, but you'll remember that we're going to be running this basically on both players as well as enemies. So only players are going to have this player weapon key pressed component. However, enemies are not going to have that component. So actually what we can do is we can actually just go ahead and save a variable called isPlayer. We'll set this equal to false by default. And so we can actually do a check here to see if this is a player ship. So the way that we do this is we do an if batch in chunk dot has, and then here we pass in again the component type handle that we want, which in this case is going to be the player weapon key type handle. So this basically means if the archetype chunk that we're on has this component type of the player weapon key, then we know that we can actually get that native array. In this case, this basically means that this is the player. So in here, we'll go ahead and set isPlayer equal to true. And then Ryder's getting mad at me because there's an easier way that I can do just that, but we're going to be adding something to here. So basically what we want to check is we want to see if the player's weapon key is pressed. And then we'll just go ahead and set this equal to false by default. And then so inside here, we'll go ahead and set the isPlayer weapon key pressed. Now again, we're going to do the batch in chunk dot get native array, passing in the player weapon key type handle. However, this is going to give us the full array, and we just want to index on one element of this array. Now we know that we only have one player in our game, so this is easy for us to do. We can just put at index 0. However, this is still not giving us the value that we want. We actually need to go ahead and check the value of that. So when we do the dot value, it's actually getting us the value of that data component for the player. So again, this is one of those things that might seem a little bit complicated, but basically we're just getting the native array. We're going to access the first element of the array, which we know is the player, and then we're actually just going to get the actual value to determine whether the player's weapon key is pressed down or not. But we'll come back to using this when we actually go ahead and iterate on all the entities within this chunk here. The next thing that we're going to go ahead and do is we'll check to see if the chunk that we're iterating across is the enemy ships. So very similar, we're just going to go ahead and do a read-only public component type handle. And this one's going to be on our target entity. And we can just call this, of course, the target entity type handle. And then so very similar, we'll just go ahead and do an if batch in chunk dot has target entity type handle. This means that we know that this, so we'll say if is enemy here, just to make that kind of clear. If is player right there. So what I'm actually going to go ahead and do is get that target entity, and we'll just make sure that that target entity exists. So we'll say var target entity equals batch in chunk dot get native array. This time we're going to be again passing in the target entity type handle. Very similar. I'm just going to look at the first element in the array. We can kind of cheat here because we know that our application only has one player. So that basically means that, you know, any enemy in our game is going to have the exact same value set for the target entity. So again, we can just do a dot value there, and that will actually return us the player's entity. Now here, we can just go ahead and check to see if it exists. Now, if the target entity does not exist, we're going to go ahead and return out of here. Basically, the reason that we're going to do this is it's kind of like a little bit of an optimization again. You know, we can just kind of look to see, you know, if that target entity exists. If it does not, we're just going to go ahead and return out of this function and not do any further processing. What this is going to happen is at the end of our game, when the player is actually destroyed, then the enemies are going to stop shooting their weapon because, well, there's no point to shoot their weapon. And so actually what we're going to do to confirm that an entity exists is we're going to use a component data from entity, and on there we can do the .has component, and that will basically confirm that the entity exists. Now we can pretty much use any component that the player has to check to see if the player exists. However, in this case, I'm going to use the local to world component. I'll be showing you kind of why I chose this more in a second, but basically we are going to be using this to determine where our firing point is later. So it just kind of makes sense to, use this one because we know that the player has a local to world component. And so again, we're going to be declaring this one as a read-only component data from entity because we're only reading data from it. It's very important that we put these read-only attributes before the ones that we have read-only access to, because there are, many optimizations that take place behind the scenes. And if we, are only reading from it, we need to make sure that we specify that. So I'll go ahead and call this the local to world lookup. So now down here, again, if it is the enemy, now we can just do a quick comparison and we'll say if not local to world lookup dot has component. And in here we pass in our target entity. And so if that's the case, we'll just go ahead and return out of the function here, because again, we just no longer want to process any shooting if the player does not exist. Okay, so now let's go ahead and actually iterate across the entities. Again, all that we're doing up here, these are all operations on the chunk. Again, this is really efficient because there are going to be significantly less number of chunks than number of entities. So it's kind of an efficiency thing. If we can kind of do some of this processing ahead of time, it makes it a whole lot more performant when we actually go to iterate across all our entities. We don't have to say, hey, does your target entity exist, when we know that the target entity is going to be the same across the board. So now we'll actually go ahead and iterate across our entities. The way we do that is just by using a simple for loop. And then for the upper bounds of it, we can do the batch in chunk dot count. And then so that basically means, what are the number of entities that we're going to be iterating across? And then of course, we're just doing a basic for loop on them. So here we're going to start by decrementing our shot timer. So first we're just going to go ahead and need a reference to our shot timer. So this is going to be the shot timer that is associated with the specific entity that we're iterating across. Now you'll remember that we did already grab the native array for it up here. So we have this shot timers that we can just go ahead and easily key into. So we can say shot timers at position I, and then here we'll just go ahead and do a shot timer dot value minus equals our delta time. Of course, we just go ahead and need to add this as another public float up here. So then here we'll just go ahead and do a quick check to see if the shot timer's value is greater than 0. If it is, we'll actually just need to go ahead and set the shot timers at position I equal to that updated shot timer, because again, because these are value types, when we decrement it here, it doesn't actually update the value in the array. So we need to go ahead and assign that back to the array, and then we can just go ahead and say continue. So this basically means, we're going to move on to the next entity because this entity's shot timer has not expired yet. Then the next check that we're going to go ahead and make is we're going to see, if this is the player and the player's weapon key is not pressed, we're just going to go ahead and continue as well. So this basically means if we are iterating across the player and the player's weapon key is not held down, just go ahead and move on to the next entity, because we only want to be shooting shots when the player is holding down that weapon key. Now basically this means that everything past here, we know that the shot is basically a valid shot and we can go ahead and actually shoot it. So the first thing that we're going to want to go ahead and do is set our shot timer dot value equal to the shot timer dot cooldown time, just to reset that timer for the next time. And again, we do want to make sure that we're setting that value in the shot timers array. Again, shot timers at position I is equal to our shot timer. So that'll just reset it here. Next thing that we're going to do is actually go ahead and instantiate the new shot. So we have a var new shot. And so again, we're just going to go ahead and use an entity command buffer. So we can do a public entity command buffer. Now this time I'm going to do one that's a little bit different. I'm going to do an entity command buffer dot parallel writer. Again, we'll call it ECB as normal. The reason that we're doing a parallel writer is because I'm going to be scheduling this job in parallel, because this job is one that can potentially be running very frequently. So this is a job that we do want to schedule parallel. Now, if we just try and use our regular entity command buffer, we're going to get a warning saying, this container is like not suitable for parallel writing, use an appropriate container. We're going to get kind of one of those warnings. The way that you fix this is just by doing an entity command buffer dot parallel writer. Now the parallel writer, the way we use that is pretty similar to a regular entity command buffer, where we can just do an ECB dot instantiate. Now you'll notice that the first value that this takes in is the sort key. Now the sort key is necessary because this is basically a way for the entity command buffer to determine what order that the commands need to be placed played back in. Of course, if we're scheduling this job across multiple worker threads, we can't guarantee, which commands should happen before others. Now there's an easy way to do this sort key. All we do is you'll see that up at the top, when we inside this execute function, we do have this integer for the batch index. So this is basically just, an index of all the batches that we're operating across. We can just go ahead and pass in the batch index right there. And then here's where we actually, of course, pass in the entity that we want to spawn. In this case, we're going to be spawning the shot prefab. Now the way that we actually get the shot prefab, we can just expose this, and then we'll get this when we actually schedule our job here. So we'll do a public entity called shot prefab. Okay, great. So at this point, we've now basically spawned the shot prefab in the world. Now we need to set that position as somewhere specific. And again, we do want to set this basically at the firing point. Now, in order to get the firing point, we're going to go ahead and create another component type handle. So we'll do a read-only public component type handle. And again, this is going to be the firing point entity. We call this the firing point type handle. And then we can do this basically after we're checking if it's an enemy or not. But before the for loop, we'll just go ahead and say var firing points is equal to batch in chunk.get native array, passing in the firing point type handle. So from that, we can get the firing point entity just by going to our firing points at position I dot value. So again, that's going to return us the entity of where our firing point is for this specific entity that we're iterating across of. So this is, say, if we're on the player right now, this is the firing point that belongs to that specific player. Next up, we're going to get the local to world component off of the firing point. So we'll just call this fire point LTW, and we'll set this equal to our local to world lookup. And then in here, again, because this is a component data from entity, we can pass in an entity into here and get our firing point entity. Now, again, there are a couple of reasons that we're using the local to world rather than the translation, because the local to world, again, it's a combination of the translation, rotation, and scale. And we want to look at not only the translation component of the firing entity, but we also want the rotation of it. So we know what orientation to fire our shot in, because we want our shot to go straight ahead of the player. Another reason that we do this is because the local to world represents the real world coordinates of our entity. If we're just looking at the translation, this would basically be the translation relative to the player position. So no matter, however much our ship moves around in the world, the translation component is always going to stay exactly the same because it is just statically in that one point right there. So here we can just go ahead and get our fire position. We'll set this equal to the fire point LTW dot position, and then we'll also get our fire orientation. Set that equal to the fire point LTW dot rotation. So now we can just go ahead and use the entity command buffer. So we can do an ECB dot set component. Again, we do need to pass in the sort key, which is the batch index. Next up, we need to pass in the entity that we're going to be setting the component on, which is just that new shot entity. And then finally, the component, we can just pass in a new translation where we'll set our value equal to the fire position. And then we'll do also an ECB.set component, batch index, new shot, new rotation, and in here we'll pass in a value of the fire orientation. So that's now going to spawn the shot in the correct world position and orientation. There's one last thing that I want to do before we can test this out, and that is just to add the team ID. So again, we can do another read-only public component type handle. Here is going to be the team ID type handle. And then again, right after we get this firing points right here, we can do a var team IDs equal to batch and chunk get native array team ID type handle. So then here we can get the current team ID, set this equal to team IDs at position I, and then we'll do an ECB.add component because the shot entity doesn't have the team ID by default. Again, batch index new shot, and then here we can just pass in the team ID because that team ID is a component type itself, so it will let us do that. Okay, so now this job is basically just about complete. We're going to come back and add one last thing to it later on, but for now, let's just go ahead and schedule this job up. So we'll go ahead and do a new shoot weapon job, and in here we can go ahead and start assigning things. So the first one is going to be the shot cooldown type handle, and we can do a get component type handle, of course passing in the type of the shot cooldown timer. And I'm going to leave the parameters empty for now and show you why, because the next one that we're going to set is the player weapon key type handle. Again, we're going to do a get component type handle, passing it in the player weapon key pressed. This time inside the parameters, I'm just going to go ahead and pass in true, because it does take in a parameter for is read only. Now is read only is false by default, so that's why I did not add it up here. Again, it's really important that anything we mark as read only down here, we do need to pass in the true here, so it actually does give us the read-only type handle. Next one is the target entity type handle. Again, we will be passing in true in here. The local to world lookup. Again, this is going to be a get component data from entity for local to world, because this is a component data from entity. Again, same thing. We do need to pass in true on here because it is marked as read-only. The firing point type handle is going to be a get component type handle for the firing point entity. Again, pass in true. The team ID type handle, get type handle on team ID. Again, passing in true because it is read only. Next up is our delta time, which of course we can just set to time.delta time. Okay, next up, we're going to need our entity command buffer. So I'm going to go ahead and define a private, and we'll spawn these in the begin initialization entity command buffer system. Again, we're going to spawn this at the beginning of the next frame, similar to how we did with spawning the new enemy ships into the world. Next up, I'll define an on start running, and we can set our ECB system equal to a world dot get existing system, passing in, of course, the begin initialization entity command buffer system. And then we can actually set our ECB equal to ECB system dot create command buffer. Now we have to do one extra thing because again, it is a parallel writer. So we just do an dot as parallel writer. Lastly, the one that we do need to define as well is the shot prefab here. And we can just go ahead and make this another class variable here for a private entity called shot prefab. Now we need to actually get this shot prefab from somewhere, so I'm just going to go ahead and create this new shot prefab. I do have the generate authoring component on here because it's just one thing and we don't necessarily need to create a whole authoring component for that. And when we go back to Unity, we're going to end up putting this on our game controller entity. So what we can do is we can just go ahead and get this shot prefab by doing a get singleton type of shot prefab, and then just do a dot value to actually give us the entity value of that prefab here. So now when we're scheduling our job, we can just easily go ahead and pass in the shot prefab there. So now let's go ahead and schedule this. We're going to do a schedule parallel, and then in here we actually have to pass in a manual entity query. So we can actually define this entity query in the on start running. So we will need another private entity query. We can just call this the shooting entity query. So I'm going to be creating this shooting entity query using a different method, which is by using an entity query description. So here we can just do a var shooting DESC equals new entity query description. And then here we can kind of define the component types that we want to set. So the first property that we're going to set is the all. This basically means that we need all of these components that we defined in here. So basically the way that we do this is we make a new component type array, and inside we can actually set the values that we want. So in here, we're going to need a type of cooldown timer, also a type of firing point entity, and then lastly, a type of team ID. So now these are basically all the required components. You know, every component that's going to be shooting needs these. Another one I'm going to put is the any. So this basically means that it needs to have at least one of the component types that are passed into here. Now in this case, again, we know that we can either run this against our players or against our enemies. So for our players, we can basically get this by doing a type of player ship tag. And then for our enemies, we can do a type of target entity. So this basically means it needs to have either the player ship tag or the target entity, or it could even have both. Now there are other things that we can do for the entity query descriptions. Like if we wanted to say none or we wanted to say exclude components from the query, we could do that as well. However, that is all we need for now. Now to actually create the query, we can actually set the shooting entity query equal to get entity query, and then we'll pass in the entity query description right there. So now that we have our entity query set, we can just go ahead and pass this into the schedule parallel. And so now the job will be scheduled. Okay, so we'll come back over to Unity. We'll go to the game controller entity and we'll add the component, and then we need the shot prefab. And then we'll go ahead and drag in the shot prefab right there. So now when we enter play mode, you'll see, we get a couple of errors here. So I'm going to show you kind of what's going on here. Argument exception, the previously scheduled job, shoot weapon job, reads from unknown object weapon type, shoot weapon job safely. You must call job handle.complete on the shoot weapon job before you can deallocate, yada, yada, yada. Okay, so basically what this is telling us is that, some component of some unknown type for whatever reason is being used in another job, and then we're trying to access it in this job. And it wants us to call the dependency.complete. And now we can do this, and this would work just fine. However, this basically means that it's going to force the jobs to completion right then and there, and then it's going to go ahead and schedule those jobs. Now there is a better way to go ahead and do this, and that is by, again, kind of integrating that auto dependency property that I was talking about earlier. So we'll say dependency equals to the new shoot weapon job, and then inside the schedule parallel, we'll put in another argument of the auto dependency here. So basically we're just passing in the dependency and then also setting the dependency back to that auto dependency. So basically in doing that, that's going to tell the job system, what are all the dependencies, and how can it order the jobs and schedule them in such a way so that we don't have any major conflicts. So if we now go ahead and hit the play button, you'll see that we actually do get another error message. And again, this is kind of, I wanted to do this intentionally to show you, some of the common error messages that you'll see and how to handle them. You'll see that this one says the previously scheduled job, shoot weapon job, writes to the Unity.entities entity command buffer. You must call job handle.complete. So again, same thing. We could come over here and we could do a, dependency.complete. However, again, we don't necessarily want to do that. So there is another way to handle these errors. When you do see that one where it, yells at you about the entity command buffer, you can actually go to the ECB system, and then we do a add job handle for producer, and then in here we pass in the auto dependency property. So that basically includes this dependency onto the ECB system. So now the ECB system knows we need to wait for that job to complete before the ECB system plays back its operations. Okay, so now we'll enter play mode, and then we'll see, okay, we finally have a barrage of shots coming at us here, and we can even fire back. If we press the space key, you'll see that I'm firing some shots now. And so now we're able to move around and shoot our weapons, and enemies can shoot at us, and it's starting to turn into a little bit of a game. So it's definitely very exciting stuff. Now, again, I know this job was a little bit more complicated, but I did just kind of want to show you kind of the manual method and give you a little bit of idea about what's happening behind the scenes. Again, I'm sure you can kind of figure out by now how to actually structure this in an iJob entity job if you wanted to. And then actually one thing that I forgot to do, you'll notice that our shots are just kind of going out into the world forever, and I'm not actually destroying them. So real quick, I'm just going to go through how to destroy those shots now after some time. So now we're going to go ahead and create this entity lifetime system. We're going to go back to use a nice, easy iJob entity here. Don't need to worry about that iJob entity batch business anymore. So in our execute function, again, we're going to be basically iterating across anything that has the entity lifetime component, which of course we can just call entity lifetime. And then we're going to want to do a public float for a delta time here. We'll just go ahead and say entity lifetime dot value minus equals delta time. And then so we'll just do a check to see if the entity lifetime dot value is greater than 0. If it is, just go ahead and return out of here. No further actions required at the time. However, if the time has expired, we're going to go ahead and add a destroy entity tag to the entity, and then we can run a system later on to basically clean up anything with the destroy entity tag. So of course, we're going to need an entity command buffer for that. So I'm going to do a public entity command buffer. I'm going to do another parallel writer here. Reason being is because, if we're going to have a lot of these shots in our system, we're going to be running, this across all the shots that are alive in our game. So that means that, ideally we would want to schedule this parallel. So real quick, I'm just going to go ahead and create an empty component data for a destroy entity tag here. Then back on my entity lifetime system, I can do an ECB.add component destroy entity tag. Now, a couple things that we do need the sort key as well as the entity that we're going to be iterating across of. So I'm going to go ahead and inside the parameters of the execute, I'm going to go ahead and do an entity, and we can just call this entity, because really this can be any entity that has that entity lifetime. And we're also going to define an integer for the sort key. Now it's important that this isn't just any integer. We do need to put an attribute before that. And this is going to be the entity in query index attribute. And the entity in query index, this is basically just an index, again, that we can use to sort out our entity command buffers. And so again, we'll just go ahead and pass in the sort key and the entity, and then that will add the destroy entity tag to that entity. Now, of course, we do just need to go ahead and schedule this. This time I'm going to be using the end simulation entity command buffer system, which I can call ECB system. And then I'll show you why in just a sec. As you know, on the on start running, we'll set ECB system equal to world.getExistingSystem end simulation entity command buffer system. In the on update, we'll do a new entity lifetime job. Of course, delta time is going to be our time.delta time. And then the ECB is going to be our ECB system.create command buffer as parallel writer. And we're going to do a schedule parallel. And once again, because we are doing a schedule parallel, we will need to do the ECB system.add job handle for producer, passing in the dependency there. And I almost forgot, I do need to add the ref keyword before the entity lifetime here. Okay, so now when we go ahead and hit play, we'll go ahead and spawn some shots into the world, and we'll take a look at one of these shot prefabs here. And you'll notice that you'll see that because this has been in the world for some time, the entity lifetime is now well below 0 right here. You'll see that it does have the destroy entity tag on it. Okay, so I've just gone ahead and created this destroy entity system right here. A couple things that I should point out is the way that I'm ordering this is that we're updating in the group for the simulation system. We're setting order last equal to Drew. And we also do want to update after the end simulation entity command buffer system has already ran. Again, the reason that we're doing that is because the entity lifetime system, we're going to be adding that tag in the end simulation entity command buffer system. So we do want to destroy our entities after that tag is actually already added to that entity, which happens in that end simulation entity command buffer system. So now, basically after that, we're going to schedule another entity command buffer for the end initialization entity command buffer system. So that means basically towards the beginning of the next frame is when we're actually going to destroy the entity. So you'll see that I've just gone ahead and of course created the ECB system and created the entity command buffer here. Now here I'm going to do an entities.forEach again. Later on, there's going to be a specific reason for the fact that I'm using an entities.forEach here. And so here we can just pass in the entity that we're going to be iterating across of, which here is the entity to destroy. And we can kind of complete this little lambda function here. And then we'll just do an ECB.destroy entity, passing in the entity to destroy. And then we're just going to go ahead and run this on the main thread. Now, basically what this is going to mean is because we're not really doing an entity query, it's basically just going to look for, any single entity and destroy that. Obviously, we don't want that to happen. So we're going to go ahead and do a dot with all parameter. And then of course, we're going to use the destroy entity tag. That means it's going to look for everything with that destroy entity tag, and then it's just going to go ahead and destroy it. So now we'll come back over to Unity and we'll fire off a couple shots, and you'll see that now after a couple seconds, you see that these shots are starting to destroy because they can only live for about 2.5 seconds within the game world before they get automatically destroyed. So that is exactly what we want. this game is starting to become a little bit hectic. Okay, so now that we can interact with our game on a base level here, let's actually turn it into a little bit of a game. So now we're going to go ahead and actually add in some collision detection so we can actually shoot shots at the other ships, and conversely the other ships can shoot shots at us. So anyways, to accomplish this, we're going to be using Unity's DOTS physics system. So first in Unity, we're just going to go ahead and add colliders to everything, and then after that we're going to do our collision detection, and then after that we're going to actually handle those collisions that we detect. So first things first, we'll just go ahead and select our player ship here. Now I'm going to just go ahead and do this on the root, the parent player ship. However, we could create another child object to handle the collisions if we wanted, but I'm just going to go ahead and do it on the parent for now. So the component that we're going to want to go ahead and add is called physics shape, and then you'll see on here basically it's going to go ahead and come up with kind of these default properties, and this is sort of basically a custom authoring component that's going to add all the necessary physics items to our entity. Now there are actually a number of them, and it's just easiest if we just drop this basically authoring component on here. So you see by default it's just going to put a box around this whole guy here. Okay, so you see that I've just gone ahead and reduced the size of the box to basically just kind of go around this wing area. You'll notice if we actually zoom in on this box, you'll see there's kind of a little bit of a bevel on the corners, and that's basically configured by this bevel radius right here. I'm just going to go ahead and leave this as the default. There's actually some performance optimizations that can be made with this bevel right here, so it's best to just go ahead and leave that at the default there. Then I'm actually going to go ahead and add another physics shape here. This time it's going to be a capsule, and this is to just go around sort of the main hull of the ship here. All right, and so that is looking pretty good to me. So now we just kind of have our basic collider here, and then you also just need to make sure to change the collision response from collide to collide raise collision events. So make sure that that is set on all the physics shapes so it properly raises these collision events. And then we'll just go ahead and do something similar to our enemy ship as well. So just on the enemy ship, we'll go ahead and add a physics shape. Okay, wonderful. So we'll go ahead and save those changes there. And then similar kind of thing with our shot, we'll just go ahead and add a new physics shape in here. Instead, we'll just go ahead and change this to a sphere, of course, and you'll see that we'll wrap right around the sphere just as we want it to, and go ahead and save those changes. So you can think of the physics shape authoring similar to like a collider. Now, the other thing that we are going to need is basically the equivalent of a rigid body. And so we can go ahead and add that. You'll see that it is this physics body is the name of the authoring component. And for motion type, we're going to go ahead and actually set this to kinematic. The reason that we're doing that is because we're moving everything through code ourselves, and we don't necessarily want these objects to, bump into each other and have dynamic interactions in this particular game. So then we'll go ahead and add one to the enemy ship as well. Again, change this to kinematic, save the changes, and go ahead and add one to the shot prefab here as well. Kinematic, save the changes. And so just to confirm, we can go ahead and enter play mode and make sure that we can still move around and shoot shots, and the other players can shoot shots at us as well. However, again, there's still no collision detection happening here. All the shots are just going right through all the players. So now that is the next thing that we're going to tackle, is actually doing some collision detection. Okay, so the one extra data component that we're going to need is this shot collision data component. Now this has a public float3 for position as well as a public entity for the hit entity. Now this is basically just going to be a data component that we're going to attach to each of the shots, and then when a collision is actually detected, we're going to populate this information about where the position of that hit has taken place. So later on in the video, when we want to add like explosions and some effects, we know the position of it and we can spawn them at that position. Also, we'll have a reference to the hit entity so that later on in another system, we can actually apply damage to that hit entity. So we just kind of want to keep a reference of, where the collision is taking place and who we are actually colliding with. So of course, we can just go over to our shot authoring, go ahead and do a dstmanager.add component, passing in the shot collision right here. Of course, going to be adding that to the shot entity. So I've created a new system here called the detect shot collision system. Now this system is only to detect shots and record the data values associated with them. And we're going to have multiple systems later on to do things like apply damage, spawn particle effects, and so on. Now you notice that I do have a number of ordering attributes up here. I am updating this in the fixed step simulation group. This is one of those built-in groups, and this one is specifically related to the the fixed step simulation, which the DOTS physics system runs inside this fixed step simulation system group, which, as you can guess, runs on a fixed time step rather than, once per frame like most of the other system groups do. Now, it's really important that when we're doing any collision detection, we need to update it after the export physics world, but before the end frame physics system. Okay, so now we're actually going to go ahead and create another job outside of the system base, and this is going to be a new job type. This is going to be one that's built into the Unity physics system. So we're going to go ahead and define a public struct, no partial struct. So I'll go ahead and call this the detect shot collision job, which implements the iCollision events job. It's going to detect any collisions within our game. There's a similar one for triggers that does basically the same thing here. And as you can imagine, there's just a public void called execute, which takes in a collision event. Now, from the collision event, we can get some certain parameters from the actual collision event. So firstly, we can get a reference to both the entities that are involved in the collision. So in this case, we'll just go ahead and call these entity A, because if we go to the collision event, there's entity A. And then we can also get the entity B, which is our collision event dot entity B. Now at this point, we don't know which entity is which. Entity A could be a shot and entity B could be a ship, or it could be the other way around, or these both could be ships, or these both could be shots. So now, how do we actually tell which one is which? Well, of course, we can do that by using a component data from entity. So here we're first going to just go ahead and define a public component data from entity, and this is going to be of type shot collision, which we just call shot collision lookup. Now we do this because we know that our shots are going to have this shot collision, and then later on, this is how we're actually going to be writing that data to the particular shot entities. Here we can say var is entity A shot equals shot collision lookup that has components, and we can pass in entity A, and then we'll do a similar thing for entity B. Now at this point, what we'd like to confirm is that between entity A and entity B, one and only one of those entities should be a shot. So again, basically we don't want to detect any collisions between two shots hitting each other or two ships hitting each other, but we would like to detect collisions between one ship and one shot. So what we can do is we could just do an exclusive or comparison, and then basically use the exclamation mark to invert that. So basically, if entity A and entity B are both shots, then we'll go ahead and return out of here. And if neither entity A or entity B are shots, again, we'll return out of the function. Now, the next thing that we need to do here is to check the team ID between the two entities that were both hit. The reason that we do this is because we don't want to have any type of friendly firing. We want only ships of opposing teams to be able to shoot at each other. So of course, we're going to go ahead and need a component data from entity. This one can be read only. So first, we'll just go ahead and confirm that both entity A and entity B have the team ID component. And if entity A or entity B does not have that component, we'll just go ahead and return out of there, because then that basically means that we're colliding with something that doesn't have a team ID, which in this case, we don't necessarily want to support. Next up, we'll just grab the team ID for entity A and entity B, just do a quick comparison on them. And again, if these are equal, we'll just go ahead and return out of the function. Again, we only want things of opposing team IDs to be able to collide with each other. And at this point, we can just go ahead and do a quick determination of which one is the shot entity and which one is the entity being hit, just by using the ternary operator there. So at this point, we can go ahead and create a new shot collision, set this equal to a new shot collision. And then for the values, of course, we can go ahead and set the hit entity equal to hit entity. That one is easy. The position, this one is a little bit more involved, because we'll actually have to go to the collision event, and then we can do a dot calculate details. Now inside here, you'll see that it wants a reference to the physics world. So we'll have to actually get that outside of here. So we can do a public physics world called physics world. And then inside the calculate details, we can do a ref to the physics world. After that, we'll do a dot, and then we can do, I prefer the average contact point position. That basically means that, if there are a number of contact points for this collision event, it's just going to take the average of those. So I feel like that gives us kind of the best result if we want to know, the specific spot that a collision happened, and we want to, maybe spawn some particle effects from that location. So then after that, we can just go ahead and assign that new shot collision to our shot entity. And we can do that just by using the existing shot collision lookup that we already have. Again, we did not mark this one as read only, so we can just go ahead and set the shot collision lookup at shot entity equal to a new shot collision. Okay, so now we have the job defined. Now we actually need to go ahead and schedule the job, and we will need to set this to the auto dependency. So we can just do a new detect shot collision job. In here for the parameters, we'll set the shot collision lookup equal to a get component data from entity, course of type shot collision. Next up is going to be and I set that as private, so I'll go ahead and change that over to public like it should be. The team ID lookup is going to be a get CDFE for team ID. Again, this is a read-only one, so we'll go ahead and pass in true there. And then finally, for the physics world, we need to actually get this off of a particular system here. So outside here, we'll go ahead and define a private build physics world, which we can just call the build physics world. And we actually do need to get a reference to that in the on start running. So this is basically just a system. So we can set build physics world equal to world.get existing system, course type of build physics world. And then for physics world in here, we can just do a build physics world physics world. Now we can go ahead and schedule this. You see there's actually not an option for schedule parallel, so we actually just have to do the schedule. So we can go ahead and schedule that. You'll see that it wants basically an eye simulation in here. So the eye simulation, we can get that off of the step physics world, which is just kind of another physics world in here. So of course we can just do a private step physics world. Again, go ahead and grab a reference to this in the on start running. So here we'll do step physics world dot simulation. That's how we get that. And then we also do need to pass in the auto dependency property there. So that is how we actually schedule that collision job. Okay, so now we can come back over to Unity and test it out, and you'll see, well, we got an error here. So it says invalid operation, the previously scheduled job physics world exporter export dynamic bodies job reads from native array of physics motion data, yada yada. Trying to schedule a new job, writes the same collection, yada yada. To guarantee safety, you must include physics world exporter as a dependency of the newly scheduled job. So basically, when you do come across this error, the fix that you need to do, you can just do this right in the on start running. So we'll just go ahead and say this.register physics runtime system read write. So now if we come back over to Unity and hit play, you'll see that now we do no longer get any error messages in the console. And now we have basically all these shots shooting out at us. And again, we don't really see anything happening because these are all basically kinematic bodies. However, if we go over into our dots hierarchy, let me go ahead and pause this. Let's go ahead and look through a couple of these shot prefabs and take a look at the shot collision. And you'll see that, look, we found one right here where it has the hit entity set to the player ship, and it also shows the exact XYZ coordinates of where that collision actually took place. We can find another one here, and this is the position as well as the hit entity. So that means that we are all good so far. We are properly detecting collisions exactly as we would want it to. Okay, so now the next thing that we're going to do is actually deal damage when these shots hit the different ships in our game. So just go ahead and create a new data component for hit points, which is a public int called value. And let's go ahead and add this to the ship authoring. The reason that we're going to be wanting to do it on the ship authoring is because both player and enemy ships are going to need this hit points data. So real quick, we'll just come back to Unity and we'll go ahead and set these player hit points to a value of 30. And for the enemies, let's just do a value of 2, just so they're nice and squishy. Okay, so I'm just going to go ahead and create a new damage on collision system with a damage on collision job that implements iJob entity. Now in this job, we're going to look for anything with a shot collision. And if there is actually an entity that is part of the hit entity, then we're actually going to apply damage to that hit entity. So for now, we only need read-only access to this shot collision here. So we can just save off a local variable for the hit entity, and we'll set this equal to the shot collision.hit entity. Now we want to make sure that this entity actually does have a hit point. So what we're going to go ahead and do is, of course, do a component data from entity of type hit points called hit point lookup. This one we actually are going to be writing to, because we're actually going to be writing the new hit points component to the entity that we hit. So we'll just go ahead and return out of here if the entity doesn't actually have a hit point component. Otherwise, we're just going to go ahead and grab the other entity's hit points. We're just going to go ahead and decrement it by a value of 1, and then we do need to set it back to the component data from entity. Again, right here we are writing to it, so we cannot declare this as read only. And then finally what we'll go ahead and do is we'll just do a quick check to see if the other entity hit points dot value is less than or equal to 0. If it is, let's go ahead and add that destroyed entity tag to it. So of course we'll want to go ahead and do an entity command buffer. I'm going to go ahead and do a parallel writer here because I do want to multi-thread this, and I will need that sort key up in the execute function here, which will allow me to go ahead and do sort key hit entity. So that means basically if the other entity has a hit points value of less than 0, we'll just go ahead and add the destroyed entity tag to it. Now, before we move on, this actually is not complete. There are a couple things that we do need to clean up. Because we are going to be writing to this component data from entity from a parallel job, you'll remember that we do need to add an attribute, which is going to be the native disable parallel for restriction, and that's going to allow us to write to this parallelly. Now, one thing that I should point out in this case, this is basically going to be a little bit of a limitation of our application, where if we were to run into a situation where, say, 2 shots hit the entity at one time, it's actually only going to decrement the value by 1, because if, say, we're on multiple threads trying to decrement the value by 1, it's actually just going to decrement those values to the same value essentially. Because when this data is being worked on in different threads, we can't guarantee that the result of that has been completed from one thread before we're writing to it in another thread. So, just be aware that there may be some strange, very strange edge cases like that. And so that's why, adding attributes like this, it's basically going to be at our own risk. It's not just to clean up some error messages. There are a reason that those error messages do exist in the console. And I should mention that there are actually better ways that we can support applying damage so that it actually, supports this, parallel adding of damage exactly as we would expect it to. But again, in this simple context, this works well for this type of game. And the other thing that I'm actually going to add in here is a change filter, and we can add a change filter to this iJob entity with an attribute, which is the with change filter. And then in here, we can basically pass in the type of component that we want to basically trigger this change filter on. So basically what this means is we don't want this job to be running, every single frame 100% all the time. We really want this to only change when we actually hit something. So this basically means that, when this shot collision is actually opened up for change, then we'll actually go ahead and run this job. Now, if shots are just kind of going out into space and they're not actually hitting anything, then this job actually does not run. So that's kind of the nice little optimization of the change filter. Okay, so of course, I'll just go ahead and schedule the job. Again, doing a schedule parallel. Of course, we're doing a get component data from entity for that hit point lookup. For the entity command buffer, again, I'm doing an ECB system, which in this case is the end simulation entity command buffer system. If you'll remember, this is the one that runs right before that destroy entity system. Of course, just go ahead and grab that system, create the command buffer as a parallel writer, and then we do have to do the add job handle for producer, passing in the auto dependency property. Okay, so we'll come back over to Unity and we'll go ahead and enter play mode, and you'll see that we can, kind of move the ship around and turn and everything like that. You remember we started off with a value of 30 hit points for our player. So now we'll just go ahead and come over here, and you'll see that pretty much right away we just got completely erased by those other entities. That was definitely not 30 shots that took us all the way down to 0. Now, what is the reason for that? Well, the reason for that is because when we actually schedule this damage on collision job, this is basically going to be applying damage every single frame for, every time that one of these shot collisions exist in the world. Now, basically in this case, what we want to happen is, just a shot who hits a ship and it just gets destroyed immediately. So we're going to go ahead and just do a quick little system to destroy those shots immediately upon collision. All right, so this is a pretty standard system at this point, so I'm not going to go through completely everything here. Basically the job here, this destroy on collision job, you'll see that it operates on everything with the shot collision. Same thing as before, we're also going to do a change filter of the shot collision, so we're not running this all the time. And then basically if the shot collision.hit entity is equal to entity.null, meaning has not hit anything yet, just go ahead and return out of this. Otherwise, if we have hit something, just go ahead and add the destroy entity tag in the entity command buffer. And then when we actually schedule it, again, we're just using the end simulation entity command buffer system, creating a command buffer as a parallel writer, and scheduling the job parallelly. And do make sure that you add in the ECB system.addJobHandle for producer, passing in the auto dependency. Okay, so now we'll enter play mode, and you'll see that we can take many more shots. Looks like we do get up to probably about 30 before we actually get destroyed. And if we go over to our dots hierarchy, we can select our player ship and then locate our hit points, which has a value of 30. You'll see that it's just going down by basically one at a time until we start getting hit by, multiple ships, of course. However, you'll notice a couple of problems here immediately. Even though the player ship has been destroyed, we can't actually see it in the hierarchy anymore. We still can see the renderer as well as the firing point here. And we're getting some warnings in the console about, the singleton and everything like that. So we're just going to go ahead and take a quick detour and clean up a couple of those errors. Now, the first system we're going to go to is the destroy entity system. Now, basically what's happening in this one is when we say destroy this entity, it doesn't actually destroy any of the child entities. Now, if you're making a real game, maybe you want to do some filtering to see, do you always want to destroy all the child entities, or are there some situations where, you want to preserve some of those as well. However, in this case, it doesn't really matter. We can just go ahead and destroy all the child entities. Now, the child entities are stored in what is known as a dynamic buffer. Now, a dynamic buffer, we're going to be actually implementing one of these on our own a little bit later, but it's basically a way that you can store component data on an entity in an array-like fashion. So typically you can't have multiple of the same component types on one entity. However, the dynamic buffer will basically allow you to have a collection of multiple component data types on that entity. So here again, we're using an entities.forEach. Now, in order to check to see if we have that basically child buffer, the way that we do that is we actually first need to get a reference to the entity manager. So we can say var entity manager is equal to entity manager. Again, remember, because this is an entities.forEach, we need to capture these variables outside of the entities.forEach. So then in here, we can say if entity manager dot has component with the type brackets child, and we want the unity dot transforms child, passing in the entity to destroy. Let's go ahead and get that dynamic buffer. We'll call this the child buffer. Set this equal to get buffer type of child, of course off the entity to destroy, and then we'll go ahead and do a for each across the child buffer. So every child in the child buffer, go ahead and do an ECB.destroy entity child.value. So again, basically this is just going to check to see if we have any children. If we do, we're going to go ahead and get that child buffer. We'll just go ahead and iterate through that child buffer and destroy all the child entities. So now we will come over to Unity, enter play mode. We will kind of move around, wait for all the shots to destroy us here. And then any moment now, you'll see that now that renderer no longer exists. Now the other thing that we're getting, let's take a look at what this error says. This says invalid operation exception, set singleton on our player move input requires that exactly 1 exists, but there are 0. And if we look around, we can see that it's in our get player input system on line 21. And so this is basically saying, we're trying to set this singleton for this player move input, but there's no entity to actually set it to. So there's a kind of an easy fix that we can do to this inside the onStart running. We'll go ahead and do a require singleton for update. Let's just go ahead and pass in the player ship tag here. And that basically just means that this onUpdate function is only going to run if a singleton entity with this player ship tag component exists in our world. Now later on, we're going to come back and change this to something different, but for now this should suffice. So this basically just runs a check to see, does that player exist in the world? If it does, let's actually get the input from the player. So now we'll go ahead and enter play mode, wait for some enemy ships to come by and just absolutely destroy us here. And then, so yep, now we're destroyed, and you'll see that we do no longer have any error messages in the console. Perfect. And actually, to confirm around, we've only just been getting destroyed. Let's make sure that we can actually destroy the other ships. And it looks like these do just take 2 shots. So we'll go ahead and shoot these a couple times. And you'll see that they are disappearing as we're shooting them with 2 shots, just as we would expect. So, you know, the game is starting to come together. We can kind of play around with it. There's a little bit of a challenge here. We can just start destroying the other enemies and all that. And there is, you know, a little bit of a fail state. If we're, you know, not careful and we get hit by 30 shots, we do get destroyed. So no bueno. Okay, so what would be a game like this without keeping track of our player score? So basically what we're going to do here is each of these ships in the world is going to have basically a score value. And then when we destroy one of those, that's going to add to, you know, the player's kind of points value here. And then right now we're actually not going to be displaying anything on the screen. We're just going to be keeping track of all that stuff internally. But then when we do go to the polishing phase, you know, that's going to be one of the first things that we do is display the actual score to the player. Okay, so to start off, I'm going to go ahead and create 3 new data components. The first one is going to be the ship score points. This is going to keep track of basically the player's score. The next one is the points given on destroy. So this is basically going to be, you know, what is the point value of one of these ships that we're destroying. Of course, these are just both integer values. Finally, the last one is a different data component type. You'll see that it implements iBuffer element data, which I've called the score buffer element. Now, this is the basics of how we can actually define a dynamic buffer. Now, a dynamic buffer, again, it is a way that we can have array-like component data on our objects. And then you'll notice that I have this attribute up here that says this internal buffer capacity, and I did pass in a value of 1. Now, the internal buffer capacity, this basically specifies how many elements of this dynamic buffer can we fit inside the chunk. Now, if you'll recall, the chunks are those 16 kilobyte blocks of memory that actually store the data associated with entities. And if we have a collection that could be of a potentially variable length, then we don't know how much memory to allocate inside these chunks of a fixed size in order to properly store the data. Now, this internal buffer capacity, that basically specifies, you know, again, how many elements of this dynamic buffer should live in the chunk. So the higher the number, the more of these elements that we will be able to store in the chunk for fast access. However, that means that we won't be able to fit as many entities in the chunk because it's going to be taking up more memory. So it is a little bit of a performance trade-off. Now in this case, I've chosen to just pass in a value of 1 because I know in most cases, we're only going to be having only 1 element in this array. If for some reason in the off case where we had maybe 2 or 3 elements in this dynamic buffer, then what's actually going to happen is all that data is going to be moved outside of the chunk, and then we're basically just going to have a pointer to that. So it does end up adding a little bit of a random access there. So that is kind of the performance trade-off that you have here. But again, in this case, I know that most likely we're just going to have 1 element in the score buffer, and it is kind of an edge case where we might have 2 or 3. So let's go ahead and add these to our ship authoring here. So I'll add a field for points given on destroy, and then down here we can do a add component data onto the new ship entity for a new points given on destroy, and set the value equal to points given on destroy. Then at the end here, we'll just go ahead and do an regular add component for the ship score points onto the new ship entity. Again, we can just, you know, add that on. We don't need to initialize it to anything because we're going to be increasing points as we go. And then finally, we'll do a DST manager.add buffer. And then here we can just pass in the type of the buffer, which again is going to be that score buffer element onto the new ship entity. And I should note that the actual type of this dynamic buffer is a type of dynamic buffer score buffer element, just like that. And then the score buffer element is basically going to be 1 element of that dynamic buffer. So let's go ahead and come back over to Unity. We'll set the points given on destroy for the enemies to a value of 10. And we don't really need to set anything for the player because we don't really care that the enemies are racking up points on us. And then one last data component that we do need to add, this is the ship entity reference. This is going to live on the shot, and it's basically just going to keep track of which ship actually shot the shot, so that when we do say destroy an entity, then we know who to apply the points to. Okay, so we'll start off by coming back to this crazy shoot weapon job. Remember this iJob entity batch that we did. And what we're going to want to do is go ahead and first just add that ship entity reference to that shot when we spawn it. Now, first we need a way to actually reference the entity that we're iterating across. And again, because this is the iJob entity batch, there's no easy way we can do that where we can't just like add an entity into this parameter here. We have to use what is known as an entity type handle. Of course, this is just going to be a read-only public entity type handle, and we can just call this the entity type handle. Now, basically from this, we can do kind of a get native array similar to this. And then we'll just pass in the index of the entity that we want to iterate across, and that will return us the actual entity that we're iterating on. So at the very end here, right after we're adding the team IDs to the new shot, we'll just go ahead and say var ship entity is equal to batch in chunk dot get native array. Here we pass in the entity type handle, and then we can just do an index to I to actually give us the entity that we're iterating across. Because if you'll remember that this is inside a for loop here, then we can finally just do an ECB dot add component. Again, we do need to put in the batch index for the sort key. We're going to be adding this to the new shot, and this is going to be a new ship entity reference, and the value will be set to the ship entity. Perfect. So that basically means that all new shots spawned into the world will have a reference to the original entity that fired them. And then we'll just need to remember to go ahead and assign this entity type handle. So I can go ahead and do that after this. So we'll set the entity type handle equal to a get entity type handle. And this one actually does not take in any parameters here, so we can leave that as is. Okay, so now we'll come back to the damage on collision system. We're going to go ahead and add in another component in our execute here. This is going to be just a read-only into the ship entity reference, which you can just call the ship entity reference. Sure, that's fine. Now, what we want to do is we want to make sure that that ship entity actually does have a score buffer on it, so we can actually, add to that score buffer to increase the score of that ship. So instead of using a component data from entity, we're actually going to use a buffer from entity. The type of this is going to be the score buffer element. So we can call this the score buffer lookup. Do want to make sure that this is a public this time. So down here, when the other entity has actually been destroyed, and after we've gone ahead and added the destroy entity tag to it, let's go ahead and check our score buffer lookup. So we'll say if not score buffer lookup dot has component, and here's where we want to pass in our ship entity reference dot value, and then go ahead and return if that's the case. So basically we're going to say, which is the entity that is actually shooting this shot. Does it have that score buffer element? If it does not, go ahead and return. Now we need to see, how much score should be added to this. And of course we can do that with a read-only component data from entity. And this is the points given on destroy. So we can get a score to add is equal to the points given lookup at position hit entity, because remember we want to get how many points the hit entity gives when it's destroyed, dot value. So that should just be the integer value there. So let's just go ahead and create a new score element equal to a new score buffer element. And for the value, we'll set this equal to score to add. Now basically we just need a way to essentially add this element to the dynamic buffer on our ship entity. So luckily the entity command buffer has a very handy method built in called the append to buffer. Of course we will need to pass in our sort key here, and we do want to add this to the ship entity reference dot value, and this will be the new score element that we just created. So now this is basically just going to go ahead and apply this to this score dynamic buffer. Okay, and then before we head back to Unity, we just need to make sure that we are setting these new values here. So after the entity command buffer, we'll set the score buffer lookup equal to a get buffer from entity. Of course, this is going to be the score buffer element, and it is read only. So we'll go ahead and pass in true there. And then the points given lookup is equal to a get component data from entity points given on destroy. Again, pass in true for read only. So we will enter play mode, and let's go ahead and let's destroy a couple of these enemy ships. Okay, so there's one down. And wait for a couple more to show up. Okay, boom, there's two down. and 3 down. Okay, let's go ahead and pause this, and we'll come over to the dots hierarchy, go to the player ship, and take a look at a couple things here. So you'll notice the ship score points, that value is still set to 0 because we aren't actually adding any points to the ship yet. What we are doing is adding elements to this score buffer. So you see that we destroyed 3 ships. You see that this buffer is a size of 3. And if we actually expand this, we can see all the individual elements of this buffer. And you'll see that each of these does have a value of 10 because each of those ships that we destroyed has a value of 10. So you know what that means. We're going to go ahead and create another system. This will be the add score system. And here we'll do another iJob entity for the add score job. You see that I am burst compiling it and do have the with change filter score buffer element. So we're only going to run this when actually things are added to that score buffer. So inside the execute, we're going to go ahead and get read-only access to the dynamic buffer of type score buffer element, which we can just call the score buffer. And we'll also need read and write access to the ship score points, so we can actually go ahead and assign points to that. Now, what we're just going to want to do is just do a quick empty check here to see if the score buffer is empty. If it is, return. If not, we'll go through each of the score buffer elements inside the score buffer, and we can do a ship score points dot value plus equals the score buffer element dot value. So of course that's just going to go ahead and add up everything in the buffer and increment the ship score points now. And then finally we'll just go ahead and do a score buffer dot clear just to clear out that buffer because we don't want the points to add up every single frame. We can just do a new add score job dot schedule just like that. Okay, so now go ahead and enter play mode. We will move around and wait for some enemies to show up. And let's go ahead and finish off a couple of these enemies here. Looks like we have a few coming from this side. So we'll go ahead and destroy 1, 2, and 3 right there. We'll go ahead and pause it. Come over to our player ship. You'll see that our score buffer element, the dynamic buffer, is now set to 0. There's nothing in that. And if we do go up to the ship score points, we do see that we have a value of 30, just as we would expect. So now the player score is incrementing exactly as we would. So at this point, now we have a pretty functioning game. You know, we're able to shoot other enemies. Enemies can shoot us. We can actually, have a score that increments. And so this is basically, everything is done on the ECS side up to this point. We haven't integrated pretty much anything with any mono behaviors, aside from doing things like authoring components and the like. However, as we move on into the polish phase, we're actually going to need to integrate with a lot of the traditional Unity stuff that you may be familiar with, such as Cinemachine, the Unity UI, adding things like particle effects and sound effects. So we're going to be doing all of that in this next upcoming section here. So at this point, this may be a good point for another break to just kind of, step back, think about what you had learned a little bit, just kind of go over the code, make sure you understand everything, and then, come back to this project with fresh eyes when you're ready to make this project beautiful and into an actual, functional game that you could hand to somebody and they can understand how to actually play because you're actually getting feedback from the game now. Okay, so at this point, we now have a playable game. Now we're going to go ahead and step into the polish phase where we're going to start adding things like UI to give our player a little bit more information, as well as just add some visual and audio effects just to make it feel a little bit more alive. And then at the end of this section, I am going to be showing you how to create a build of this application that you can package up and share with all your friends. And during this section, we're going to be integrating a lot of features that you'll find in the Unity game engine by default into this project made with Unity's entity component system. So we're going to be using things like game objects and other types of mono behaviors and being able to, use the existing tools that are built into the Unity editor to make some cool things. But then we're going to go ahead and integrate those with this ECS project that we've created. And I should also mention that I'm not going to be going super into detail on all of the things that are considered kind of more general Unity knowledge. I'm mostly just going to be focusing on how we actually integrate those with Unity ECS, but I still will show you everything that you need in order to get the end result that we're going for. So the first thing that we are going to integrate is Cinemachine. So we're going to use Cinemachine to basically follow around our player so we can basically move throughout our world. So just to give you kind of like a high level overview about what the theory is. So if you are familiar with Cinemachine, you'll know that there's a way that where we can basically target a transform in the world. This is just a regular Unity game object transform, and it can basically look at and follow that transform. Now we're going to be doing that same thing here. Unfortunately, when we basically convert our spaceship to an entity, there's no longer going to be any translations on the game object side that our Cinemachine camera can follow. So what we're going to end up having to do is basically create an empty transform, and that's going to mirror the position of our player ship, and then we can have our Cinemachine virtual camera target that empty transform within the world. So in the regular game object hierarchy here, we'll just go ahead and create an empty game object, and we can just call this the camera target. And it doesn't really matter where this is in the world, but let's just go ahead and put it at 0, 0, 0. And we're going to leave the convert to entity box unchecked because again, we want to leave this as a game object. Next thing we're going to do is go ahead and create a Cinemachine virtual camera, and we can just leave that default name as is. So I'm just going to go ahead and set the transform values to the same thing that we had for the main camera. And then for follow, it's going to have us put in a transform here. So we'll just go ahead and drag in our camera target transform there, and we can just go ahead and leave the look at transform as empty because this is basically going to be a top-down view. We don't need our camera to be looking around or anything. Then under body, we're going to have the mode set to transposer. The binding mode is going to be lock to target with world up, and the follow offset is going to be set to 0, 10, 0, and then all the rest can be left as default here. So now when we enter play mode, still nothing is happening because we're not actually mirroring that transform position. You see that if we do take our camera target and we start to move it around, you see that our camera does start to move around in the game view there. So now basically we need to get this camera target to mirror the position of our player ship. Luckily, Unity ECS has a built-in way that we can do this, that we can hook into, and it's super easy to get set up. Okay, so I've gone ahead and created a new mono behavior script. This is called the managed object container. You'll see that I'm using the singleton pattern by doing a public static managed container called instance, and then just go ahead and setting that in the awake function here. And then basically we're going to be using this singleton to grab the particular managed objects that we need and go ahead and assign those as needed on the ECS side. So I'm going to go ahead and create a serialized field for the camera target, which is going to be of type transform, and that's just so we can set it right in the editor. And then I'll go ahead and create a public transform property, which will just go ahead and return that camera target, so we can actually get that camera target from other scripts outside of this one. Okay, so we'll come back to Unity. We'll go ahead and create a new empty game object, and this is going to be called the game controller go for game controller game object. We can just kind of put that right under the game controller entity there. And then on here, I'll just go ahead and add that managed object container on there. And then we can just go ahead and drag in our camera target right there. Okay, so now I'm going to go ahead and create a system. This is going to be the initialize managed objects system. And you'll see that it is updating in the initialization system group. This is another of those built-in groups. And this is kind of the first group that happens in the player loop, which happens before the simulation system group. So anyways, this initialized managed object system is basically going to look at any of these objects that are on that mono behavior singleton that we just created. And then we're going to go ahead and do whatever is necessary to make a link over to the ECS side. Now, again, this is only an initialization system, so we only want this to run one time. We don't want this to continually update. So what we're going to do is just go ahead and set the enabled property to false. And then so that means that this system is basically only going to run this update loop one single time. And we're including all this code in the update loop so we can ensure that all the on start runnings and start methods and everything like that have already completed before we go ahead and actually do the work that we need to do in here. So then at this point, we're going to go ahead and add in the functionality that's needed to copy the position of the player ship over to our camera target. Like I mentioned, that there is something built into Unity that allows us to do this. Basically, what we're going to do is add a tag component to our player, which is the copy transform to game object. Just be aware that there's also a copy transform from game object if you want the game object side to drive anything on the entity side. But we'll be using this copy transform to game object, which is just a regular empty data component, so it's a tag. And then we'll also add the transform component of the camera target to our player ship entity. Now just remember that the camera ship target is going to be just a regular Unity game object transform. And then once both of those things are on the player ship, Unity will take care of the rest. So whenever we move our player entity around, Unity is basically going to move the translation and rotation of that camera target to match the player ship. So first thing we're going to do is just go ahead and get a reference to the player entity here. And we can do this by doing a get singleton entity. And for the type, we'll go ahead and do the player ship tag. And then we're going to go ahead and use the entity manager to do an add component. And this will be the type of copy transform to game object. And then inside here, we just need to pass in the entity that we want, which is the player entity. Now, again, we do need to just go ahead and add that transform component to the player entity. So first we're going to go ahead and get a reference to that. And so again, we can just use our singleton by doing a managed object container.instance.camera target, and that will just go ahead and return that transform that we need. And then now we can do an entity manager.add component object. First thing it's going to want is the entity, which again is just the player entity. And then now we can just pass in our camera target just like that. So we do have to do this add component object because you'll remember that this camera target is just a regular Unity mono behavior transform, which is not a blittable data type, which is not, compatible with the burst compiler and everything like that. So basically what's actually going to happen is we're going to add essentially a reference to our player, which references that camera target transform. And then Unity has a built-in system that's just going to go ahead and take the translation and rotation of the player and then go ahead and copy that over to the camera target. So we can come back over to Unity and enter play mode, and now we can move around and you'll see that the camera is now following us as we're moving through space here. So this is great. This is exactly what we want. Now we can, kind of move around, fly around and explore this little world that we've built out a little bit more. But let's go ahead and make this a little bit more realistic. Right now you'll see that, the background is maybe a little bit unnatural feeling just because we have these asteroids that are a little bit more close, and then we have the kind of further layer back, which are the stars, and everything is basically just all flat looking. So next thing we're going to go ahead and do is add a little bit of parallax to this background, the stars layer here, just so it looks a little bit more real. Okay, so I'll just go ahead and create a new mono behavior. This is the parallax controller here. This is basically just going to, apply to any of those background image layers. And then it's going to just expose one field here, which is going to be the scroll factor. And the scroll factor is just kind of, a factor that we will multiply by to determine, how much the background should be moving by. And you'll see that I do have a reference to that same camera target. And then in start, we're just going to be setting it the same way that we do in our system by just going to the managed object container instance. And we do just want to get a reference to the start position of this whatever object it is, just so we can properly calculate the offset in the update method here. Okay, so we'll just go to our 4-star backgrounds that we have right here. Go ahead and add a component, which is going to be the parallax controller. And I'll just use this scroll factor of 0.25. Now when we enter play mode, everything should basically work. You'll see that the background now has a little bit of a parallax effect, just so it looks, a little bit more kind of realistic, like we actually are flying through space. So again, that's pretty much all on the game object side. But again, we are still using that same, camera target that is being copied over from our player ship entity. Okay, so next up, we're going to start giving our player a little bit more information about what is going on in the game. So we're going to give them an indication of their health just by using a regular Unity UI slider. And we're also going to be using a Text Mesh Pro UI element to display the player's score onto the screen. Okay, so I've just gone ahead and created a simple little HUD UI. You'll see that in the upper right, we do have this score counter, which is a Text Mesh Pro object. And then down in the lower center of the screen, we do have this player health slider. And then in some ways, sort of similar to what we did with the camera target, we're actually just going to add these managed objects as elements of our player ship. Then we create some systems of our own to update the data values of these. So again, it's going to be a little bit similar to what we did with the camera target. However, this time we actually are creating our own system to update the things on the managed game object side. So we'll start on our managed object container. We'll create a new serialized field of type slider, which is the Unity engine.ui, and we'll call this our player health slider. And then we'll do another serialized field for the TextMesh Pro UGUI. This will be called the player score text. And then of course, we'll just go ahead and set up some public properties so we can get the player health slider as well as the player score text. So we'll come over to Unity, we'll go ahead and select our game controller game object, and then we'll just go ahead and set the player health slider to our player health slider that I've created here. And then I'll go ahead and drag over the player score text as well. Next up, we'll come to our initialize managed objects system, and then we're going to go ahead and actually initialize these values here. So let's first just get the player health slider from the managed object container, and we're going to go ahead and set the player health slider's max value equal to get component of type hit points off of our player entity, and then we'll just have to do a dot value to return the actual value. So again, we did get this player entity from earlier using the get singleton entity. And then now we can use a get component, which is the system-based get component. So we can actually get a Unity ECS data component of type hit points off our player entity. And then we actually want the value of that. So now we can set our max value of our player health slider. Then we can also do a player health slider dot value equals player health slider dot max value, just so it's at the full value right there. And then lastly, we're going to do another of these entity manager dot add component object to our player entity of our player health slider. So again, basically what this is going to allow us to do is now in a system that we create, we will now be able to access this player health slider and then set it to the appropriate value. And then real quick, we might as well just go ahead and set up the player score text as well. So we'll actually set the text of it equal to just a default 000 like that. And again, we can just go ahead and add the player score text as a component object there. Okay, so you'll see that I've created a new system here, which is the display player health system, and it's going to update in the presentation system group. So this is kind of the third system group that happens after the simulation system group. So this is kind of the one towards the end of the player loop here. And then of course I've created an iJob entity for the display player health job. Now you'll note that I do not have the burst compile attribute above this. This is because we are using managed data types, so we're not allowed to use the burst compiler here. So now down in the parameters of our execute method, let's go ahead and define our query here. So first we're going to look for anything with the slider, which we can call the player health slider. Again, we did that add component object. So this is basically going to be considered a data component. Even though it is a reference type, we still can't assign it to the entity. Then also we're going to need to look at our player's ship's hit points. You can just do that by doing an in hit points called hit points. And in here, all we really do is just do player health slider dot value is equal to hit points dot value. And then just to make this a little bit more efficient, so this isn't running all the time, we can do a with change filter type of hit points. So it's only going to run when the hit points value is open for change. And then to schedule the job, all we do is just do a new display player health job dot run. And we do need to do a dot run. We cannot schedule this on a worker thread. We must do a dot run to run this on the main thread. Okay, so I'm going to go ahead and enter play mode. So first thing you'll notice, I'm actually just going to go ahead and pause this. First thing you'll notice is that the player health slider has filled up to the max value. And if we actually go ahead and select the player health slider here, you'll see that the maximum value is now that value of 30 because our player does have 30 hit points available to us. And you'll see the value is also set to 30. Then if we were to go over to the dots hierarchy and select our player ship, you'll see that down towards the bottom, we do have these managed objects showing up. So you see that the player slider, we also do have the TextMesh Pro UGUI for the player score text, as well as the camera target. Now you notice that the icon of these is a little bit different. It kind of has this little bit of a puzzle piece, but with these curly braces on it, that basically indicates that this is a reference type. So it's not something that's say stored in the chunk, but we do have to reference outside of the chunk to access that. And now if we just go ahead and resume the game, you'll see that now as we start getting hit by these enemies, the player's health slider starts going down, down, down. and then all the way once it reaches 0, then our player actually gets destroyed there. So the player health is accurate. Now let's go ahead and add the player score text in. Okay, so now I've created a new system, which is the display player score system, and this one is basically the same as setting the player slider, but I'm going to show you a different way. We're going to do this with an entities.forEach instead. So we'll do an entities.forEach. Again, we kind of do the double parentheses here. So in our query, we're going to do a TextMesh Pro UGY. This, of course, is going to be our player score text. And we're also going to want to read from the ship score points, and we'll go ahead and complete out this lambda function here. And then so again, we do need to run this without burst on the main thread. So the way we do that is after the end here, we just do a dot without burst dot run. And then in here we can set our player score text dot text equal to, then we'll use the string interpolation here just by doing a little $, quotation marks, we'll say score. In here we'll do the ship score points dot value, and then the format we want is 000, comma 000, just like that. And again, we do want to make this one run a little bit more efficiently, so let's go ahead and do a dot with change filter type of ship score points. So we'll come back over to Unity, go ahead and enter play mode here, and then now we'll wait for some enemy ships to come by, and let's go ahead and shoot these guys a couple times, and you'll see that now our player score counter is starting to increment. So if we hit these guys, you see that now we're up to 30 points here. So now it's, remember earlier before we were just calculating the score, but we weren't actually displaying it to the player. At this point, we're just kind of hooking into that, player ship score that we're already, we're keeping track of, and now we're just displaying it out to the player. So that is looking wondrous. Okay, so next up, we're going to continue adding some UI to our game. This time we're going to add some menus. So there's going to be a main menu at the beginning of the game, and then a game over screen at the end. And so I'll just kind of go ahead and show these to you one at a time. So here's the main menu. It just kind of has the title of the game. There's a play button, and then it lists out some of the controls here. And then here's the game over menu. It just has options to restart the game and quit. And then as you can see right now, everything's kind of layered over top of each other. And when we enter play mode, we can still kind of move our player around, and our game starts playing already. So we're definitely going to want to fix that. So first thing we're going to do is we're just going to go ahead and create a menu controller. This is just a regular Unity mono behavior. You see that I have serialized fields for the main menu UI, game over UI, and the HUD UI. And then at start, I just go ahead and set the main menu UI to active, and then disable the game over and HUD UIs. Then we'll come back over to Unity. We'll go to our game controller game object, and I'll go ahead and add that menu controller on there. And then here we can drag in our main menu UI, our game over menu UI, and then our HUD UI. So now when we enter play mode, you see that by default, we just have the title screen here. However, we still can, move around and shoot and everything like that. And the play button actually does not do anything. So let's just go ahead and basically disable gameplay first. So here I've gone ahead and created two data components. Here's going to be the enable input tag. And this one we're going to basically add to our player. And we're only going to collect input from our player if this enable input tag is active. And the other one is going to be the enable spawning tag. And then this one's going to be associated with the enemy spawner. So we're only going to spawn enemies if this enable spawning tag is on that entity. Okay, so here let's go to our get player input system, and instead of doing a require singleton for update on the player ship tag, let's actually just go ahead and change this to a require singleton for update on the enable input tag. So basically this means this update method is only going to run to gather the input if that enable input tag is present on any entity in our game. Next up, we'll go ahead and open the spawn enemies system class, and then we're actually going to go down to our spawn enemies job, and we can add another attribute here, and this is a really handy one where we can do a with all type of, and then here we're going to be doing the enable spawning tag. So basically doing this with all attribute here, this is going to add this type of entity to this entity query here. So basically anything that does not have this enable spawning tag, it's not going to match this query. So basically this whole spawning system is not going to run. Also, we can do other things that you might expect. So we could do like say a with none, or we could do a with any. It's just really nice that they've included those attributes right there. So now we'll go ahead and enter play mode, and you'll see that our game is effectively paused. I can't move around with WASD, I can't shoot with the space bar, and we don't have any enemies spawning across the screen and trying to shoot at us when we're in the menu. So now the next thing is to actually make this play button function so we can actually, enter play mode and then start moving our ship around and shooting things. Okay, so we'll come back to our menu controller and we'll just add a couple more fields here. So the first one is we're going to do a private world for our default world. We will be needing this a little bit later, but we will also use that to get our entity manager here. And then so we'll just go ahead and get these in the awake. So we'll set default world equal to world.default game object injection world, and then we can get our entity manager off the default world.entity manager. And so again, we do need to do this because we are in a mono behavior, and if we do want to do any entity operations, we will need that entity manager off of our default world here. And of course, the default world is this default game object injection world. So after start, let's go ahead and make a public void, which is on button start game. So first we'll just set up our UI. So we'll say our main menu UI dot set active is false, and then the HUD UI is a set active of true. Now we're going to go ahead and get our player ship entity, and now we can't just do a get singleton here because this is part of a mono behavior, so we don't have access to say that get singleton entity here, and we can't use the entity manager to do a get singleton or anything like that. So I'll just go ahead and create a new method for the get player ship entity, which returns an entity. And so basically the way that we do this is we can define an entity query, and then we can get the singleton entity off that entity query. So we'll do a var player ship query, and of course we can use the entity manager to create entity query, and we'll do a component type dot read only type of player ship tag, and that's basically all that we need for our query on there. And then we can just do a return player ship query dot get singleton entity. So basically we're just going to create a little entity query using the component type of player ship tag, which we know only returns one entity. And then we can just do a return player ship query dot get singleton entity. And then so once we have our player ship entity, we can use the entity manager to go ahead and add a component, which is the enable input tag. Of course, again, we're going to be adding that to our player ship entity. Now let's do something very similar for the enemy spawn entity. And this time we'll just go ahead and build this enemy spawn query using the type of spawn point reference as well as the spawn timer. And just go ahead and return the get singleton entity here. And then we can do an entity manager dot add component, enable spawning tag onto the enemy spawn entity. So we'll come back over to Unity, we'll go to main menu, and we'll find the play button here, and then for our on click we'll go ahead and drag in the game controller game object, and then this will be under the menu controller on button start game. Let's go ahead and enter play mode. You see that again we can't press any of the movement keys, and then when we hit play, we're now in the game, we can move around, and the enemies are now spawning and shooting at us, and we can shoot back and make sure our score is still incrementing and everything like that. Wonderful. Okay, so at this point we can now enter play mode and basically enter the game here. The next thing that we're going to do is just go ahead and add actually a C# event, and this is going to fire once our player gets destroyed. And then what it's going to do is it's going to show the game over screen. And one thing that you'll also see that's happening, if I kind of zoom out here, it may be kind of tough to tell, but basically ships are still spawning. If we go over into our dots hierarchy, you'll see that ships will continue to spawn every couple of seconds in here. So one thing that we're going to want to go ahead and do is just go ahead and disable that enemy spawning as well. So we're going to go ahead and define this event as well as fire it from the destroy entity system. Now, if you remember back from when we originally created this, I mentioned that there was a reason that we had to use this entities.forEach here, and this is basically that reason, that is because we are using a C# event, which we will be able to use inside this entities.forEach as long as we do a without burst and run on the main thread. However, we can't do it in an iJob entity because we would basically need to have one of the fields of that iJob entity be the event, and it's not going to let us do that because it's a managed type. So here we can just go ahead and define a public delegate void. We can just call this, say, the game event delegate. So maybe, for example, later on we could have like a on start game or some other type of events that we want. But we'll just go ahead and create a public event of type game event delegate. This will be for the on game over. Now you remember inside these entities.forEach, we do need to capture any variables here. So we can do a var on game over equals on game over. And then so what I'll do is at the top here, I'll do a quick component check where I say if has component, and this would be the player ship tag on the entity do destroy. In here, then we can just go ahead and do an on game over (dot invoke, and the question mark basically just confirms that it is not null. So long as it's not null, we'll just go ahead and invoke that event. And then one thing that we do need to remember is we do need to add the without burst option to this entities.forEach function here, because this is a managed data type, so we have to run it without the burst compiler. Now we need to actually subscribe some things to the event so things can happen in our game when the event gets fired. So down at the bottom, I'm going to go ahead and create another method here. This will just be a private void show game over screen. And all this is going to go ahead and do is just set the game over menu as active, and then go ahead and disable the HUD UI as well. So that is the method that we want to run. Now we can just do this in the on start. We'll just go ahead and do a default world dot get existing system. This would be the destroy entity system, and then we can get the on game over events, and then we'll go ahead and add the show game over screen to it like that. Then we'll go over to the spawn enemy system inside the on start running. We'll do a world.getExistingSystem destroy entities system dot on game over, and this time what we're going to do is actually just go ahead and do kind of a little bit of a lambda expression here, and this will basically just allow us to set the enabled property of this system equal to false. So basically every system has this enabled property with a flag where we can either enable it or disable it. And then so basically all that we're going to do here is when the on game over event is fired, we'll just go ahead and disable this system here. Okay, so now let's go ahead and enter play mode here. Again, we can't move around or anything. We'll go ahead and press play. We can still fire our weapon and destroy other ships, and our score is counting up. Now let's go ahead and get into that game over state by destroying our ship here. And then you see the on game over menu popped up just as we want it to. And then if we do look over on the dots hierarchy, you'll see that we're not spawning any new enemy ships here. So then the next thing that we need to do is just go ahead and add in functionality for the restart and quit buttons. So the on button quit game, this one's super easy. We can just do an application.quit just like that. Now for restarting the game, I'm going to do this in a little bit of a hacky way. Basically what we're going to do is just nuke and reload everything. That's kind of what I found is sort of the easiest way to just kind of showcase how to do a basic level restart here. Basically what's going to happen is we're going to destroy all the entities within our game, and then also destroy all systems, because if we were just to say, load another scene or something like that, all of our systems are still going to be active. And that we've done a bunch of things kind of within the, like on start running methods, and we're saving some, variables onto the systems. And so if we were to just basically just destroy the entities and reload the scene, sure, we'd get the entities back, but a bunch of our systems would break because we would kind of need to essentially reinitialize a lot of the systems with the new versions of the entities in the world. So it does get a little bit more complicated to do kind of a clean restart of the game, if you will. So again, I feel the easiest way just to showcase for now is to just, nuke everything and restart fresh. So here we can go to our entity manager, and we'll do an entity manager.destroy entity. Inside here, we can pass in an entity query, and then there's one thing that we can do is the entity manager.universal query, and that will literally just get every single entity in the world associated with that entity manager and just go ahead and destroy that. Now again, our systems are still going to be running at this point, but what we can do is just do a default world.dispose, and that's going to essentially dispose all of the systems in our game. Now we don't want them to go away forever. So what we can do is a default world initialization dot initialize. And then in here we pass in what we want the name of the world to be, which in this case is just going to be default world. And then we can just use the regular Unity scene manager to do a scene manager dot load scene. And then we'll do a scene manager dot get active scene dot name. So we'll just go ahead and reload that same scene here. Then of course we'll just come back to Unity, make sure that we go to our restart button and go ahead and set the on click functionality equal to be the on button restart game. And we'll do something similar for the on button quit game here. Okay, so now we'll enter play mode and we'll go ahead and quickly get to the game over event here. Just wait for us to get destroyed by this enemy here. So now we can just go ahead and hit restart, and you'll see that we have restarted. However, there are some warnings and some error messages in the console here. The first one, this unloading scene, this one I haven't figured out a way to work around. This is basically just, a warning saying that you can't reload the same scene for some reason. I don't know why I've been getting that, but nonetheless, it doesn't really hurt our game, so we can just kind of ignore that one for now. And then so these next two are basically complaining about the get target system. It doesn't like the way that we're actually getting this singleton entity. So you see that basically what's happening is in the on start running, we're trying to get this player ship entity, but we don't exactly have it. So there's a couple things we can do. One, we can go ahead and do a require singleton for update player ship tag, but that doesn't completely resolve our issues. Another thing that we are going to have to do is inside the on create, I'm gonna go ahead and set the enabled property equal to false. So it's not actually going to go ahead and update this system here. And then I'll go back to the menu controller, and in the on button start game, let's go ahead and do a default world dot get existing system, get target system, and then we'll just go ahead and set enabled equal to true. And then when we set enabled equal to true in the menu controller, this on start running function is going to run again. So it's just going to go ahead and get that singleton entity here. So now when we come back over to Unity, let's just go ahead and get destroyed by this enemy right here. And then now when we restart our game, you see that we only still have that same one warning message that I can't figure out how to get rid of. If you do have any ideas about how to get rid of that, definitely let me know. But you'll see that we've basically resolved any issues with restarting our game there. So at this point, we do have a pretty competent game that's playable from front to back. We can restart the game, so we have a little bit of a gameplay loop here. But I think there's still just a little bit more that we can add in terms of, polish and juice to just make the game feel a little bit more alive. So right now we're going to go ahead and add in some visual effects and sound effects to make this, really feel like a real legit game. Okay, so over in Unity, I've just gone ahead and created this shot effects prefab. It's just a regular game object prefab. You see that it has a trail renderer component that starts with a width of 3.5, and then after a little bit, it just kind of, drops off in this little curve here. So we have this nice little trail renderer here. And then here are the rest of the parameters. You'll see that we do have a little bit of a gradient going on. The only other thing that I've really added to this is also an audio source where I've passed in this shot sound that I got off of opengameart.com. And you'll see that it's just set to play on awake. It doesn't loop or anything like that, but it does have the 3D sound settings set just so we can kind of have a little bit of spatial audio happening in our game here. And then basically what we're going to want to do is just go ahead and spawn one of these every time that we spawn a shot. And similar to what we've done before, is we're just going to go ahead and do a copy transform to game object. So our shot entity can go ahead and copy its position and rotation over to our shot effects game object. Okay, so I've just gone ahead and created a new data component here. One thing that you'll notice is I'm doing a public class as opposed to a public struct. This public class will basically allow us to use any managed data component type. So we can use, game objects or any other mono behaviors on here. So this is something that we're probably going to be using very frequently if we are, integrating any ECS stuff with mono behaviors. And so this is basically known as a managed data component because it has managed types available to us. Still just implementing regular iComponent data. And this time I've just gone ahead and done a public game object for shot effects. We will be adding another game object prefab in here, and that's for kind of the explosion effects that happen when an entity gets hit. But we'll come back to that later. So for now, we'll just come over to Unity, and on our game controller entity, we'll go ahead and add on the shot game object prefabs, and we can go ahead and drag in our shot effects right there. Okay, so I'm going to go ahead and create a new system here. This will be the spawn shot game object object system. Basically, this is going to run on any shot that does not already have an existing companion game object. And then we're just going to go ahead and instantiate one of those into the world and then set up our copy transform to game object here as well. So what I'm going to do is just keep a reference to the game object for the shot game object, and go ahead in the on start running, we'll go ahead and get a reference to the game controller entity just by doing a get singleton entity shot prefab. Now you'll notice that this is the base shot prefab, that first one that we did, that's that like the entity version of the shot prefab, not the shot game object prefab. The reason that we have to do this is because we have to pass in a non-managed data component type into this get singleton entity. And we do need a actual reference to the entity so that we can do an entity manager.get component object, and this would be of type shot game object prefabs off of our game controller entity. And we will want to get a reference to that shot effects here. So let's go ahead and set the shot game object equal to that. Now in the onStart running, we're going to go ahead and define an entities.forEach. So what we're basically going to want to do here is we're going to want to read the translation of this entity just so we can kind of know where initially we want to spawn that game object into the world. And then we also will need a reference to this new shot entity because we are going to be doing a little bit of operations on it. Now this entity query is not all that complex. This is going to run on everything with the translation component, which we don't necessarily want to happen. So let's go ahead and do a dot with all for the shot tag, which is something that we've already gone ahead and defined. And then we'll also do a with none of type copy transform to game object. So this basically is just looking for any shot that does not already have a companion game object. So what we can do here is do a var new shot game object equal to object dot instantiate, and then we'll go ahead and want to pass in the game object prefab. Again, we do need to capture that, so we can do a var shot game object equals the shot game object there. So we'll go ahead and instantiate that shot game object at the translation.value, and then we can just do a quaternion.identity there. Next up, we're going to need the entity manager to do a couple of operations. So we'll do an entity manager equals entity manager. And here we're just going to go ahead and use the entity manager to add the component of the copy transform to game object, of course, to the new shot entity. And then we'll also do an entity manager dot add component object to our new shot entity. And this is going to be the new shot go dot transform. So again, in order to get this copy transform to game object to work, we do need a reference to the game object's transform. And the reason that we're using an entity manager here as opposed to say an entity command buffer, which is ideally what we would want, is because we can't actually do this add component object in the entity command buffer, at least as of right now. And because we are doing structural changes in here, we do need to at the end do a dot with structural changes. We also need to do this without burst because we are doing a managed object in .instantiate here. And then lastly, we do still need to run that on the main thread. So now we will come over to Unity, enter play mode, and you'll see that we now have these awesome trail effects coming out of the ships here, and we do also have those sound effects happening here. Now you'll notice something a little bit weird, kind of a little bit of a weird effect going on when we're like destroying these entities. You'll see that it kind of like the tail end kind of goes away in a weird way. If we look over in our hierarchy, we have just like a ton of these shot effects, and then looking over in the scene view, we have all these audio things here. So basically what's happening here is when the entity shot gets destroyed, it's not automatically cleaning up its companion shot game object. So let's come back to our destroy entity system, and then we'll go ahead and add in just a little bit of a cleanup here. So right here, we'll just go ahead and do an if has component copy transform to game object entity to destroy. We'll go ahead and get the companion game object by doing an entity manager dot get component object transform off the entity to destroy, and then we do a dot game object because again we're just getting the base transform, and then we just need to do the dot game object off of that. And then we can go ahead and do an object.destroy, passing in the companion game object. Now, just keep in mind that this is basically going to mean, any companion game object is going to be destroyed. In some cases, we may not want that to happen, where if, say, the entity gets destroyed, we want that game object to persist in the world. Or maybe if we get a little bit more complex and we have some sort of, pooler or something like that, this is kind of how we would handle basically returning this to the pool. Okay, so now let's go ahead and enter play mode, and you'll see when the shots disappear, you'll see the whole trail render disappears because that game object is being cleaned up. And then if you look over in the scene view, you see that we don't have all those little gizmos for all those audio listeners as well. Okay, so the next thing that we're going to go ahead and do is add some collision effects. So basically, when one of these shots collides with a ship, we're going to go ahead and spawn a little explosion into the world just to add, a little bit more, again, kind of life to this game. So here's this explosion effects prefab that I made here. You'll see that it's basically just a particle system. If you do want to, replicate this for yourself, here's all the things that you need to know here. Of course, I will have all this stuff available with the project files included with this video. There are some of the renderer settings, and then I've also gone ahead and added an audio source for another of these short explosions. Again, this is just going to go ahead and play on awake, and it does also have some 3D audio associated with it. So we'll come over to the shot game object prefabs, and we'll add another public game object for the shot explosion. So then back on the game controller entity, just go ahead and drag the explosion effects into the shot explosion. Okay, so I'll just go ahead and create this spawn effects on collision system. And then so, pretty much similar to what we did in the previous system, we'll just go ahead and, have a local reference to this shot explosion. And then we'll get that off of the game controller entity, doing the get component object and getting the actual shot explosion on there. And we'll be doing another entities.forEach. So of course we'll need to go ahead and save a local reference to the shot explosion. Just go ahead and capture this. And then so we'll go ahead and do an entities.forEach, looking for anything with this shot collision component. Again, the shot collision is basically that particular component that we populate whenever a collision takes place. So we know the position of the collision as well as the entity that we collided with. So here what we can do is we'll just go ahead and check if shot collision.hitEntity.equals entity.null. If that's the case, just go ahead and return out of here. We only want to run the following steps if we actually collided with an entity. And so we'll just go ahead and get the hit position here. And remember, we can get this from the shot collision.position. That is something that we calculated earlier on when we were actually detecting the collision. And so here we can do an object.instantiate. Of course, we'll go ahead and spawn the shot explosion at the hit position on quaternion.identity. Now, in order to do this, again, we go ahead and run this without burst on the main thread. And then one other little optimization that we can do here is go ahead and do a with change filter on the shot collision. So this is basically, only going to be running when new collisions are taking place. So now when we enter play mode, we can kind of wait for some shots to come through. And when our player gets hit, you'll see that these explosions are now basically spawning into the world. And you can also hear these sound effects. And same thing when we shoot at enemies, we're spawning these little explosions into the world right where that collision took place, and we are hearing those explosions happen as well. So that's exactly what we want to happen, and it's looking really cool. And one thing that I do want to point out, if I just go ahead and pause the game real quick, you'll see that we do have a bunch of explosion effects here, and they're all just kind of cluttering up in our scene. Again, there's nothing that's really cleaning these up, so we do have to manually clean these up here. Luckily, that's easy enough to do. We'll just go ahead and create a mono behavior. One thing that you may not know is you can actually turn the start function into a coroutine just by doing private IEnumerator start. And then here we can just do a yield return new wait for seconds, the destroy time here that will pass in. Once that's happened, we'll just go ahead and destroy the game object. So simple as that. We'll just come over to our explosion effects prefab here, go ahead and add in the explosion effect cleanup, and we'll just destroy it after 1 second here. And then so now we can have all those explosions happen, and we'll go ahead and pause the game, and you'll see that we do not have any explosions in our hierarchy at all. I think the next thing that we want to go ahead and do is just something that I wanted to show off because it is kind of an important feature of using ECS is basically being able to do material property overrides. And these material property overrides will basically just allow us to maybe apply a specific color to an entity. In this case, we're just going to be using them to basically flash the ship white for just a very brief moment when it gets hit. So it just kind of, flashes real quick just to, again, sell the effect that it's getting hit a little bit more. So basically the way this is going to work, whenever a collision is detected on essentially our parent ship, which again has all the transform components and everything like that, we're going to basically reference our rendering component, and then we're going to add this material property override on it to just flash it white for a brief moment and then go ahead and remove that. So here we'll go ahead and create a new data component called ship render entity, and this is basically what's going to allow us to reference the ship renderer from our main parent entity. And then we'll come over to our ship authoring and we'll go ahead and add a new serialized field for the ship render entity, and then down inside the convert we'll just go ahead and do a dst manager.add component data to the new ship entity, and this will be a new ship render entity, and the value will be equal to conversion system.get primary entity. In here we can go ahead and pass in our ship render entity. So now we'll come back over to Unity, we'll go to our player ship, and then we'll go ahead and drag this renderer into the ship render entity. And then same thing with the enemy ship prefab. We'll go ahead and open this up and drag the renderer into the ship renderer entity and save those changes. So next up, we'll create this material flash timer. This is just going to be a public float called value. And what it's going to do is we're going to initialize it to a specific value that we'll set through the Unity editor, and then it'll actually decrement by delta time each frame. And then once that has expired, then we can just go ahead and remove this component as well as the material property override from our render entity. And if you don't quite understand what I mean by that, I'm going to go ahead and walk you through it right now. So I'll go ahead and create a new class. This will be the flash on collision system. Now this is basically just going to kick the flash off. So it's going to apply that material property override to our renderer entity. And then we're going to have another system that actually counts down that timer. So what I'm going to do is set up a couple public variables. So the first one is going to be a public float for called a color. We're using the float for because that is kind of the new Unity.mathematics more efficient type that works really nicely with the burst compiler and all. And then a public float for duration. So unfortunately, we can't just directly set these through the editor like we could with a mono behavior. We'll have to use a basically custom mono behavior in order to set these components. So I'll just go ahead and create a new mono behavior called flash properties. And then I'll go ahead and set up two serialized fields, one for the flash color and one for the flash duration. And you'll notice that we're using the color type because on here, it doesn't really matter that we're not using that more efficient type because basically we're just going to be setting that flash color to the float for color. And using this color right here, this just gives us that nice, color picker through the interface that we can use. So inside the on start, let's just go ahead and get a reference to the flash system. So of course we can get that by doing our world.default game object injection world.get existing system. And this is the flash on collision system. And then here we can go ahead and set the flash system.color equal to a new float for, where we can do flash color.r, flash color.g, flash color.b, and flash color.a. And then we can also set the flash system.duration equal to flash duration. Okay, so now we'll come back to Unity, go to our game controller game object, and then here we can add in the flash properties, the flash color. Let's go ahead and set this equal to white with an alpha value of 1, and the flash duration will be 0.07 seconds. Okay, so now we'll create the flash on collision job. This of course will be an iJob entity, and you see that I've gone ahead and created the whole thing. I'll just kind of walk through what this code does real quick. So you do see that it is burst compiled, and we are only going to be running it with the change filter of shot collision. In here we have the ship render entity lookup. This is going to be a read-only component data from entity, of course of type ship render entity. And then what this will allow us to do is when we know the entity that we hit, we can use that to get its ship renderer entity and then basically apply the flash properties to that. You do see that I have a parallel entity command buffer, and then of course I'm also just passing in the float for color and the flash duration here. In the actual execute, of course, I have a sort key for my entity command buffer, and then again we're going to be reading in from a shot collision. So in here we're just going to go ahead and first get a reference to that hit entity for the shot collision.hit entity. We'll just do a quick null check on it here. If it's null, just go ahead and return out. Next thing that we're going to do is do a ship render lookup dot try get component. So this is going to be kind of, combining a couple steps that we've done previously into one. So the try get component, this will basically see, hey, does this hit entity have a ship renderer on it? If it does, just go ahead and pass it out to this render entity variable here. And then if we do not, then we'll just go ahead and return out of here. Then we're also just going to go ahead and do a quick null check on that render entity right there. Of course, if it's null, just go ahead and return out of here. But now when we have the render entity, we can use the entity command buffer to go ahead and first on the render entity, and remember we need to do render entity.value because this render entity is the component type. We'll go ahead and add a new material flash timer with the value equal to flash duration. And then we'll also go ahead and add this, which is a built-in component. So this is the URP material property base color. So basically what these material property overrides do is they basically override specific things on the base color. And I'm not going to get too deep into it right now because I did do a video going over this, but basically there are a number of efficiency gains that can take place just by using these property overrides as opposed to a whole new material. And then of course we'll just go ahead and create this job here, pass in all the proper components that we need, and then do a schedule parallel. And of course, make sure that we're doing the ECB system.add job handle for producer, so all the dependencies get set properly. So now when we enter play mode, something interesting is going to happen because it's not completely finished yet, but watch, when we get hit, the player ship is just going to turn white because it just basically adds that material property override component, which is now overriding it. And same thing when we hit any of the entities, they're just going to turn white and stay white. Now we actually just want to add a little bit of a system in so we can basically have them just only flash white instead of stay completely white for the entire time. Okay, so now we're going to go ahead and create our final system of this entire video, which is the flash material system. I'm just going to kind of go through it real quick because most of this should be familiar. We're doing an nsim entity command buffer here. And then of course, just going to schedule this flash material job, which we will schedule parallel. The flash material job in here, inside this execute function, we're just going to go ahead and do this on the flash entity. Of course, have a sort key for the ECB. And then we're doing a read and write access to this flash material timer here. And I should also point out that I do have the withal for the URP material base color because we want to make sure that that component is present. So basically what we'll just go ahead and do is just decrement this timer by delta time. If it is greater than 0, just go ahead and return out of here because that's just kind of normal. We don't need to do anything extra. However, if it is less than or equal to 0, that means that the timer has expired, and then we're good to just go ahead and remove the component, which is the material flash timer, as well as the URP material property base color, so that we just go back to the default instead of the overrided material. Okay, boom. And so with that, we are basically done with our game here. So you'll see that now when we enter play mode, you see that the ships basically flash white when they get hit. So that happens to our player ship as well as the enemy ships. And everything is being cleaned up and displaying as exactly as we would want it to. And then the last thing that I'm going to do before we package this game up and build it, let's just go ahead and add some background music here. So I'm going to go ahead and create an empty game object. This will be for the background music. We'll go ahead and add an audio source. For the audio clip, we'll do this observing the star. And we can just have this play on awake and loop. Then real quick, I'm just going to go ahead and create this background music controller where it has a singleton instance. If the singleton already exists, we'll just go ahead and destroy the current game object. Otherwise, if it doesn't, we'll set that instance and also set it to do not destroy on load. So basically when we nuke and reload everything, the background music is going to persist. And then on the background music, we'll just go ahead and add on the background music controller. And go ahead and enter play mode. You see that we do have some background music playing right away. We still do have the sound effects for shooting and explosions and everything. Let's just go ahead and get completely destroyed here. And then now we'll go ahead and restart the game, and we'll listen closely to make sure that our music doesn't skip a beat or anything. And yeah, I think we're good. And go ahead and just enter play mode. Music's just continuing to play here. Can still move around and shoot and everything like that. And UI is still continuing to function, so everything is working, and we're ready to package this up, make a build of it, and share it with the homies. All right, so make sure that we save our scene. Now, in order to make a build, we can't just go up to File and then build and run and do all the build settings as we normally would. We actually have to create a build configuration asset. So I'm gonna go ahead and go into my assets folder and the settings folder. We'll just go ahead and do a right click and do a create build configuration, empty build configuration, and we can just call this build config. Now we can get really crazy with these build configurations, and there's a lot of cool and interesting things that we can do, but I'm just going to keep it pretty simple for the time being, just so we can just create a basic build of the game that we can share with our friends. So this build configuration asset, we can basically add components to it to configure our build config. So the first one that I'm going to add is just a general settings here, and this will basically allow us to set a project name. So I can call this, say, Turbos Space Shooter. Company name, Turbo Makes Games. This will be version 1.0. Now we're going to go ahead and add another component, which will be the scene list. So this is basically going to, say which scenes that we're going to add. For scene infos, we'll say, go ahead and say add an element. This element scene asset, we'll just set this to our sample scene. So if you do have multiple scenes, we're gonna want to go ahead and add all these in here. And then lastly, the thing that we're going to go ahead and add is a classic build profile here. And the classic build profile, this will basically allow us to kind of configure some of the settings that we want. So in this case, I'm going to be building for the Windows platform. This is where you can set if you want it to be a debug, development, or release build. Of course, if you use a development or debug build, you can have it hook into the Unity profiler to get some extra performance metrics on it. So that's actually the preferred way to get performance metrics, because there is a little bit of an overhead with the player loop and everything like that. But for now, we're just going to go ahead and create a release build here, and all these other settings look good to me. So we'll just go ahead and hit the apply button down at the bottom, and then here we can have options to do a build and run, or clean. So let's just go ahead and say build and run. You see, it does just take a few moments to go ahead and build here. All right, and so we have a build succeeded. And so now it's going to go ahead and open up here, and then you'll see that we have this Turbos Space Shooter. Of course, it's playing this beautiful background music. And we can go ahead and enter play mode here and start, playing around on our game. So again, everything's working. We can kind of move, shoot, aim. We have the parallax effects happening. Our score UI is updating. Our player health UI is updating. Again, we're, showing these explosions, and our players are flashing and everything like that. And so yeah, this is a complete game, and now it's good. We can share this out on itch.io or share it with our friends or anything like that. So yeah, now we have this complete bullet hell game that is actually kind of fun to play, to be honest. And just confirm that we can still restart the game and come back in, and yeah, so that's just about it there. And we'll also just confirm that we can actually quit out of the game as well. Perfect, that is exactly what we want to see. And boom, just like that, we are all done. We have created a full game using Unity's data-oriented technology stack and their entity component system. Really do hope that you enjoy this full journey going through sort of the theory behind data-oriented programming, going into the project setup, the ECS actual tutorial section of the video, and then integrating with some of the more common Unity features that we can get, graphical effects and sound effects and everything like that. I definitely had a ton of fun making this project for this video, recording this over multiple recording sessions, and then now I'm looking forward to editing about 12 hours of video footage. So that's going to be my life over the next couple days. Anyways, once again, if you did find this video helpful, I'd really appreciate it if you share it with someone who you think might find it interesting, or maybe some online community that you're part of. That definitely would be the best way to show your appreciation for this video. Also, I'd appreciate it if you hit that like button. Also, subscribe to the channel for lots more videos about Unity's data-oriented technology stack and their entity component system. I definitely have a lot of really exciting things planned now that I have this whole big introduction video out there, so definitely stay tuned for those. By the way, if you do have any questions for me or suggestions for future videos, you can always leave those down in the comments section below, or come join us over on Discord over at tmg.dev/discord. And with that, I just wish you well on your continued learning and exploration to all sorts of things about the Unity game engine. I hope this inspired you to create something cool with Unity's data-oriented technology stack, and then it gets you excited for some of the new features that are coming in the 1.0 release of DOTS sometime next year. Anyways, with that, I do hope that you all have a fantastic rest of your day, and I'll see you in the next one.